Langchain experimental data anonymizer deanonymizer matching strategies case-insensitive matching strategy. This matching strategy ignores case sensitivity when identifying and replacing sensitive information in text data. For example, if the mapping includes the key John Doe and the input text contains John Doe, the strategy will still replace John Doe with the corresponding replacement value. This approach is useful when the exact case of the sensitive information is unknown or irrelevant. Inputs. This is the text that will be anonymized. This text can contain sensitive information. This is a mapping of sensitive information to replacement values. For instance, the mapping might associate the sensitive information John Doe with the replacement value redacted. Outputs. This is the anonymized text, where sensitive information has been replaced with the corresponding replacement values from the mapping. Steps. The input text is converted to lowercase. This ensures that case differences between the sensitive information and the input text are ignored. The mapping is applied to the lowercase input text. This means that any instances of sensitive information, regardless of their case, are replaced with their corresponding replacement values. The anonymized text is converted back to its original case. This step restores the original capitalization of the text, preserving the original formatting as much as possible. Prerequisites. The mapping of sensitive information to replacement values is a critical prerequisite. This mapping dictates which sensitive information will be anonymized and what values will replace them. Without this mapping, the strategy cannot function. Fine-tune parameters. There are no fine-tune parameters for this strategy. This means that the strategy operates in a fixed manner, without any customization options. Challenges and fixes. One potential challenge is that the original case of the text is lost during the anonymization process. For example, if the input text contains John Doe, the anonymized text might become redacted. This can be addressed by preserving the original case of the text. This involves tracking the original case of each character and applying it to the replacement values after anonymization. Another challenge is that this strategy might not be suitable for all scenarios. For example, if the sensitive information is case sensitive, this strategy may not be able to correctly identify and replace it. Consider a username John Doe that should not be replaced with redacted. In this scenario, John Doe is not the same as John Doe and would not be anonymized. For cases where case sensitivity is important, a case-sensitive matching strategy should be used. This strategy would only replace sensitive information if the case matches exactly. This ensures that only the intended sensitive information is anonymized. Langchain experimental data anonymizer deanonymizer mapping format duplicated operator. Inputs. The original data that needs to be anonymized. For example, a customer list with names, addresses, and phone numbers. A mapping that defines the anonymization rules. This mapping can be based on different anonymization techniques, such as pseudonymization or tokenization. Outputs. The anonymized data, where sensitive information is replaced with anonymized values based on the provided mapping. Steps. Applying the anonymization mapping to the original data. This involves replacing sensitive information with anonymized values according to the mapping rules. For example, replacing real names with pseudonyms. Generating a de-anonymization mapping, which allows for the recovery of the original data from the anonymized data. This is useful for scenarios where the anonymized data needs to be de-anonymized later on. Prerequisites. Data format. Comma-separated values CSV format. a common format for storing data in tabular form, where each row represents a record and each column represents a field. JavaScript Object Notation JSON format, a widely used data exchange format that represents data as key-value pairs, arrays, and nested objects. Anonymization method. Pseudonymization involves replacing sensitive information with non-sensitive alternatives while maintaining a link between the original and anonymized values. For example, replacing a customer's real name with a pseudonym. Tokenization involves replacing sensitive information with random tokens, which are unique identifiers that have no inherent meaning. This method makes it difficult to link the anonymized data back to the original data. Fine-tune parameters. The level of granularity in the mapping, which determines the extent of anonymization. A more granular mapping anonymizes more information, while a less granular mapping anonymizes less information. The chosen anonymization method, which determines the specific technique used to anonymize the data. Different anonymization methods have different trade-offs in terms of security, privacy, and usability. Challenges and fixes. Data inconsistencies. Data cleaning involves identifying and correcting errors or inconsistencies in the original data before anonymization. This helps ensure the accuracy and integrity of the anonymized data. Mapping collision. Collision resolution strategies are methods for handling cases where multiple sensitive values map to the same anonymized value. These strategies aim to minimize collisions and ensure unique mappings for different values. Performance bottleneck. Optimized mapping algorithms are used to improve the efficiency and speed of the anonymization process, especially when dealing with large datasets. These algorithms can optimize the mapping process and reduce processing time. Langchain experimental data anonymizer deanonymizer matching strategies case-insensitive matching strategy. This strategy enables case-insensitive matching during data anonymization and de-anonymization. Inputs. The original data that needs to be anonymized. For example, a list of customer names like John Doe, Jane Doe, and Alice Smith. A mapping of original values to their anonymized counterparts. This mapping ensures that the same original value is consistently replaced with the same anonymized value. For example, John Doe A1, Jane Doe A2, Alice Smith A3. Outputs. The anonymized data. The original data with all values replaced with their corresponding anonymized values. For example, A1, A2, A3. A mapping of anonymized values to their original values. This reverse mapping allows for successful de-anonymization. For example, a first John Doe, A2 Jane Doe, A3 Alice Smith. Steps. The original data and all values in the mapping are converted to lowercase. This allows for case-insensitive matching, ensuring that values like John Doe and John Doe are treated as identical. The actual matching and anonymization process takes place. The lowercase original data values are matched against the lowercase mapping values and replaced with the corresponding anonymized values. Prerequisites. The original data must contain values that are case-sensitive. For example, John Doe and John Doe should be treated as distinct entities. The mapping of original values to anonymized values is required for the anonymization process. This mapping should contain all original values in lowercase to ensure consistent case-insensitive matching. Fine-tune parameters. There are no fine-tune parameters for this strategy. The anonymization process is solely dependent on the provided original data and mapping. Challenges and fixes. Matching failure due to case sensitivity can occur if the original data and mapping are not consistently cased. To overcome this, the strategy converts all data to lowercase, ensuring consistent matching. De-anonymization becomes difficult if the anonymized values cannot be easily mapped back to their original values. This strategy provides a reverse mapping of anonymized values to their original values, enabling successful de-anonymization. Langchain experimental data anonymizer deanonymizer matching strategies exact matching strategy. This strategy aims to reverse the anonymization process by precisely matching anonymized data with its original counterpart. It leverages direct comparisons between anonymized and original datasets to identify corresponding entries, restoring the original identifiers or attributes. Inputs: the anonymized data, which is a version of the original data with sensitive information obscured or replaced with generic values. It might involve replacing names with unique identifiers, masking email addresses, or substituting numerical values with ranges. The original data, which contains the complete and unmasked information. This serves as the reference point for the de-anonymization process. Outputs: the de-anonymized data, which represents the original dataset with its sensitive information restored. This output is achieved by successfully matching anonymized data points with their corresponding original entries. Steps: the process begins by identifying the anonymized data and its original counterpart. This step involves recognizing the specific transformations applied during the anonymization process to establish a clear link between the two datasets. Next, the anonymized data is compared with the original data. This comparison is performed using a defined matching criteria or threshold, ensuring that only data points that meet the criteria are considered for de-anonymization. Prerequisites: the presence of unique identifiers is essential for the exact matching strategy to work. These identifiers act as keys for linking anonymized data points with their original counterparts. For instance, user IDs can be employed as unique identifiers. Each user in the dataset would have a distinct ID, allowing for straightforward mapping between anonymized and original records. Fine-tune parameters: the matching threshold represents a parameter that controls the strictness of the matching process. This threshold determines the level of similarity required between anonymized and original data points to be considered a match. A higher threshold implies stricter matching, while a lower threshold allows for more flexibility. Challenges and fixes: data changes, such as modifications in values or the addition of new entries, can disrupt the matching process, leading to inaccurate de-anonymization. Pre-processing techniques can be employed to mitigate this challenge. These techniques involve cleaning and standardizing the datasets to minimize discrepancies and ensure accurate comparisons. Limited data availability for de-anonymization can hinder the effectiveness of the exact matching strategy. Insufficient data might prevent finding a sufficient number of matches, resulting in incomplete de-anonymization. Data augmentation techniques can be implemented to address this issue. These techniques involve generating synthetic data points that are similar to the original dataset, but with varied characteristics, increasing the pool of data available for de-anonymization. Langchain experimental data anonymizer deanonymizer matching strategies NGRAM fuzzy matching strategy. This strategy uses a specified number of consecutive characters NGRAMs to find matches between anonymized and original data. The goal is to reverse the anonymization process, restoring the original values to the data. Inputs: anonymized data. This refers to the data that has been modified to protect sensitive information. It could be text, where names, addresses, or other personally identifiable information have been replaced with generic terms. Or it could be numerical data where specific values have been obfuscated. Original data. This is the original, unmodified data set that contains the sensitive information. It is used as the reference point for de-anonymization. Outputs. De-anonymized data. This is the output of the de-anonymization process, where the original values have been restored as much as possible based on the matching of NGRAMS. The aim is to achieve a high level of accuracy and avoid false positives. Steps. Split anonymized and original data into NGRAMS. This involves breaking down both the anonymized and original data into overlapping sequences of characters of length n. For example, if n is 3, the phrase "Hello World" would be split into hail, l, yo, lo, ow, wo, wo, o. Compare NGRAMS using a similarity metric like Jacquard similarity. This step involves calculating the similarity between NGRAMS from the anonymized and original data sets. Jacquard similarity is a common metric that measures the ratio of shared NGRAMS to the total number of unique NGRAMS. Identify potential matches based on similarity scores. Once NGRAM similarity scores are calculated, potential matches are identified based on a predetermined threshold. Engrams with a similarity score above the threshold are considered potential candidates for de-anonymization. Refine matches by considering context and other factors. This step aims to improve the accuracy of the de-anonymization process by taking into account the surrounding context of the potential matches. This might involve analyzing the position of the matched NGRAMS within sentences, considering the overall meaning of the text, and incorporating other known information about the data. Prerequisites. Anonymized and original data should have some overlapping information. This means that the anonymized and original data sets should share some common elements that allow for the matching of NGRAMS. For example, if the original data contains names and the anonymized data has replaced those names with generic terms like person X or individual Y, there would be sufficient overlap to allow for NGRAM matching. The more overlap, the better the accuracy of the de-anonymization process. Example values for prerequisite 1. For example, imagine you are working with patient records. The original data might include the patient's full name, address, and diagnosis. The anonymized data might have replaced the patient's name with a unique identifier and the address with a generic location. If the diagnosis information is preserved in the anonymized data, there is still some overlap that can be used for matching. The choice of NGRAM size should be appropriate for the data. The size of the NGRAMS, the value of n, influences the granularity of the matching process. If n is too small, there might be many false positives, as common NGRAMS could appear in both anonymized and original data. If n is too large, there might be too few matches, making it difficult to de-anonymize the data effectively. The ideal size of n depends on the complexity of the data and the desired level of precision. Example values for prerequisite 2. Consider a data set containing names and addresses. A small NGRAM size might lead to many false positives because common NGRAMs like Saint or Avenue could appear in multiple addresses. A large NGRAM size might not find enough matches for accurate de-anonymization because unique NGRAMs might be infrequent in the data. Fine-tune parameters. Ngram size. This parameter directly controls the length of the NGRAMS used for matching. As described previously, The choice of NGRAM size has a significant impact on the accuracy and efficiency of a de-anonymization process. Similarity threshold. This parameter defines the minimum similarity score required for two NGRAMs to be considered a potential match. A lower threshold will lead to more potential matches but could increase the number of false positives. A higher threshold will be more selective but might miss some valid matches. Challenges and fixes. False positive matches due to common NGRAMs. This is a common challenge in NGRAM-based de-anonymization. Some NGRAMs may be very frequent and appear in both the anonymized and original data sets, leading to false positives. Consider context and refine matches to mitigate this issue. The strategy often incorporates additional mechanisms to refine the potential matches. This can involve analyzing the context of the matched NGRAMs within the larger text, comparing the frequency of NGRAMs in the anonymized and original data sets, and incorporating other domain-specific knowledge to eliminate false positives. Low precision due to limited NGRAM information. If the NGRAM size is too small or the data is very complex, there might not be enough unique NGRAMs to achieve a high level of precision in de-anonymization. Increase NGRAM size or use additional matching strategies to address this issue. The approach could involve increasing the NGRAM size or combining NGRAM matching with other de-anonymization strategies, such as rule-based matching or machine learning models. This can improve the precision of the de-anonymization process by leveraging a wider range of information. Langchain experimental data anonymizer de-anonymizer matching strategies NGRAM fuzzy matching strategy. This strategy leverages fuzzy string matching algorithms to correlate anonymized data with its original counterpart. The goal is to establish connections between anonymized records and their original versions, enabling data de-anonymization or analysis while maintaining privacy. Inputs. Anonymized data. This refers to the dataset that has undergone anonymization techniques to protect sensitive information. Anonymized data could include obfuscated names, masked addresses, or generalized demographics. Original data. This is the original dataset containing sensitive information that was used to generate the anonymized data. It holds the true values of the attributes that have been anonymized. Outputs. Matched pairs. The strategy outputs pairs of anonymized and original data records that are identified as matches based on the applied fuzzy matching algorithm. This output provides a linkage between the anonymized and original data for analysis or de-anonymization purposes. Steps. 1. Pre-process data for fuzzy matching. This step involves preparing the data for effective fuzzy matching. It might include tasks such as removing irrelevant characters, e.g., punctuation, special characters, standardizing formatting, e.g., converting to lowercase, and handling inconsistent spellings. The goal is to create a consistent structure for the data that facilitates accurate matching. 2. Apply a fuzzy matching algorithm. This step involves applying a suitable fuzzy matching algorithm to compare the anonymized and original data. Fuzzy matching algorithms, like Levenshtein distance or Jaro-Winkler, calculate the similarity between strings, even if they have minor differences. For instance, Levenshtein distance measures the minimum number of edits, insertions, deletions, substitutions needed to transform one string into another. These algorithms enable matching records even if there are typos, variations in spellings, or small discrepancies in the data. 3. Filter and refine matched pairs. After applying the fuzzy matching algorithm, The resulting matches are filtered and refined to remove false positives and ensure high accuracy. This can involve setting a threshold for the similarity score, meaning only matches with a score exceeding the threshold are considered valid. Additionally, confidence scores can be assigned to the matches based on the strength of the similarity, allowing further refinement based on confidence levels. Prerequisites: data cleaning and normalization. Data should be cleaned and normalized before applying fuzzy matching. This involves addressing data inconsistencies, removing unnecessary characters, and ensuring a consistent format. For example, removing leading and trailing spaces, standardizing date formats, and handling duplicate entries. Selection of appropriate fuzzy matching algorithm. Choosing the right fuzzy matching algorithm is crucial for accuracy and efficiency. Considerations include the type of data, the expected level of noise or variations, and the desired accuracy. For example, if the data has many typos or variations in spelling, an algorithm like Jaro-Winkler might be more appropriate. Fine-tune parameters. Threshold for similarity score. This parameter sets the minimum similarity score required to consider a pair as a match. A higher threshold increases accuracy but may miss some valid matches. Matching algorithm parameters. Each fuzzy matching algorithm has its own parameters that can be adjusted to fine-tune the matching process. For example, the Levenshtein distance algorithm can be configured to weight different types of edits, insertions, deletions, substitutions differently. Challenges and fixes. Challenge 1: false positives due to high similarity between unrelated data. This issue arises when unrelated records have high similarity scores, leading to incorrect matches. For instance, two different people with similar names and addresses might be incorrectly matched. Fixes to challenge 1: adjust threshold. Increasing the threshold for similarity scores can filter out matches with lower similarity, reducing the chances of false positives. More specific matching algorithms. Using more specific matching algorithms, like those that consider additional attributes beyond name and address, can improve accuracy and reduce false positives. Challenge 2: missing matches due to low similarity between related data. This occurs when related records have low similarity scores due to significant variations or noise in the data. For instance, a person's name might be spelled differently in the original and anonymized data. Fixes to challenge 2: lower threshold. Lowering the threshold for similarity scores can increase the number of matches, potentially capturing more related records. More lenient matching algorithms. Using more lenient matching algorithms, which tolerate greater variations in the data, can enhance the chances of capturing matches with lower similarity scores. Langchain experimental, data anonymizer, Presidio anonymizer based summary. Langchain experimental, data anonymizer, Presidio anonymizer based summary. The Presidio anonymizer base class serves as a foundational structure for anonymizing text using Presidio. This abstract base class provides essential functionalities and outlines methods that must be implemented by concrete anonymizers, ensuring consistent and robust anonymization capabilities. Presidio anonymizer base class inputs. Text to be anonymized. The input to the anonymizer is the text that needs to be processed for privacy protection. For example, if a text contains personally identifiable information like names, addresses, or financial details, it needs to be anonymized before further use or sharing. Presidio anonymizer base class outputs. Anonymized text. The output of the anonymizer is the same input text but with sensitive information replaced with anonymized tokens. For instance, A name like John Doe might be replaced with 4x4x. Or an email address like john.doeexample.com might be replaced with xxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxxx When asked while still preserving pay. Structure and overall meaning of the text. Presidio Anonymizer base class steps. Instantiates a Presidio analyzer. This step involves creating an instance of the Presidio analyzer. Presidio is a library that provides the necessary tools for identifying and anonymizing sensitive information within text. It leverages sophisticated algorithms and machine learning models to recognize different types of entities, such as names, locations, dates, and financial data. Analyzes the text to identify entities. This step leverages the Presidio analyzer to scan pay provided text and pinpoint instances of sensitive information. The analyzer carefully analyzes the text, examining patterns and context to determine if a word or phrase represents an entity that needs anonymization. Applies anonymization techniques to the entities once Presidio identifies sensitive information. It applies appropriate anonymization techniques. These techniques could include replacing names with generic placeholders like 4x4x. Redacting email addresses or phone numbers by replacing portions with asterisks, like johndoe.com, or replacing dates with generic values like xxxxxxxxx. Employing techniques like tokenization or generalization to anonymize sensitive data without completely obscuring the underlying information. Returns the anonymized text after applying anonymization techniques. The Presidio Anonymizer base class returns the processed text with the sensitive information replaced with anonymized representations. This anonymized text can then be used in various applications where privacy considerations are crucial. Presidio Anonymizer base class prerequisites. Presidio installation. To utilize the Presidio Anonymizer base class, you need to install the Presidio library. You can install it using the Python package manager pip with the following command: pip install Presidio. Presidio configuration. Presidio's effectiveness relies on proper configuration. You need to set up various parameters, including model paths defining the location of the pre-trained models for entity recognition. Anonymization strategies. Selecting appropriate anonymization techniques for different entity types. Language settings. Specifying the language of the input text. Additional configurations. Tailoring settings to suit your specific anonymization needs, such as customizing the behavior of the anonymizer or incorporating domain-specific dictionaries for better accuracy. Presidio Anonymizer base class fine-tune parameters. Presidio Analyzer. An instance of Presidio Analyzer. This parameter represents a custom instance of the Presidio Analyzer. You can configure this instance with specific settings or models to fine-tune the analysis process. For example, you might want to use a custom model trained on a specific domain or industry to improve accuracy of entity recognition. Anonymization techniques. A list of anonymization techniques to apply this parameter allows you to specify the exact anonymization techniques you want to use for different entities. For example, you might choose to redact names, generalize locations, and replace email addresses with unique identifiers. By controlling the techniques used, you can tailor the anonymization process to meet your specific privacy requirements. Presidio Anonymizer base class challenges and fixes. Presidio might not identify all entities. While Presidio is a powerful tool, it might not always identify all sensitive information within a text. For example, it may struggle with unfamiliar terms, slang, or ambiguous phrases. Consider using custom models or fine-tuning to address this. You can train custom models using data specific to your domain. This allows Presidio to learn the patterns and terminology relevant to your use case, enhancing its ability to identify sensitive information. Alternatively, you can fine-tune the existing Presidio models by adjusting parameters or adding domain-specific dictionaries. This helps to improve the performance of the anonymizer for your particular data. Anonymization techniques might not be effective. The effectiveness of anonymization techniques can vary depending on the context and the sensitivity of the information being masked. Certain techniques might not adequately protect sensitive information, especially in cases where the anonymized text can still be linked back to the original data. Explore alternative techniques or adjust parameters to address this challenge. You can experiment with different anonymization techniques. Presidio provides a range of options, each with its strengths and weaknesses. Alternatively, you can adjust the parameters of existing techniques to fine-tune their behavior. For example, you can control the level of generalization, the length of redactions, or the type of tokenization used. By experimenting and adjusting parameters, you can achieve the desired level of anonymization while minimizing the impact on the usability of the text. Langchain Experimental CPAL Models System Setting Model. A model that generates system settings for applications. This model takes user requirements and application domain as input, and outputs system settings. Inputs. User requirements. This refers to the specific functionalities and features that the user expects the application to provide. For example, a user might require an e-commerce application to have a secure payment gateway, personalized recommendations, and a user-friendly interface. Application domain. This refers to the specific industry or area of operation of the application. For instance, an application domain could be healthcare, finance, or e-commerce. Knowing the domain helps the model understand the specific requirements and constraints of a application. Outputs. System settings. These are the configuration parameters that define the behavior and functionalities of the application. They include settings like database connections, API keys, security protocols, logging levels, and user access permissions. Steps. Analyze user requirements. This involves understanding the user's needs and translating them into specific functional requirements for the application. This might involve identifying key functionalities, desired performance levels, and user interface preferences. Identify system components. This step involves breaking down the application into its constituent parts, such as user interface, data storage, backend logic, and communication protocols. Each component has specific settings that need to be defined. Define settings for each component. This step involves setting specific values for each component based on the analyzed user requirements and the application domain. This includes configuring database settings, specifying API endpoints, and determining access control policies. Generate system settings. This step involves compiling the defined settings for all components into a cohesive system settings file. This file serves as the configuration guide for the application, defining its overall behavior and functionalities. Prerequisites. Understanding of user requirements. The model needs to have a clear understanding of the user's expectations and needs. This involves analyzing user stories, conducting user interviews, and reviewing user feedback. Knowledge of application domain. The model should be familiar with the specific industry or area of operation of the application. This includes understanding the relevant regulations, business practices, and technical standards in the domain. Fine-tune parameters. Domain-specific settings. These are settings that are specific to the application domain. For example, a healthcare application might require specific data privacy settings, while a financial application might need to comply with security regulations. User preference settings. These are settings that are tailored to the user's preferences. This might include personalizing the user interface, setting language preferences, or customizing notification settings. Challenges and fixes. Ambiguous user requirements. If user requirements are not clear or well defined, the model might struggle to generate accurate settings. Clarify requirements. This involves working with the user to understand their needs in detail. This can be done through follow-up discussions, conducting user research, or providing prompts to clarify the requirements. Unforeseen system interactions. There might be unexpected interactions between different system components that could lead to errors or unexpected behavior. Implement robust error handling. This involves implementing mechanisms to handle unexpected scenarios and prevent crashes or data loss. This might include logging errors, implementing exception handling, and designing fault-tolerant systems. Overfitting to specific domain. If the model is trained on a single domain, it might struggle to generalize to other domains. Introduce generality. This involves incorporating data from multiple domains during training to broaden the model's understanding and improve its ability to generalize. Summary of langchain experimental data anonymizer faker procedure mapping gets pseudo-anonymizer. Mapping creates a mapping between data types from the procedure library and faker's data generation functions, enabling the conversion of real data into synthetic substitutes for anonymization purposes. Inputs. Procedure data types represent various types of sensitive information, including phone numbers, email addresses, and names, that need to be anonymized to protect privacy. For instance, phone number would be one such data type. Faker's data generators are functions that produce synthetic data, such as phone numbers, email addresses, and names, that resemble real data but are not associated with specific individuals. For instance, phone number would be one such generator function. Outputs. A mapping that connects procedure data types to corresponding faker data generators. This mapping allows for the automated anonymization of sensitive information by replacing real data with synthetic equivalents. Steps. The process iterates through each procedure data type, one by one. For each data type, it finds the equivalent faker generator function that produces similar data. This step effectively translates procedure's data type vocabulary into faker's data generation capabilities. A dictionary is created to store the mapping. This dictionary associates each procedure data type with its corresponding faker generator. This mapping represents the foundation of the anonymization process, enabling the translation of real data into synthetic substitutes. Prerequisites. Procedure is a library that helps in identifying and masking sensitive information within text. To use this mapping, Procedure needs to be installed. The installation is achieved through the command pip install procedure, which downloads and installs the procedure library on your system. Faker is a library that generates realistic fake data, such as names, addresses, and credit card numbers. To use the mapping, Faker needs to be installed. The installation is achieved through the command pip install Faker, which downloads and installs the Faker library on your system. Fine-tune parameters. This mapping function does not have any fine-tuning parameters. This means that the mapping is predefined and does not require any user-specific adjustments. Challenges and fixes. There might be cases where a Presidio data type does not have a directly corresponding faker generator. For example, Presidio might identify a type like bank account number while faker might not have a specific generator for such a type. In such cases, a generic faker generator that produces random strings of a similar format can be used as a fallback. Alternatively, the mapping can skip these data types if no appropriate faker generator is found. The format of the data generated by faker might not perfectly match the requirements for anonymization. For example, a phone number generator might produce a number in a different format than the original number. To address this, custom faker generator functions can be used. These custom functions can be tailored to generate data in the desired format, ensuring consistency with the original data. Alternatively, post-processing steps can be applied to the generated data to adjust its format to meet the specific requirements. Langchain experimental, fallacy removal, base, fallacy chain summary. This class aims to identify and remove fallacies from text. It leverages language models to analyze text and detect logical fallacies. Fallacies are common errors in reasoning that can weaken arguments and mislead audiences. The goal is to enhance the clarity and soundness of text by eliminating these logical flaws. Inputs. The input to this class is text that needs to be analyzed for fallacies. This text can be in various formats, such as a string, a document, or a list of sentences. Outputs. The output of this class is text with identified fallacies removed. The class strives to preserve the original meaning of the text while eliminating fallacious arguments. The output will be in a similar format as the input. Steps. 1. Analyze input text for potential fallacies. This step involves using a language model to scan the text and identify phrases or arguments that might contain fallacies. The model will assess the logical structure and reasoning within the text to flag potential errors. 2. Identify and remove fallacies. Once potential fallacies are identified, the class will use a combination of rules and language model capabilities to confirm and remove fallacious arguments. This may involve replacing fallacious statements with more accurate or neutral language or rephrasing arguments to address the underlying logical errors. Prerequisites.
A list of common fallacies. This list provides a foundational understanding of the types of fallacies the class can detect. Some common fallacies include ad hominem. This fallacy attacks the person making the argument, rather than addressing the argument itself. For example, you can't trust anything he says because he's a convicted felon. Straw man. This fallacy misrepresents an opponent's argument to make it easier to attack. For example, you want to ban all guns? So you're saying criminals should be free to do whatever they want? Appeal to authority. This fallacy relies on the authority of a source to support an argument, even if the source is not an expert in the relevant field. For example, my doctor said that vaccines cause autism, so they must be dangerous. A language model capable of identifying fallacies. This model needs to have been trained on a large corpus of text, including examples of fallacious reasoning. The model should be able to understand the logical structure of arguments and identify patterns that indicate fallacies.
Fine-tune parameters. Threshold for identifying fallacies. This parameter determines how strict the class is in identifying fallacies. A higher threshold will result in fewer fallacies being identified, while a lower threshold will result in more fallacies being identified. This can be adjusted based on the specific requirements of the application. Challenges and fixes. Identifying complex fallacies. Some fallacies are more subtle and difficult to identify than others. This can be challenging for even advanced language models. Use a more sophisticated language model. More advanced models, such as those trained on specialized datasets of logical reasoning, may be better able to identify complex fallacies. Removing fallacies without altering the meaning of the text. This is a delicate balance. Removing fallacies should not change the overall meaning or intent of the text. Use a language model that understands the nuances of language. A model that can understand the context and meaning of the text will be better able to remove fallacies without altering the meaning. This might involve using a model with advanced natural language processing capabilities. Langchain experimental generative agents, generative agent summary. A framework for building and deploying complex language-based agents. Generative agents are designed to interact with the world through language, learning and adapting to new situations. They can be used to automate tasks, provide information, and even generate creative content. Inputs. User input, referring to the text or commands provided by the user to the agent. For example, a user might ask an agent what is the capital of France, or book a flight to Paris. Contextual information, referring to the knowledge and data that the agent has access to, including past conversations, external data sources, and the agent's internal memory. This context helps the agent understand the user's intent and provide relevant responses. For example, if the user has previously asked about travel destinations, the agent might use this information to provide more tailored recommendations. Outputs. Agent actions, referring to the steps that the agent takes to fulfill the user's request. These actions might involve querying a database, searching the web, or interacting with other systems. For example, an agent responding to the query book a flight to Paris might take actions such as accessing a flight booking website, searching for available flights, and selecting a suitable option. Agent responses, referring to the text or actions that the agent provides to the user. This might include providing information, completing tasks, or generating creative content. For example, an agent might respond to the query "What is the capital of France?" with the answer Paris, or to the query "Book a flight to Paris" by displaying a list of available flights and allowing the user to select one. Steps. Receive user input, referring to the first step where the agent listens to the user's request, accepting their input in the form of text or voice. Process input and retrieve relevant information, referring to the step where the agent analyzes the user's input to determine their intent and any relevant information from its knowledge base or external sources. For instance, if the user requests book a flight to Paris, the agent might need to access its database of flight information, understand the user's desired travel dates, and potentially retrieve relevant information from weather websites or travel blogs. Generate response, referring to the step where the agent creates a response to the user based on the processed information and its internal knowledge. This might include generating text, performing specific actions, or even creating multimedia content. For example, an agent could respond to the query "What is the capital of France?" by generating the text Paris, or to the query "Book a flight to Paris" by presenting a list of available flights and associated details. Execute actions, referring to the final step where the agent performs any necessary actions to fulfill the user's request. For example, if the user asks the agent to book a flight, The agent might need to execute actions such as communicating with an online booking system, selecting a flight option, and confirming the booking with the user. Prerequisites: langchain, referring to a framework designed to provide a common interface for interacting with various language models (LLMs), memory systems, tools, and chains, making it easier to build complex language-based applications. LLMs, large language models, referring to advanced deep learning models trained on large text datasets and capable of understanding and generating human-like text. This includes models like GPT-3, Lambda, and BERT, which can be leveraged for tasks like text generation, translation, summarization, and question answering. Memory, referring to the ability of the agent to store and retrieve information from previous interactions, allowing it to learn from past experiences and provide more contextually relevant responses. Tools, referring to external applications or services that the agent can interact with to perform specific tasks. These might include APIs, application programming interfaces for searching the web, accessing databases, or controlling external devices. Chains, referring to sequences of steps or functions that the agent can execute in a specific order, allowing for complex workflows and problem solving. For instance, a chain might involve accessing a database, processing the retrieved information, and then generating a response. Python, referring to a widely used high-level programming language commonly employed for developing web applications, data analysis, and machine learning. 3.7 or higher, referring to the minimum required version of Python for running the langchain framework and its associated libraries. Fine-tune parameters. Agent memory, referring to the configuration and settings related to the agent's memory, including the size, structure, and methods used for storing and retrieving information. This allows for fine-tuning the agent's ability to learn and adapt to new situations. For example, an agent might be configured to store only the last few user interactions or to maintain a detailed history of all past conversations. Agent reasoning capabilities, referring to the ability of the agent to analyze information, draw inferences, and make decisions based on its knowledge and understanding of the world. This can be fine-tuned by adjusting the agent's reasoning model, such as choosing different logic-based reasoning systems or incorporating additional knowledge graphs. For example, an agent might be trained to better understand user intent, identify inconsistencies in information, or generate more complex and nuanced responses. Challenges and fixes. Memory management, referring to the challenge of efficiently storing and retrieving large amounts of information without compromising performance or accuracy. Use efficient memory strategies, referring to various techniques for optimizing memory usage, including using specialized data structures, data compression algorithms, or techniques for forgetting or summarizing less relevant information. Action execution, referring to the challenge of reliably and accurately performing actions in the real world, including interacting with web services, controlling physical devices, or manipulating data. Ensure robust action execution, referring to strategies for handling errors, unexpected situations, and ensuring the successful completion of actions. This might involve incorporating error handling mechanisms, retries, and monitoring systems to ensure the agent's actions are executed as intended. Agent reasoning, referring to the challenge of enabling agents to reason logically, understand complex relationships, and make informed decisions based on their knowledge and understanding of the world. Improve agent reasoning abilities, referring to various techniques for improving the agent's reasoning capabilities, such as integrating knowledge graphs, implementing advanced logic-based reasoning systems, or leveraging techniques from artificial intelligence research such as Bayesian networks and probabilistic reasoning, handling complex tasks, referring to the challenge of breaking down complex tasks into smaller, manageable steps that the agent can execute effectively, implement task decomposition and planning, referring to techniques for dividing complex tasks into smaller subtasks, planning the order in which these subtasks should be executed, and coordinating the execution of these subtasks to achieve the overall goal. Agent safety and alignment, referring to the challenge of ensuring that the agent behaves ethically and responsibly, avoiding harmful actions or biased outputs, ensure safe and ethical agent behavior, referring to measures and strategies for aligning the agent's behavior with human values, including establishing safety guidelines, implementing mechanisms for monitoring and controlling the agent's actions, and incorporating ethical considerations into the agent's decision-making process. Langchain experimental fallacy removal models logical fallacy. This YAML file describes a model designed to identify logical fallacies in text. Logical fallacies are errors in reasoning that can render an argument invalid. This model aims to help users understand and avoid these errors in their own arguments and to identify them in the arguments of others. Inputs. The input to the model is text. This can be a paragraph, an article, a conversation, or any other form of written communication. The model will analyze the text to identify potential logical fallacies. Outputs. The model's output is a description of the fallacy type detected in the input text. This could include, for example, ad hominem, straw man, appeal to emotion, or false dichotomy. The model will also provide an explanation of the fallacy, outlining why the argument is flawed and how it deviates from logical reasoning. For example, an explanation for ad hominem might point out that the argument attacks the person making the claim, rather than addressing the claim itself. Steps. The model first analyzes the input text, breaking it down into its constituent parts and identifying the main claims and arguments presented. Next, the model uses its knowledge of common logical fallacies to identify potential errors in reasoning. This process may involve pattern recognition, keyword matching, and the application of semantic analysis techniques. Finally, the model provides its output, presenting the identified fallacy type and a clear explanation of why the argument is flawed. Prerequisites. The model requires a comprehensive knowledge of common logical fallacies. This knowledge base should include the definitions of various fallacy types, their common forms, and examples of how they are used in real-world arguments. Challenges and fixes. One challenge for the model is handling complex arguments, especially those that involve multiple premises, nested claims, and intricate reasoning structures. To overcome this challenge, the model can leverage advanced natural language processing (NLP) techniques, such as dependency parsing, semantic role labeling, and discourse analysis. These techniques allow the model to understand the relationships between different parts of the argument and to identify fallacies that occur at a deeper level of analysis. Another challenge is distinguishing fallacies from valid arguments. Some arguments may contain elements that superficially resemble fallacies but are actually sound. To address this challenge, the model must be trained on a diverse dataset that includes both fallacious and valid arguments. This training data should be carefully annotated with labels indicating the presence or absence of logical fallacies. By exposing the model to a wide range of examples, it can learn to distinguish between genuine fallacies and valid reasoning patterns. Fine-tune parameters. The fallacy detection threshold determines the model's sensitivity to potential fallacies. A higher threshold will make the model more likely to flag potential fallacies, even if they are subtle or borderline. Conversely, a lower threshold will make the model more conservative in its identification of fallacies. The explanation generation style determines how the model explains the detected fallacies. Some models might use a more formal, academic style, while others might opt for a more conversational and accessible tone. The chosen style should be appropriate for the intended audience and the context of the analysis. Langchain Experimental Generative Agents Summary. A framework for building and managing large language model LLM-powered agents. These agents can interact with the world, learn, and adapt based on their experiences. For instance, an agent could be designed to manage your email, book appointments, or even generate creative content based on your inputs. The information the agent receives to trigger an action. This can be a user query, a notification, or any other relevant data. For example, a user query like book a flight to Paris would be an input for a travel agent. The agent's current state reflects its internal knowledge and understanding of the situation. This includes its past actions, memory of previous interactions, and any other relevant context. For example, a virtual assistant might remember past conversations with the user to tailor its responses. Outputs. The agent's actions are the steps it takes to fulfill a request or perform a task. For example, a travel agent might book a flight and a hotel, then send a confirmation email. The agent's response to the user is the information it provides back. This could be a summary of the actions taken, a piece of information, or a creative output. For instance, the travel agent might send a confirmation email with flight and hotel details as its response. Steps. The agent receives input from the user or the environment. This could be a text message, a voice command, or an event triggering an action. For instance, a chatbot receives a text message from the user. The agent analyzes the input and determines the appropriate action based on its knowledge and objectives. This might involve processing natural language, retrieving relevant information from its knowledge base, or making a decision based on a set of rules. For example, a chatbot might identify the user's request as wanting to book a flight. The agent takes action based on its analysis. This might involve interacting with external systems, such as booking a flight or sending an email, or generating creative content. For example, the chatbot might query a travel API to find flights. The agent communicates its results back to the user. This could be a summary of the actions taken, a piece of information, or a creative output. For example, the chatbot might display the flight options found and ask for confirmation from the user. Prerequisites. Access to an LLM is essential for powering the agent's capabilities. This includes application programming interface API access to services like OpenAI, Hugging Face, or Google AI. For example, an agent might use the OpenAI API to generate creative text content. Memory management is crucial for keeping track of past interactions and context. This ensures the agent can maintain a coherent conversation and respond appropriately to user requests. For instance, an agent might store previous conversations to provide personalized responses based on the user's history. Fine-tune parameters. The agent's personality refers to its communication style and tone. This can be adjusted to match specific user expectations or brand identities. For example, an agent could be programmed to be friendly, informative, or formal. The agent's knowledge base is the collection of information it uses to understand and respond to user requests. This can be tailored to specific domains or areas of expertise. For example, a financial advisor agent might have a knowledge base containing financial data, market trends, and investment strategies. Challenges and fixes. Agent hallucination occurs when an agent generates incorrect or nonsensical information. This can be addressed by using reliable data sources, implementing fact-checking mechanisms, and providing clear feedback to the agent. For instance, an agent could be trained on a large corpus of factual information and use a knowledge graph to verify the accuracy of its responses. Agent getting stuck refers to situations where the agent fails to progress towards a goal or complete a task. This can be addressed by implementing robust error handling mechanisms, providing alternative paths for the agent to follow, and enabling retry mechanisms for failed actions. For example, an agent could be designed to handle exceptions and retry failed requests, or to offer alternative solutions when an initial plan fails. Agent losing context refers to the agent's inability to remember and utilize past information in its responses. This can be addressed by utilizing memory management techniques, using context windows to maintain a consistent understanding of the conversation, and employing techniques for summarizing past interactions. For example, an agent could use a conversational memory system to store past interactions and retrieve relevant information when responding to the user. Langchain experimental data anonymizer deanonymizer matching strategies NGRAM fuzzy matching strategy. This strategy aims to match anonymized data to its original form by leveraging fuzzy matching techniques based on NGRAMS. Inputs. Anonymized data refers to data that has been transformed to conceal sensitive information, like names or addresses, while still preserving its utility. It is commonly used in data privacy efforts, particularly when sharing data for research or analysis. Original data represents the data in its raw form, before any anonymization processes have been applied. It contains the sensitive information that needs to be protected, but also holds the true context and relationships within the data. Outputs. Matching pairs are the results of the matching process, revealing the connections between anonymized data entries and their corresponding original data entries. These pairs are essential for de-anonymization, allowing the recovery of the original information while maintaining the anonymization goal. Steps. Calculate NGRAMS for both anonymized and original data. N-grams are consecutive sequences of n items, usually words or characters extracted from the text, which are used to represent the underlying structure and patterns within the data. Compare NGRAMS using fuzzy matching algorithms. Fuzzy matching algorithms account for minor variations or errors in the data, allowing for matches even when the data is not perfectly identical. This is crucial when dealing with anonymized data, as the process can introduce small changes. Identify matching pairs based on similarity scores. By comparing the NGRAMS extracted from anonymized and original data, the algorithms generate similarity scores that indicate the degree of resemblance between the two sets of data. Based on these scores, the strategy identifies the most likely matching pairs. Prerequisites. Cleaned data refers to data that has undergone pre-processing steps like removing irrelevant characters, correcting typos, and standardizing formatting. This ensures accurate NGRAM extraction and reduces the risk of false matches. A real-world example is standardizing dates across a dataset so that 12,102,023 and 20,231,210 both are considered the same. Tokenization is the process of breaking down text into smaller units, called tokens. This can involve separating words, punctuation, or even characters, depending on the specific task. It is essential for NGRAM extraction and allows for better comparison between anonymized and original data. For example, splitting the sentence "This is a sentence" into the tokens "This is a sentence." Fine-tune parameters. Engram size is a parameter that determines the length of the NGRAMs to be extracted. Larger NGRAMs capture more context and potentially improve matching accuracy. Smaller NGRAMs are more sensitive to noise and may lead to more false positives, but can be useful when dealing with shorter text snippets. Similarity threshold is a value that defines the minimum similarity score required for two NGRAMs to be considered a match. A higher threshold is more stringent and may lead to fewer matches, while a lower threshold is more lenient and may result in more false positives. Challenges and fixes. High false positive rate occurs when the algorithm identifies matches that are not actually accurate. This can be caused by factors like the similarity threshold being too low, NGRAMs being too small, or data containing noise or inconsistencies. Adjusting the threshold to a higher value can mitigate the issue. Additionally, refining the NGRAM size by choosing larger NGRAMs can improve accuracy. Low recall, also known as low sensitivity, occurs when the algorithm fails to identify many genuine matches. This can be caused by the similarity threshold being too high, NGRAMs being too large, or the data containing significant variations. Increasing the NGRAM size can help in finding matches, especially if the text snippets are long and complex. Adjusting the threshold to a lower value can also improve recall, but it may also increase the number of false positives. Langchain experimental graph transformers, diffbot graph transformer summary. This graph transformer utilizes diffbot's application programming interface API to extract information from websites. Inputs: URL of the website to be analyzed. This is the web address of the website you wish to analyze. For example, a URL could be https://www.example.com. API key for diffbot. To use diffbot's API, you need an API key. You can obtain this key by creating an account with diffbot. Outputs: extracted data in JSON format. The information extracted from the website is returned in JSON format. JSON JavaScript object notation is a human-readable format used for data exchange. Steps: 1. Fetch the content of the provided URL. This step retrieves the HTML content of the website specified by the provided URL. 2. Send the content to diffbot's API for analysis. The HTML content fetched from the website is sent to diffbot's API. The API analyzes the content to extract specific information like articles, products, or reviews. 3. Receive and pass the JSON response from diffbot. Diffbot responds with the extracted data in JSON format. This JSON data is then passed into a structured format that can be easily understood and used by other applications. Prerequisites: 1. Diffbot API key. This is a unique identifier that allows you to access diffbot's API. You can get this key by creating an account on diffbot's website. Diffbot account. A diffbot account is required to access and use their API. It allows you to generate API keys and manage your usage. 2. URL of the website to analyze. The website address you want to analyze using diffbot. It is essential to provide a valid and accessible URL. Website URL. The complete address of the website, including the protocol HTTP or HTTPS and domain name. For example, https www.example.com. Fine-tune parameters. 1. API endpoint for diffbot. This refers to the specific URL endpoint within diffbot's API that you want to use for a particular task. Different endpoints are available for extracting different types of information. For example, an endpoint for extracting articles might be HTTPS API, diffbot, comv3 article. 2. Custom configuration options for diffbot's API. You can customize the behavior of diffbot's API by providing specific configuration options. These options could include specifying the type of information to extract, limiting the number of results, or filtering the content based on certain criteria. Challenges and fixes. 1. API key errors. Check for valid API key. If you get an error related to the API key, make sure you are using a valid key that is active and authorized. Double-check the key for typos and verify if your account is properly set up. 2. Network issues. Check for internet connection. Network issues can prevent the graph transformer from accessing the website or diffbot's API. Verify that your internet connection is active and stable. 3. Incorrect URL. Verify the URL. Make sure the provided URL is correct and points to the website you want to analyze. Verify the spelling, protocol HTTP or HTTPS, and the complete address. 4. Rate limits. Implement a rate limiting mechanism to prevent abuse and ensure fair access to the API. Diffbot might enforce rate limits. This means restricting the number of requests you can send within a specific time period. Implement a mechanism to track your request count and pause or slow down requests if you approach the limit. 5. API errors. Handle API error responses. Diffbot's API may return error messages if something goes wrong. Handle these responses appropriately by identifying the error type, logging it, and taking necessary actions like retrying the request or notifying the user. 6. Data parsing issues. Ensure correct JSON parsing. If the extracted data from diffbot is in JSON format, make sure you have the necessary tools and libraries to correctly parse the JSON and extract the information you need. Use robust parsing libraries and handle potential errors during parsing. 7. Incorrect API endpoint. Verify API endpoint. Double-check that you are using the correct API endpoint for the specific information you want to extract. Consult diffbot's documentation to confirm the endpoint URL. 8. Incorrect data format. Format data before sending to diffbot. If the website content is not in a format that diffbot can easily analyze, you might need to format or preprocess the data before sending it to the API. This might involve removing unnecessary HTML tags, cleaning up the text, or restructuring the data. 9. Invalid configuration. Validate custom configuration options. If you are using custom configuration options for diffbot's API, make sure they are valid and consistent with the API's requirements. Validate the options before sending the request. 10. Unreachable website. Verify website reachability. If the website is unavailable or inaccessible, the graph transformer will not be able to extract information. Verify that the website is online and reachable. 11. Diffbot downtime. Implement retry mechanisms. Diffbot's API might be temporarily unavailable due to maintenance or technical issues. Implement mechanisms to retry requests if you encounter downtime. You can use exponential backoff techniques to gradually increase the delay between retries. Langchain experimental graph transformers, diffbot, nodes list. This component extracts a list of nodes from a response received from a diffbot application programming interface. It is a part of langchain, a framework for building language models. The nodes extracted can be of different types depending on the specified node type in the fine-tune parameters. For example, the nodes extracted can be articles, images, or videos. Inputs. A response received from the diffbot application programming interface is the input to this component. This response contains information related to the requested data. For example, the response could contain information about an article retrieved from a web page. The response is in a format specific to the diffbot API and needs to be passed to extract the relevant information. Outputs. The output of this component is a list of nodes. Each node represents a piece of information extracted from the diffbot API response. The type of node depends on the requested node type in the fine-tune parameters. For example, the output could be a list of articles, images, or videos. Steps. The first step is to pass the response received from the diffbot application programming interface. This involves interpreting the structure of the response and identifying the relevant information. This step is important to extract the information in a structured format. The second step is to extract the nodes from the passed response. This involves identifying the relevant information based on the specified node type and extracting it from the response. For example, if the node type is articles, the component will extract the article title, author, and content from the response. Prerequisites. This component requires a diffbot application programming interface key to access the diffbot API. The key can be obtained from the diffbot website at diffbot.com developers. The key allows the component to authenticate with the diffbot API and access its services. This component requires a diffbot API endpoint to interact with the diffbot API. The API endpoint is a specific URL that the component uses to send requests to the diffbot API. The diffbot website provides documentation on the various API endpoints at diffbot.com docs-API. The specific endpoint used depends on the type of information being requested. Fine-tune parameters. This component requires a node type to be specified as a fine-tune parameter. The node type determines the type of information that will be extracted from the response. For example, if the node type is articles, the component will extract articles from the response. Different node types can be specified, such as images, videos, products, etc., depending on the information being requested. Challenges and fixes. One challenge is the rate limiting imposed by the diffbot application programming interface. This means that there is a limit on the number of requests that can be made to the API in a given time frame. To address this, a rate limiter can be used. A rate limiter is a mechanism that controls the rate at which requests are made to the API. This prevents exceeding the rate limit and ensures smooth operation. Another challenge is specifying the incorrect node type in the fine-tune parameters. This can lead to the component extracting unwanted information or failing to extract the desired information. To address this, it is important to verify the node type specified in the fine-tune parameters against the information available in the API response. This ensures that the node type is accurate and that the component extracts the relevant information. Langchain experimental Graph transformers. Diffbot type option. Diffbot is a web data extraction service that provides application programming interfaces (APIs) to retrieve structured data from websites. These APIs enable users to extract relevant information, such as product details, articles, or reviews, from a web page in a structured format. Inputs: the URL of the website from which you want to extract data. This URL acts as the input to the Diffbot API, providing it with the target web page for data extraction. For instance, you could provide the URL of an online store product page, a news article, or a social media profile. Outputs: the output of a Diffbot API call is structured data extracted from the input website. This structured data could be in various formats like JSON or XML, depending on the specific API used. The extracted data might contain information such as product names, prices, reviews, article text, or social media post details. Steps: first, you need to initialize a Diffbot API client using your API key. This client acts as your interface to the Diffbot service, allowing you to make requests and receive responses. Once the client is initialized, you send a request to the Diffbot API, specifying the target URL and the desired extraction type. The API request includes parameters defining the type of data you want to extract. For example, you might use the article API to extract text content from a news article, or the product API to retrieve product details from a website. After sending the request, the Diffbot API processes the target web page and returns the extracted data in a structured format. This response data is passed by your application to process and use the information. Prerequisites: a Diffbot application programming interface API key is required to access and use the Diffbot services. This key acts as your authentication token, allowing Diffbot to identify you and track your API usage. The Diffbot application programming interface API URL specifies the address of the Diffbot server you will interact with. This URL is used by your API client to send requests and receive responses from the Diffbot service. Fine-tune parameters. The API endpoint defines the specific API you want to use for your data extraction task. Different Diffbot APIs are available for specific tasks, such as extracting product information, articles, or social media posts. API parameters are used to fine-tune the data extraction process. These parameters allow you to control aspects like the data format, specific fields to extract, and any other relevant settings for the extraction task. Challenges and fixes. API rate limiting is a mechanism implemented by Diffbot to manage the number of requests you can make to their service within a given time frame. If you exceed the rate limit, your requests might be blocked or delayed. Use an API key with a higher rate limit to accommodate your increased usage needs. Diffbot offers different API key plans with varying rate limits, allowing you to choose a plan that best suits your application's requirements. Data parsing errors can occur when the extracted data is not in the expected format or structure. This can happen due to variations in website structure, updates, or changes in the data being extracted. Adjust the API parameters or data parsing logic to handle these errors. You can modify parameters like the extraction format or use more robust parsing algorithms to address inconsistencies in the data. API connection errors can occur if there are network connectivity issues, problems with the Diffbot server, or temporary disruptions in the service. Check your network connectivity and ensure that you are connected to the internet. Verify the status of the Diffbot server to ensure it is operational. If the issue persists, contact Diffbot support for assistance. Langchain experimental, graph transformers, diffbot, type option summary. A description of the langchain experimental, graph transformers, diffbot, type option object in YAML format. Diffbot is a third-party application programming interface that provides structured data from web pages. Diffbot uses a combination of machine learning and natural language processing to extract information from web pages. This information can be used in various applications, such as knowledge graph construction, data analysis, and web search. Inputs: URL of the web page from which to extract data. For example, you can provide a URL like https://www.example.com. Outputs: structured data from the web page, in a format that is easy to process and use. The output can be in JSON, XML, or CSV format. Steps: extract relevant data from the URL provided as input. This involves identifying the relevant sections of the web page and extracting the text and other elements from those sections. Transform the extracted data into a structured format, such as JSON or CSV. This involves cleaning the data, organizing it into a consistent structure, and adding any necessary metadata. Prerequisites: diffbot application programming interface key. Obtain an application programming interface key from the diffbot website. You will need this key to authenticate your requests to the diffbot application programming interface. Fine-tune parameters. Application programming interface endpoint to which you will send your requests. Parameters to specify the type of data you want to extract and the desired format for the output. Data. Challenges and fixes. Application programming interface rate limits. Diffbot has rate limits to prevent abuse of the service. Handle rate limits gracefully by implementing strategies such as exponential backoff, retrying requests with a delay, or using a queue to buffer requests. Data extraction errors can occur if the web page is formatted in an unexpected way or if the data is incomplete or inaccurate. Retry extraction with different parameters. Adjust the extraction logic to handle different web page formats, or use a fallback mechanism to provide a default value if the extraction fails. Langchain experimental, graph transformers.llm. Unstructured relation. An LLM-based graph transformer that can be used to extract relations from unstructured text. This approach utilizes a large language model LLM to analyze text and identify relationships between entities. The extracted relations are then represented as graph triples, providing a structured representation of the information contained in the text. Inputs: the input text that needs to be analyzed for relations. For example, the capital of France is Paris. A schema defining the relations to be extracted. This schema specifies the entities and their relationships, defining the structure of the extracted knowledge graph. For example, capital of country, city defining the desired relation to be extracted as a country and its corresponding city. Outputs: a list of relation triples, each representing a relationship extracted from the input text. For example, France, capital of Paris. Steps: the input text is first tokenized, breaking it down into individual words or units. The tokens are then analyzed to extract relevant entities, which are the subjects and objects of the relations. For example, France and Paris in the input text. The extracted entities are then analyzed to identify the relationships between them. This involves determining the connection or association between the entities, like capital of in the example. Based on the identified relationships, the relation triples are formulated. representing the extracted knowledge in a structured format. This triple is then used to construct the knowledge graph, a graph representation of the extracted relationships from the text. Prerequisites: a pre-trained LLM, a large language model trained on a vast dataset of text and code, capable of understanding and extracting relations from text. For example, a pre-trained LLM like GPT-3 or Jurassic 1 can be used to analyze text and identify the relationships between entities. A relation schema, a clear definition of the desired relations to be extracted. This schema specifies the entities and their relationships, defining the structure of the extracted knowledge graph. For example, capital of country, city defining the desired relation to be extracted as a country and its corresponding city. Fine-tune parameters, a relation schema, a clear definition of the desired relations to be extracted. This schema specifies the entities and their relationships, defining the structure of the extracted knowledge graph. For example, capital of country, city defining the desired relation to be extracted as a country and its corresponding city. LLM parameters. These parameters control the behavior of the LLM during the analysis. This includes parameters like temperature, top K, and top P, which control the randomness and creativity of the LLM during the analysis. Challenges and fixes. Entity extraction errors, incorrect identification of entities in the input text. To address this challenge, pre-trained entity recognition models can be utilized. These models are specifically designed to identify named entities, such as people, organizations, and locations, within text. These models can be fine-tuned to improve their accuracy and precision in identifying entities relevant to the specific domain of the input text. Incorrect relation identification, misinterpreting or incorrectly identifying the relationships between entities. To address this challenge, the LLM can be fine-tuned with domain-specific data, providing it with additional context and examples relevant to the target domain. This allows the model to learn and adapt to the specific relationships present within the domain, leading to more accurate relation identification. Summary of langchain experimental graph transformers. LLM graph transformer. An LLM-based graph transformer is a model that leverages the power of large language models (LLMs) to transform graphs, representing complex relationships and structures in data, for improved natural language understanding and generation. Inputs. Text. The input text provides context and information that is used to influence the graph transformation process. This text could be a document, a series of sentences, or a question, depending on the specific application. For example, if the input text is a news article about a company's financial performance, the LLM can use this information to modify the graph representing the company's relationships and connections to other entities. Graph. A graph is a data structure that represents relationships between entities, often represented as nodes and edges. These entities could be people, places, organizations, or concepts, and the edges represent the connections between them. For instance, a graph representing a social network might have nodes representing users and edges representing friendships between them. Outputs. Transformed graph. The output of the graph transformer is a modified graph, incorporating the information from the input text. The graph can be restructured, expanded, or contracted, depending on the LLM's analysis of the input text. For example, if the input text mentions a new business partnership, the graph transformer might add a new edge representing this partnership to the graph. LLM output. The LLM's own output which may include summaries, insights, or interpretations derived from the input text and graph. This output can further guide the graph transformation process, allowing the model to provide more nuanced and informed results. For instance, the LLM might generate a text explaining the implications of the new partnership identified in the input text, further enriching the understanding of the graph. Steps 1. Encode text using LLM. The input text is processed by the LLM to extract its meaning and generate a representation of its content. This representation could be in the form of embeddings, which are numerical vectors capturing the semantic meaning of the text. For example, the LLM might analyze the input text about a company's financial performance and generate embeddings that represent the key concepts like revenue, profit, and market share. 2. Transform graph based on LLM output. The LLM's output, often in the form of embeddings, is used to guide the transformation of the input graph. This transformation could involve adding new nodes or edges to the graph, changing the weights of existing edges, or merging nodes together, based on the information derived from the LLM's analysis of the input text. For instance, the LLM's output might indicate a relationship between a company and a new market, leading the graph transformer to add a new edge between the corresponding nodes in the graph. 3. Decode graph using LLM. The transformed graph is then processed by the LLM to generate a human understandable output. This output might be a summary of the transformed graph, a description of the changes made, or a set of insights derived from the graph. For example, the LLM might generate a textual description of the transformed graph, highlighting the newly formed business partnership and its potential impact on the company's financial performance. Prerequisites. LLM. A powerful language model. LLM is essential for processing the input text and guiding the graph transformation. LLMs are trained on massive text datasets and possess a deep understanding of language, enabling them to perform complex tasks like summarizing information, identifying relationships, and generating natural language outputs. For example, popular LLMs like GPT-3, GPT-4, and Llama 2 are capable of understanding the context of the input text and generating relevant insights that can inform the graph transformation. Graph database. A graph database is required to store and manage the input graph, enabling efficient retrieval, modification, and analysis of the relationships represented in the graph. Graph databases are specifically designed to handle complex relationships and structures, making them ideal for applications involving graph transformers. Examples of popular graph databases include Neo4j, dgraph, and ErangoDB. Fine-tune parameters. LLM model. The choice of LLM model plays a crucial role in the performance of the graph transformer. Different LLMs possess varying strengths and weaknesses in terms of their understanding of language and ability to generate relevant outputs. Fine-tuning the LLM model on specific tasks and data can improve its performance and ensure that it generates outputs tailored to the specific needs of the graph transformer. Graph embedding. Graph embedding refers to the process of converting graph data into numerical representations, which are easier for machine learning algorithms to process. Fine-tuning the graph embedding method can significantly impact the accuracy and efficiency of a graph transformer. Experimenting with different graph embedding techniques, such as Node-2-Vec or DeepWalk, can help optimize the performance of the graph transformer on specific tasks. Challenges and fixes. Overfitting to training data. Overfitting occurs when the model learns the training data too well. resulting in poor performance on unseen data. This can be addressed by using techniques like regularization, which penalizes complex models, and data augmentation, which artificially increases the size of the training data to prevent the model from memorizing training examples. For example, techniques like dropout or L1-L2 regularization can be employed to prevent overfitting. Data augmentation can involve creating variations of the training data by adding noise, changing the order of elements, or generating synthetic examples. Low performance on unseen data. When the model performs poorly on data it has not been trained on, it indicates a problem with generalization. This challenge can be mitigated by fine-tuning the model on diverse data, which exposes the model to a wider range of examples and improves its ability to generalize to unseen data. For instance, fine-tuning the model on a diverse dataset that includes different types of text, graphs, and tasks can improve its ability to handle various input scenarios and generalize to unseen data more effectively. Langchain experimental graph transformers, diffbot, simplified schema, extract structured data from web pages using diffbot's application programming interfaces. Diffbot is a web data extraction service that uses artificial intelligence to extract structured data from web pages. Inputs: the URL of the web page to extract data from. This URL represents the address of the web page you want to extract data from. For example, you might provide the URL of a news article, a product page, or a company website. The diffbot application programming interface key. This key allows you to authenticate your requests to the diffbot application programming interface. You obtain this key from your diffbot account. It acts as a unique identifier that verifies your access to the service. Outputs: structured data extracted from the web page. The extracted data is organized in a structured format, like a JSON object or a table, making it easier to analyze and use in applications. For example, you might extract information like article title, author, publication date, product name, price, or company contact details. Steps: input a web page URL. This step involves providing the URL of the web page that you wish to extract data from. It's like telling the diffbot service where to find the information. Send a request to the diffbot application programming interface with the URL and application programming interface key. You send a request to the diffbot application programming interface. This request includes the URL of the web page and your application programming interface key. The diffbot application programming interface then processes this request. Receive the extracted data from diffbot application programming interface. The diffbot application programming interface processes the request and extracts the data from the specified web page according to your chosen extraction method. The service then sends back the extracted data in a structured format. Prerequisites: diffbot application programming interface key. This key acts as your identity when using the diffbot service. You obtain this key by registering for a diffbot account. It's necessary for making API calls to the service. Web page URL. This is the address of the web page you want to extract data from. It could be an article, a product page, or any website that contains the information you are interested in. Fine-tune parameters. Application programming interface endpoint to use for data extraction. This refers to the specific part of the diffbot application programming interface you interact with to extract data. Different endpoints might be used for different types of web pages or for extracting specific types of data. Specific fields to extract from the web page. These are the specific pieces of information you want to extract from the web page. You might specify fields like the title, author, date, price, or any other information relevant to your task. Challenges and fixes. Application programming interface request errors. These are issues that occur when you send a request to the diffbot application programming interface. For example, you might encounter an error if your application programming interface key is incorrect, if the provided URL is invalid, or if the diffbot service is experiencing temporary issues. Check application programming interface key in URL validity. Ensure that your application programming interface key is correct and valid. Check if the provided URL is correctly formatted and accessible. Try accessing the URL directly in your browser to see if it loads successfully. Data extraction errors. These occur when the diffbot application programming interface fails to extract the data from the web page as expected. For example, you might encounter errors if the web page structure is complex or if the specific field you are trying to extract is not found on the page. Check application programming interface endpoint and fields to extract. Make sure that you are using the correct application programming interface endpoint for the type of web page you are trying to extract data from. Double-check that the fields you want to extract are actually present on the web page and are formatted in a way that diffbot can recognize. Langchain experimental graph transformers (LLM) create unstructured prompt. This function is responsible for creating an unstructured prompt suitable for a graph transformer. Large language model (LLM). The prompt acts as a clear instruction for the LLM, guiding it to analyze and process a given graph based on a specific task. Inputs. The graph, which is the primary input for the LLM. The graph represents a structured data format where entities and their relationships are explicitly defined. This representation enables the LLM to understand the connections and interactions within the data. The task specifies the desired operation or analysis to be performed on the graph by the LLM. For example, the task might be to identify key individuals in a social network based on their connections or to predict the likelihood of a certain event occurring within the graph. Outputs. An unstructured prompt, designed to be easily understood by a graph transformer LLM. This prompt acts as a clear instruction, guiding the LLM to process the input graph and fulfill the specified task. Steps. The process begins by receiving the graph and the task as inputs. The function then utilizes both the graph and the task to construct the suitable prompt. This prompt will be specifically designed to direct the LLM's processing of the graph, ensuring it focuses on the desired task. Prerequisites. The input graph must be in a format that the LLM can comprehend. For instance, the graph could be represented as an adjacency list, an adjacency matrix, or a graph database format. The chosen format should be compatible with the LLM's capabilities and processing limitations. Example values for prerequisite 1. Real-world example: if the LLM accepts graphs in the form of adjacency lists, the input graph should be provided in that format. The LLM can then use this representation to understand the relationships between nodes within a graph. The task must be clearly and unambiguously defined. This ensures the LLM understands the desired outcome and can accurately process the input graph. The task description should avoid vagueness and use precise language to communicate the intended analysis. Example values for prerequisite 2. Real-world example: instead of a general task like analyze the graph, a clearer task would be identify the most influential individuals in the social network or predict the most likely outcome of a specific event based on the relationships within the graph. Fine-tune parameters. The prompt can be further refined or adjusted to enhance the LLM's performance. This involves tailoring the prompt to better guide the LLM and elicit the desired output. This fine-tuning can include adding more context or background information to the prompt to help a LLM understand the graph and task more effectively. Additionally, the prompt can be modified to specify the desired output format, such as a list of key individuals, a probability score for an event, or a specific graph visualization. Challenges and fixes. The LLM might encounter difficulty in understanding the structure of the graph or the specific task it is intended to perform. Fixes to challenge 1. This issue can be addressed by carefully structuring the prompt to clearly communicate the graph's format and the desired analysis. For instance, the prompt could include examples of how the LLM should interpret relationships between nodes in the graph or clarify the expected outcome of the task. The prompt itself might lack clarity or be insufficiently detailed, making it difficult for the LLM to understand the intended analysis. Fixes to challenge 2. To mitigate this, the prompt can be expanded to provide additional context, specify the desired output format, and use clear language to articulate the task. For instance, the prompt could include examples of the desired output, explain the criteria for determining influential individuals, or provide a step-by-step breakdown of the task. Langchain experimental graph transformers diffbot format property key summary. This component is designed to extract property values from responses received from the diffbot application programming interface. Inputs. The input to this component is a response received from the diffbot application programming interface. The response contains data in a structured format, usually in JSON or XML, which is then processed by this component. Outputs. This component outputs formatted property values extracted from the diffbot application programming interface response. These values can be further utilized by other components in the workflow or can be used directly for analysis and decision making. Steps. The first step involves parsing the diffbot application programming interface response. This parsing step converts the response from the raw format into a structured representation that can be easily processed. After parsing, the component extracts property values from the structured representation of the diffbot application programming interface response. This extraction process identifies the specific values of interest and separates them from the rest of the data. Finally, the extracted property values are formatted according to the desired output format. This formatting can involve rearranging the values, applying specific data types, and ensuring that the output is compatible with downstream applications. Prerequisites. A valid diffbot application programming interface key is required for this component to function. This key is used to authenticate requests to the diffbot application programming interface and access the necessary data. Your diffbot API key. Fine-tune parameters. The property names can be specified as parameters to this component. This allows users to customize the extraction process to focus on specific properties of interest. The output format can be configured based on the requirements of the downstream application. Users can choose to output the values in a specific format, such as JSON, CSV, or a custom format. Challenges and fixes. Property names extracted from the diffbot application programming interface response might not always match the desired format or naming conventions used in the downstream application. To address this challenge, String manipulation functions can be used to format the extracted property names to match the desired format. This involves operations like replacing characters, trimming whitespace, or applying consistent capitalization. The output format generated by this component might not be compatible with the requirements of a downstream application or other components in the workflow. To overcome this challenge, the formatting logic within the component can be adjusted to meet the specific requirements of a downstream application. This involves modifying the data transformation steps to ensure that the output conforms to the desired format and data types. Langchain experimental graph transformers LLM format property key. Description of the langchain experimental graph transformers LLM format property key. Inputs. The input text is the text that will be processed by the langchain graph transformers LLM format. Property key. The graph nodes are the nodes of the graph that will be used to generate the output text. Outputs. The output text is the text that is generated by the langchain graph transformers LLM format. Property key. Steps. The retrieve graph nodes step retrieves the nodes of the graph from the graph database. The construct text from graph step constructs the output text from the graph nodes. Prerequisites. LangChain is an open source library for building and deploying language models as applications. Graph transformers are a type of transformer that can process graph data. Example values for prerequisite 2 are the specific graph transformer libraries and frameworks that are compatible with the LangChain implementation. Fine-tune parameters. The graph type is the type of graph that will be used to generate the output text. The max tokens parameter specifies the maximum number of tokens that the LangChain graph transformers LLM format property key can generate. Challenges and fixes. Handling large graphs is a challenge because large graphs can be difficult to process and store. Utilize graph partitioning techniques are used to break down large graphs into smaller pieces that can be processed more easily. Maintaining context is a challenge because the LangChain graph transformers LLM format property key needs to remember the context of the graph nodes to generate coherent output text. Employ context-aware transformers are transformers that are designed to handle contextual information and are effective for preserving the context of graph nodes during text generation. LangChain experimental graph transformers.llm.map to base relationship. This component, map to base relationship, bridges the gap between large language models LLMs and graph databases. It takes an LLM response, which is often unstructured text or JSON, and converts it into a structured graph representation. Inputs. The LLM response, which could be text, a JSON object, or any other format that the LLM outputs. An existing graph database, like Neo4j or ErangoDB. This is where the LLM-derived information will be stored. Outputs. The updated graph database, enriched with the information extracted from the LLM response. Steps. The LLM response is parsed, identifying key elements and their relationships. This might involve using natural language processing techniques to understand the text or extracting structured data from JSON. The parsed entities from the LLM response are mapped to nodes in the graph database. For example, if the response mentions people, places, or concepts, these would be represented as nodes. Relationships between these nodes are created based on the information extracted from the LLM response. For example, if the LLM response mentions that a person worked at a company, a relationship between the person node and the company node would be established. Prerequisites. A defined schema for the graph database. This schema defines the types of nodes and relationships that the database can store. Popular graph databases like Neo4j and ErangoDB offer flexible schema options. A clear understanding of the LLM response format. Knowing whether the response is structured like JSON or unstructured like plain text helps. Determine how the parsing and mapping should be done. Fine-tune parameters. An entity extraction model, which identifies the key elements entities in the LLM response. For example, a named entity recognition NER model could be used to extract person names, organizations, and locations. Relationship mapping rules, which define how the relationships between the extracted entities should be translated into graph. Relationships. These rules can be based on the context of the LLM response and the domain knowledge of PE. Application. Challenges and fixes. Ambiguous entities. The LLM response might contain entities that have multiple interpretations. For example, apple could refer to the fruit or the tech company. Entity disambiguation techniques, which use context and additional knowledge sources, can be employed to resolve such ambiguities. Missing relationships. The LLM response might not explicitly state all relationships between entities. In these cases, relationships can be inferred from the context using techniques like relationship extraction or knowledge graph embedding models. Incorrect relationship types. The mapping rules might lead to incorrect relationship types being assigned between entities. Supervised learning, where a dataset of labeled examples is used to train a model, can help fine-tune the relationship mapping rules and improve accuracy. Langchain experimental graph transformers LLM optional enum field summary. This component enhances the functionality of graph transformers by allowing users to incorporate optional enum fields within the structure of language models (LLMs). Inputs. A graph transformer, which represents a data structure that organizes entities and their relationships in a network-like manner. A language model LLM, capable of processing and generating human-like text. Outputs. An updated graph transformer that now includes an optional enum field, enhancing its flexibility and adaptability. Steps. The process begins by defining an enum field, which represents a predefined set of values that can be assigned to a particular attribute. The defined enum field is then integrated as an optional argument within the LLM. This enables the LLM to utilize the enum field during its operations, enhancing its ability to handle diverse input data. Prerequisites. A pre-existing graph transformer, ready for enhancement. An LLM available for integration. Fine-tune parameters. There are no specific fine-tuning parameters required for this component. Challenges and fixes. Potential incompatibility between the data type of the enum field and the input requirements of a LLM. This challenge can be addressed by converting the enum field to the data type that the LLM can handle. For example, if the LLM expects a string input, a numeric enum field would need to be converted into a corresponding string representation. Incorrect definition or configuration of the enum field. To avoid this issue, it's crucial to ensure that the enum field is defined correctly and its structure aligns with the capabilities of the LLM. This may involve specifying the valid values for the enum field and verifying that these values are compatible with the LLM's input format. For example, the enum field might need to be defined as a list of strings or integers, depending on the LLM's input requirements. Langchain experimental graph transformers LLM optional enum field. This component is about adding an optional enum field to a graph transformer LLM, which represents knowledge graphs. Inputs. Graph transformer LLM. A graph transformer LLM large language model is a type of AI model that leverages knowledge graphs to answer questions and generate text, utilizing relationships between entities in the graph. Enum field. An enum field defines a set of allowed values for a given attribute or property. For instance, in a person object, an enum field gender could have values like male, female, or other. Outputs. Graph transformer LLM with enum field. This is the output of the component. A graph transformer LLM with an additional optional enum field. This means the LLM can now utilize this field in its reasoning and generation processes, adding extra context and structure to the data. Steps. Create a graph transformer LLM. The initial step involves creating or loading an existing graph transformer LLM. This LLM, as mentioned before, uses knowledge graphs to understand and process information. Add an optional enum field to the LLM. The next step is to add the optional enum field to the LLM. This is done by defining the name and possible values for the field. The LLM can now utilize this field for its operations, choosing from the defined values when appropriate. Prerequisites. Graph transformer LLM. A graph transformer LLM that represents the knowledge graph. This is the core component, providing the knowledge base and reasoning capabilities. Enum field. An enum field that defines the possible values for the optional field. This adds structure and limits the range of acceptable values for the field, ensuring consistency in the data. Fine-tune parameters. Enum field name. The name given to the enum field. This should be descriptive and clearly indicate the purpose of the field. For instance, gender or language would be appropriate names. Enum field type. This defines the type of the enum field. This could be a simple string, an integer, or even a more complex structure depending on the specific needs and the data being handled. Challenges and fixes. Challenge 1. Handling missing values. The LLM needs to handle cases where the optional enum field is not provided. This could involve defaulting to a specific value or ignoring the field entirely, depending on the context and the LLM's purpose. Challenge 2. Validating enum field values. The LLM must ensure that the value provided for the enum field is one of the predefined values in the enum. This prevents errors and ensures data integrity. Summary of langchain experimental LLM bash process. This component allows you to run bash commands via an LLM, effectively bridging the gap between natural language and the powerful capabilities of the bash shell. This opens up a world of possibilities for automating tasks, executing scripts, and interacting with your system in new ways. Inputs. The input is a bash command, expressed in natural language. This could be anything from a simple command like list all files in the current directory to a more complex command like download the latest version of a software package and install it. The LLM interprets the natural language command and converts it into a valid bash command that can be executed. Outputs. The output of the command is returned as a string, providing you with the result of the executed bash command. This output could be anything from a simple list of files to a more complex output like a log file, or even a new file created by the command. Steps. The LLM, trained on a large dataset of bash commands, will generate a bash command based on the user's natural language input. This is where the LLM's ability to understand context and translate natural language into technical language comes into play. The generated bash command is then executed by the component using the bash shell. This means that the command is actually running on the system, and the component can access the output of the command. The output of the command is captured and returned to the user, providing them with the results of their bash command. This allows for seamless integration into workflows and applications where the output of a bash command is required for further processing. Prerequisites. The bash shell needs to be installed on the system. Bash is a standard component of most Linux and Mac OS systems. But if you are using a different operating system, you may need to install it separately. The LLM must be capable of generating valid bash commands. This is a crucial aspect of the component, as the LLM acts as the translator between natural language and technical commands. The LLM should have been trained on a large dataset of bash commands to ensure its accuracy and ability to generate valid commands. Fine-tune parameters. This parameter allows you to specify a prefix that will be added to the beginning of each generated bash command. This can be used to modify the behavior of the command or to provide additional context. For example, you could set the command prefix to sudo to ensure that all commands are executed with root privileges. This parameter allows you to specify a suffix that will be added to the end of each generated bash command. This can be used to modify the behavior of the command or to provide additional context. For example, you could set the command suffix to dev_null to suppress any error messages from the command. Challenges and fixes. One of the potential challenges is that the LLM might generate invalid commands, leading to errors or unexpected behavior. To address this, the component should include robust error handling mechanisms. This could involve catching errors during command execution and providing informative messages to the user. Additionally, the component could incorporate validation checks on the generated commands to ensure their validity before execution. The LLM might generate commands that take a long time to execute, potentially causing delays in the workflow. To address this, the component can allow users to specify a timeout for each command. This ensures that if a command takes too long, it will be terminated, preventing the component from being blocked indefinitely. This timeout parameter provides the user with control over the execution time and prevents unnecessary delays in the workflow. Langchain experimental graph transformers.llm.map to base relationship summary. This function takes a relationship as input and outputs its base relationship. Inputs: a relationship which is to be mapped to a base relationship. For example, the relationship could be the Earth is a planet. This relationship can be mapped to the base relationship as a large language model LLM that is capable of reasoning over relationships. This LLM will be used to determine the base relationship from the input relationship. For example, the LLM could be used to identify the base relationship from the input relationship the Earth is a planet by determining that the relationship type is a and that the entities are Earth and planet. Outputs: the base relationship of the input relationship. For example, the base relationship of the Earth is a planet is as a. Steps: the first step is to identify the relationship type. For example, the relationship type of the Earth is a planet is as a. The next step is to extract the entities from the relationship. For example, the entities of the Earth is a planet are Earth and planet. The final step is to determine the base relationship based on the relationship type and entities. For example, the base relationship of the Earth is a planet is a based on the relationship type is a and pay. Entities Earth and planet. Prerequisites: The LLM should be capable of reasoning over relationships. For example, identifying the base relationship from a given relationship. It is important for the LLM to be capable of recognizing different types of relationships and their corresponding base relationships. For example, the LLM should be able to recognize the is a relationship, such as the Earth is a planet, and determine that the base relationship is a. The relationship should be well defined and unambiguous. For example, the relationship is well defined and unambiguous because it clearly indicates a relationship of type is a between two entities. On the other hand, the relationship has a could be ambiguous. For example, the relationship the Earth has mountains could be interpreted as the Earth has mountains as part of it, or the Earth has mountains as a feature. The relationship type and entities should be clear to the LLM to avoid ambiguity. Fine-tune parameters. This function has no fine-tune parameters. Challenges and fixes. One challenge is that the LLM may struggle to identify the correct base relationship for complex relationships. For example, the LLM might struggle to identify the base relationship of the relationship the Earth has a large moon as has a. This is because the relationship is complex and involves multiple entities. The LLM may need to be trained on a larger dataset of relationships to improve its reasoning capabilities. Another challenge is that the relationship type may be ambiguous or unclear. For example, the relationship the Earth is a big planet could be interpreted as the Earth is a big planet in size or the Earth is a big planet in terms of importance. It is important to provide a more specific and unambiguous relationship type. For example, instead of the Earth is a big planet, one could use the Earth is a large planet to clarify the relationship type and make it less ambiguous. Langchain Experimental LLM Symbolic Math. This tool empowers large language models LLMs to perform symbolic mathematics using the SymPy library. LLMs, often known for their prowess in natural language processing, can now leverage this tool to tackle mathematical problems with symbolic manipulation. Inputs. Input string. This refers to the mathematical expression that the LLM will process. The LLM receives the mathematical expression as a string, which it then converts to a SymPy expression. For example, the input string could be 2 by 3 or SymPy 2. Outputs. Output string. After processing the input string, the LLM produces an output string representing the result of the symbolic math operation. This output string could be a simplified expression, a numerical value, or a more complex mathematical representation depending on the input and the SymPy operations performed. Steps. Convert input string to SymPy expression. This step involves parsing the input string and converting it into a format that SymPy can understand and work with. SymPy uses its own syntax for representing mathematical expressions. Evaluate the SymPy expression once the input string is converted to a SymPy expression. The tool evaluates the expression using SymPy's powerful capabilities. This evaluation could involve simplification, differentiation, integration, or solving equations, depending on the nature of the input expression. Convert result to string. Finally, the evaluated result, which may be a SymPy expression itself, is converted back to a human-readable string format. This allows the LLM to present the result to the user in a clear and understandable way. Prerequisites. SymPy. This refers to the SymPy library, a Python library designed for symbolic mathematics. SymPy provides a rich set of functionalities for symbolic manipulation, including differentiation, integration, simplification, and solving equations. To use the langchain experimental LLM symbolic math tool, The SIMPy library must be installed. Pip install SIMPy. This command is used to install the SIMPy library using the pip package manager. Installing SIMPy ensures that the tool has access to the necessary functions and capabilities for symbolic math operations. Python 3.7 or higher. The langchain experimental LLM symbolic math tool requires Python 3.7 or a later version. Python is the programming language that the tool is built upon, and it provides the foundation for running and executing the tool's code. Python version. This command is used to check the version of Python installed on your system. It ensures that you have a compatible version of Python for using the tool. Fine-tune parameters. None. This tool does not have any fine-tune parameters. Fine-tuning parameters are typically used to adjust the behavior or performance of a model during training. The langchain experimental LLM symbolic math tool does not have any training phase and relies on the underlying SIMPy library for its mathematical capabilities. Challenges and fixes. LLM may not be able to understand complex math expressions. LLMs are trained on vast amounts of text data, which often doesn't include complex mathematical expressions. This can lead to difficulties in interpreting and understanding complex mathematical formulas, especially those involving unusual symbols or uncommon mathematical concepts. Improve LLM's understanding of math expressions through fine-tuning to enhance the LLM's ability to understand complex math expressions. A focused fine-tuning process can be employed. This involves feeding the LLM with a specifically curated dataset consisting of various mathematical expressions, including those with complex structures and uncommon mathematical concepts. Through this process, the LLM can learn to recognize and interpret these expressions with greater accuracy. LLM may generate incorrect SIMPy code while LLMs can generate code. There's a risk of generating incorrect SIMPy code. This could happen due to misunderstandings of the mathematical context or errors in the code generation process. Use a code validator to ensure the generated SIMPy code is correct to mitigate this risk. Code validation tools can be integrated. These tools analyze the generated SIMPy code for syntax errors, logical inconsistencies, and potential semantic issues. They can help ensure that the generated code adheres to the correct SIMPy syntax and is free from common errors, enhancing the reliability and accuracy of the LLM's symbolic math operations. SIMPy may not be able to evaluate all expressions. While SIMPy is a powerful library, it may encounter limitations when evaluating certain types of mathematical expressions. These limitations could stem from the complexity of the expression, the presence of non-standard mathematical functions, or the lack of closed-form solutions for certain types of equations. Use a different symbolic math library or simplify the expression to address this. Alternative symbolic math libraries, such as Mathematica or Maple, can be explored. These libraries may offer broader support for a wider range of mathematical expressions. Alternatively, simplifying the expression by breaking it down into smaller, more manageable components can sometimes facilitate evaluation. Langchain experimental.llm symbolic math base LLM symbolic math chain summary. NaN, a chain that uses an LLM to perform symbolic math. It does this by converting the input to a symbolic math expression, then using the LLM to evaluate that expression. Inputs: a string representing the math problem. For example, the input can be what is the square root of 16? The name of the LLM to use. For example, the input can be GPT 3.5 Turbo. Outputs: the result of the math problem. For example, the output can be 4 steps. Convert the input string to a symbolic math expression. For example, the input string which is the square root of 16 can be converted to the symbolic math expression sqrt16. Use the LLM to evaluate the symbolic math expression. For example, the LLM can evaluate the symbolic math expression sqrt16 and output the result for. Prerequisites.
An LLM that can understand and evaluate symbolic math expressions. The LLM should have been trained on a dataset that contains mathematical expressions and their corresponding solutions. For example, the LLM could be GPT 3.5 Turbo or GPT-4.
Fine-tune parameters. The temperature of the LLM. Temperature controls the randomness of the LLM's output. A higher temperature leads to more diverse and creative responses, while a lower temperature results in more predictable and conservative responses. The top K of the LLM. Top K controls the number of tokens the LLM considers when generating its output. A higher top K value allows the LLM to consider more potential outputs, potentially leading to more diverse and creative responses, but also possibly decreasing accuracy. A lower top K value limits the LLM's options, resulting in more focused and potentially accurate responses. Challenges and fixes. The LLM may not be able to understand or evaluate all symbolic math expressions. This can occur if the LLM has not been trained on a sufficiently diverse dataset of symbolic math expressions, or if the expression is too complex for the LLM to handle. Fixes to challenge 1. Use a more powerful LLM, or fine-tune the LLM on a dataset of symbolic math problems. For example, a larger LLM like GPT-4 could be used, or the current LLM could be fine-tuned on a dataset specifically designed for symbolic math. The LLM may return incorrect results. The LLM's understanding of symbolic math expressions might be incomplete, resulting in inaccurate results. Fixes to challenge 2. Use a more powerful LLM, or fine-tune the LLM on a dataset of symbolic math problems. For example, a larger LLM like GPT-4 could be used, or the current LLM could be fine-tuned on a dataset specifically designed for symbolic math. Summary of langchain experimental LLM bash base. LLM bash chain. LLM bash chain is a component in the langchain experimental library that bridges the power of large language models LLMs with the versatility of bash scripting. This tool empowers users to interact with their systems by sending commands to the shell using LLMs, thereby leveraging the capabilities of both. It acts as an intermediary, translating human-readable instructions into executable bash scripts, thus enabling users to automate tasks and manipulate system resources through natural language inputs. Natural language instruction. This refers to the user's request expressed in plain English or another human understandable language. For instance, list all files in the current directory or download the latest version of a specific software package. Outputs. Bash script output. This encompasses the results of executing the bash script generated by the LLM. This could include a list of files, downloaded data, or any other output produced by the shell commands. Steps. User provides a natural language instruction. This step involves the user interacting with a LLM bash chain by inputting their command or request in a natural language format. The instruction is sent to the LLM. The provided natural language instruction is then forwarded to the LLM for processing. The LLM generates a bash script. The LLM analyzes the user's instruction and generates a corresponding bash script, a sequence of commands that can be executed by the bash shell. The script is executed in the shell. The generated bash script is then passed to the bash shell for execution. This involves running the script's commands and executing the associated actions. The output of the script is returned to the user. The final results or output generated by the bash script are then returned to the user, providing them with the outcome of their requested command. Prerequisites: Bash shell installed. The LLM bash chain relies on the bash shell, a command line interpreter that processes and executes commands. Therefore, a properly installed bash shell environment is essential for this component to function. LLM capable of generating bash scripts. A key component of LLM bash chain is an LLM that possesses the ability to generate bash scripts. This requires the LLM to understand the structure and syntax of bash scripting and translate user instructions into executable shell commands. Fine-tune parameters. LLM model. The choice of LLM model significantly impacts the quality and effectiveness of generated bash scripts. Optimizing the LLM bash chain might involve selecting a specific LLM known for its strengths in code generation or fine-tuning an existing model with relevant bash scripting examples. Bash script generation parameters. This refers to any parameters or configurations specific to the bash script generation process. These might include instructions for formatting the script, handling specific shell commands, or setting constraints on the generated script's complexity. Challenges and fixes. LLM may generate incorrect or inefficient scripts. LLMs, despite their capabilities, are not immune to errors. An LLM might generate scripts with logical flaws, syntax errors, or inefficient execution strategies. Fine-tune the LLM model or provide specific guidance for script generation to mitigate this issue. Users can fine-tune the LLM model on a dataset of correct bash scripts. Alternatively, providing the LLM with specific guidance, such as defining acceptable commands or outlining desired script behavior, can improve the accuracy and efficiency of the generated scripts. Bash script may require specific environment setup or dependency. Scripts generated by LLM bash chain might rely on external tools, packages, or libraries that need to be installed and configured correctly on the user's system. Ensure necessary packages or libraries are installed and configured correctly to address this challenge. The user must ensure that all required packages, libraries, and dependencies are properly installed and configured on their system. This may involve using package managers like apt or yum to install missing packages or modifying system configuration files to accommodate the specific needs of the generated scripts. LLM bash chain summary. A detailed explanation of the functionality and components of the LLM bash chain tool. Inputs. A natural language prompt that clearly specifies the desired task or action to be performed, which will be used to generate the corresponding bash command. An optional input that allows the user to provide context variables, which can be used within the bash script generated by the language model to personalize the command. Execution. Outputs. A textual string that represents the output generated after executing the bash script. This output would contain the results of the executed command. Steps. The provided natural language prompt is analyzed and processed to extract the desired bash command. This step involves understanding the user's intent and translating it into a valid bash command. The extracted bash command is executed using the provided context variables, if any. This step involves dynamically substituting the variables within the bash script to personalize the command execution. The output produced by the execution of the bash command is returned. This step makes the results of the command execution available to the user. Prerequisites: an LLM large language model capable of generating functional bash scripts. The language model needs to be proficient in understanding natural language instructions and translating them into executable bash commands. The presence of bash, a Unix shell command interpreter, installed on the system. Bash is responsible for interpreting and executing the generated bash scripts, ensuring proper functionality. Fine-tune parameters: the specific language model to be used for script generation. This parameter allows the user to select the language model that best suits their needs, based on its capabilities and performance in generating bash scripts. The prefix to be used for the bash command. This parameter provides a way to customize the generated bash command by adding a specific prefix to the command string. Challenges and fixes: the LLM might produce incorrect or incomplete bash commands due to misinterpretations or limitations in its understanding of the prompt. The user should ensure that the prompt is clearly worded, providing sufficient information and context to the language model. This reduces the chances of the LLM generating erroneous or incomplete bash commands. The generated bash command may fail to execute properly due to errors within the script or missing permissions required for its execution. The user should carefully review the generated bash script for any potential errors or inconsistencies. Additionally, they need to confirm that the necessary permissions are granted to the script for successful execution. Langchain experimental LLM symbolic math base LLM symbolic math chain summary. A detailed explanation of the LLM symbolic math chain. A chain designed to solve symbolic mathematics problems using a large language model (LLM). This chain leverages the capabilities of LLMs to process and understand mathematical expressions, making it a valuable tool for solving complex symbolic equations. Inputs: the input to this chain is a mathematical problem that needs to be solved. This problem can be presented in various formats, such as a textual description, a mathematical equation, or a combination of both. For example, a problem could be stated as solve for x in the equation 2 by 5 11, or what is the area of a triangle with base 10 and height 5. Outputs: the output of this chain is the solution to the provided mathematical problem. The solution is presented in a format that is readily understandable, typically as a numerical value or a simplified mathematical expression. For instance, if the input problem is solve for x in the equation 2 by 5 11, the output would be x3. Steps: 1. The first step involves converting the input problem into a format suitable for the LLM to process. This might involve translating the problem into a standardized mathematical notation or breaking it down into smaller, more manageable subproblems. For example, if the problem is presented as a textual description, it needs to be converted into a mathematical equation that the LLM can understand. 2. Once the problem is formatted appropriately, it is sent to the LLM. The LLM is trained on a vast dataset of text and code, enabling it to understand and interpret mathematical concepts and expressions. It processes the input problem and generates a response, potentially including the solution or steps towards finding the solution. 3. The final step involves parsing the LLM's response and extracting the solution. This might involve analyzing the LLM's output, identifying the relevant information, and converting it into a structured format. For example, if the LLM provides a series of steps to solve the problem, the chain needs to extract the final solution from these steps. Prerequisites: An LLM with the capability to solve symbolic math problems is essential for this chain to function. The LLM should have been trained on a dataset that includes mathematical concepts and expressions, enabling it to understand and interpret mathematical problems. There are various powerful LLMs available, such as GPT-3, Lambda, and Palm, which have demonstrated abilities in solving symbolic mathematics problems. The choice of LLM depends on the specific requirements of the task and the available resources. Fine-tune parameters. This chain does not require any fine-tuning parameters. The chain's functionality is based on the underlying LLM's capabilities, and no additional fine-tuning is necessary. However, the performance of the chain can be improved by selecting an LLM that is well suited for solving symbolic math problems. Challenges and fixes. Challenge 1: an LLM may not be able to solve all symbolic math problems. The complexity and scope of mathematics are vast, and LLMs, despite their impressive capabilities, may struggle with certain types of problems. For instance, solving complex differential equations or proving abstract mathematical theorems may be beyond the current capabilities of many LLMs. Fixes to challenge 1. One approach to address this challenge is to use a more powerful LLM. LLMs with larger model sizes and advanced training datasets may be better equipped to handle complex mathematical problems. Another approach is to provide the LLM with more context. This can be achieved by providing additional information about the problem, such as relevant definitions, theorems, or examples. By providing more context, the LLM can better understand the problem and potentially arrive at a solution. Challenge 2: an LLM may return an incorrect solution. LLMs are trained on massive amounts of data, but they are not perfect and can sometimes make mistakes. The nature of mathematical problems is such that even a small error can lead to an incorrect solution. Therefore, it is crucial to verify the LLM's solution. Fixes to challenge 2. To ensure the accuracy of the solution, it is recommended to verify the LLM's solution manually. This can be done by reviewing the steps taken by the LLM and ensuring that they are logically sound. Alternatively, one can use a different LLM to solve the same problem. If both LLMs arrive at the same solution, it increases confidence in the accuracy of the result. Langchain Experimental LLMs. This YAML file provides a comprehensive overview of experimental language models (LLMs) within the langchain framework. Langchain is an open-source framework that offers tools for building and deploying applications using LLMs. This document delves into the specifics of working with these experimental LLMs, outlining their capabilities, challenges, and best practices. Inputs. The input to the experimental LLMs can be plain text or a structured prompt. The text input is a basic textual input that can be processed by the model. A prompt, on the other hand, is a carefully crafted instruction that guides the LLM to generate a specific output. The prompt is a key input for guiding the LLM in its processing. It can be as simple as a question or as complex as a multi-step instruction that includes context, constraints, and desired output format. Outputs. The experimental LLMs produce textual outputs, which are the generated responses based on the provided inputs. These outputs are often in natural language, reflecting the model's understanding of the input and its ability to generate coherent and relevant text. The LLMs also generate tokens as outputs. Tokens are the basic units of text processed by the model. Understanding the token count is essential for managing costs and optimizing the performance of the model. Steps. The first step involves initializing the LLM. This step typically includes loading the model, configuring its parameters, and establishing the necessary connections for communication. After initialization, the next step is to call the LLM. This involves sending the input text or prompt to the model and receiving the generated output. This process involves the model's internal processing, where it applies its learned knowledge and patterns to generate the output. Prerequisites. Langchain is the core framework used for building and working with LLMs. It provides a standardized interface and a wide range of tools for interacting with different LLMs, managing their outputs, and integrating them into applications. Langchain 0.0.243. This specific version of Langchain ensures compatibility with the experimental LLMs and provides access to the latest features and improvements. The experimental LLMs are powered by specific LLM providers. OpenAI is a leading provider of LLMs, known for their advanced models like GPT-3 and ChatGPT. OpenAI API key is a crucial component for accessing and utilizing OpenAI's LLMs. This key acts as a credential, enabling authentication and authorization for accessing the model's capabilities. Hugging Face is another prominent provider of LLMs, offering a diverse collection of models and tools for working with them. Fine-tune parameters. Temperature is a parameter that controls the randomness and creativity of the LLM's output. Higher temperatures lead to more unpredictable and potentially surprising outputs, while lower temperatures produce more predictable and coherent responses. Top P is a parameter related to the probability distribution of the model's output. It controls the diversity of the generated text by filtering out words with low probabilities. Lower top P values lead to more focused and predictable responses, while higher values result in more diverse and potentially less coherent outputs. Challenges and fixes. API key errors can arise when the provided API key is invalid or expired. Provide a valid API key is the solution, ensuring that the key is valid, active, and properly configured in the system. Rate limiting occurs when the number of requests to the LLM exceeds the permissible limit. Implement a rate limiter involves setting up a mechanism that controls the frequency of requests to the LLM, preventing exceeding the usage limits and avoiding potential penalties. Unexpected behavior can occur due to various factors, such as errors in the code, unexpected input data, or inherent limitations in the model. Debug the code is essential for identifying and fixing these errors, ensuring that the application functions as expected and generates accurate outputs. LLM availability might be impacted by server outages, maintenance, or other unforeseen circumstances. Use a different LLM provides flexibility and resilience by switching to a different LLM provider or model, ensuring continued operation even when a specific LLM is unavailable. Token limits are imposed by the LLMs, restricting the amount of text that can be processed at once. Truncate or split input text involves breaking down large inputs into smaller chunks that fit within the token limit, enabling processing and generating outputs in manageable segments. Memory management is essential for handling the large amounts of data involved in LLM interactions. Use an appropriate memory strategy involves implementing techniques like caching, efficient data structures, and optimized algorithms to manage memory efficiently and avoid performance bottlenecks. Model choice plays a significant role in achieving the desired outcomes. Select an appropriate model involves carefully considering the specific needs of the application and choosing the model best suited for the task. Considering factors like size, training data, and intended usage, Performance optimization is crucial for maximizing the efficiency of LLM applications. Optimize code involves identifying performance bottlenecks, optimizing algorithms, and utilizing hardware resources effectively to improve the speed and efficiency of the application. Cost considerations are essential, especially when using paid LLMs. Use a cheaper LLM involves exploring alternative LLMs or adjusting usage patterns to minimize costs, while maintaining the desired functionality. Security is paramount when working with sensitive data or user input. Sanitize user input involves implementing measures to filter out malicious or inappropriate content, protecting the application and users from potential harm. Privacy concerns arise when dealing with personal information. User privacy preserving LLM involves selecting LLMs that prioritize user privacy. Utilizing techniques like differential privacy or homomorphic encryption to minimize data leakage. Fairness is crucial for ensuring unbiased and equitable outcomes. Use a fair LLM involves selecting models trained on diverse datasets and implementing techniques to mitigate biases. Promoting fairness in the generated outputs. Bias is a significant challenge in LLM applications, stemming from biases in the training data. Use a debiased LLM involves employing methods to detect and mitigate biases in the models. Promoting more equitable and inclusive outputs. Transparency in LLM operations is essential for understanding how the model works and building trust. Use a transparent LLM involves selecting models that provide insights into their decision-making processes, allowing users to understand the reasoning behind the generated outputs. Explainability is crucial for understanding the rationale behind the model's outputs. Use an explainable LLM involves selecting models that can provide explanations for their predictions, making the decision-making process more transparent and understandable to users. Reliability is a key factor in ensuring consistent and trustworthy results from LLMs. Use a reliable LLM involves selecting models known for their accuracy, consistency, and robustness, ensuring that the generated outputs are trustworthy and dependable. Robustness refers to the model's ability to handle unexpected inputs or variations in the data. Use a robust LLM involves selecting models that are less prone to errors or failures when presented with unusual or noisy inputs. Scalability is crucial for handling increasing workloads and data volumes. Use a scalable LLM involves selecting models that can be effectively deployed and scaled to handle large amounts of data and requests without significant performance degradation. Interoperability is essential for seamlessly integrating LLMs with other systems or tools. Use an interoperable LLM involves selecting models that adhere to standardized interfaces and protocols, enabling seamless integration with existing applications and workflows. Customization allows tailoring the LLM's behavior and outputs to specific needs. Fine-tune the LLM involves training the model on a specific dataset relevant to the application, improving its performance and tailoring it to specific tasks. Integration is crucial for leveraging the power of LLMs in real-world applications. Integrate with other tools involves connecting the LLM to other tools and services, expanding its capabilities and enabling it to interact with various data sources and systems. Deployment is the process of making the LLM application available for use. Deploy the LLM involves choosing an appropriate infrastructure, configuring the application, and making it accessible to users. Monitoring the LLM's performance and behavior is essential for identifying potential issues and ensuring its ongoing functionality. Monitor the LLM involves tracking key metrics, such as latency, error rates, and resource utilization to identify and address any performance degradation or unexpected behavior. Maintenance is crucial for ensuring the LLM application's long-term stability and effectiveness. Maintain the LLM involves updating the model, patching vulnerabilities, addressing performance issues, and ensuring that the application continues to function as expected over time. Langchain Experimental LLMS Summarization. This YAML file describes the experimental large language models LLMs that are implemented in the langchain library, and describes how to use them effectively. LLMs are a type of artificial intelligence model that are trained on massive amounts of text data and can be used to perform a variety of language-related tasks, including summarization, translation, and question answering. In langchain, these models are wrapped in a consistent interface, allowing for easy use and experimentation. Inputs: the text that will be processed by the LLM. Optional context that can be provided to the LLM to aid in the summarization process. Outputs: the summarized text produced by the LLM. Embeddings are numerical representations of the input text, which can be used to perform tasks like semantic search and clustering. Steps: the first step is to create an LLM object, which represents the specific LLM model that will be used. Once the LLM object is created, it can be called to perform the desired summarization task. Prerequisites: langchain library, which is a framework for building and deploying LLM applications. It provides a standardized interface for interacting with different LLM providers and facilitates building complex chains of LLM operations. Version 0.0.237 or later is required to use the experimental LLMs. LLMs from providers such as Hugging Face, OpenAI, or Google are required. These providers offer different types of LLMs, each with its own strengths and weaknesses. For example, OpenAI provides the popular GPT-3 model, while Hugging Face hosts a wide variety of open-source LLMs. Fine-tune parameters. This parameter controls the randomness in the LLM's output, which can be adjusted to generate more creative or more predictable responses. The top K parameter controls the number of possible words that the LLM considers at each step in the generation process. This can be adjusted to produce more diverse or more focused outputs. Challenges and fixes. LLMs can be slow to generate text, especially for large inputs or complex tasks. One way to address this is to use a faster LLM model or optimize the code to reduce the number of computations required. For instance, you can use a smaller model or choose a more efficient LLM architecture. Additionally, you can optimize the code by vectorizing operations and using efficient data structures. Using LLMs can be expensive, especially for large models. One way to reduce costs is to use a cheaper LLM or optimize the code to reduce the number of API calls required. For example, you can use a smaller model or choose a more efficient LLM architecture. Additionally, you can optimize the code by batching requests and using caching techniques. LLMs can require significant memory to operate. This can be a problem if you are working on a machine with limited memory. One way to address this is to use a smaller LLM or optimize the code to reduce the memory footprint. For example, you can use a model with fewer parameters or implement memory-efficient data structures. LLMs are often accessed through application programming interfaces (APIs), which have rate limits to prevent abuse. To avoid hitting these limits, you can use a different LLM. Optimize the code to reduce the number of API calls required. or explore alternative methods for accessing the LLM. Examples include using a local version of the LLM or using a different provider that offers more generous rate limits. Summary of Langchain Experimental LLMs Llama-P Chat Llama API. A detailed summary of the Langchain Experimental LLM API for interacting with Chat Llama models. Outlining its purpose, inputs, outputs, steps involved, prerequisites, fine-tuning parameters, and potential challenges and their solutions. Inputs. Text prompt: the text input provided to the Chat Llama model for generating a response. For instance, a user could input a question, a creative writing prompt, or a command to be executed by the model. Outputs. Text response: the generated response from the Chat Llama model based on the provided text prompt. The output is in the form of text, which can be a conversational answer, a story, a piece of code, or any other text-based output depending on the prompt and the capabilities of the model. Steps. Sends prompt to Chat Llama application programming interface. The text prompt is sent to the Chat Llama application programming interface API for processing. This involves sending the prompt as a request to the API endpoint. Receives response from Chat Llama application programming interface. The Chat Llama API processes the prompt and generates a text response based on the selected Chat Llama model. This response is then sent back to the user or application that initiated the request. Prerequisites. Chat Llama application programming interface key: a unique identifier that grants access to the Chat Llama API. This key is used for authentication and authorization purposes, allowing users to interact with the API and access Chat Llama models. Your Chat Llama application programming interface key: a specific alphanumeric string that acts as a password to access the Chat Llama API. It is provided by Chat Llama upon account creation or subscription to their service. Chat Llama model: a specific language model trained by Chat Llama to perform specific tasks, such as generating text, translating languages, or summarizing information. Each model is designed with different capabilities and training data. Chat Llama model name: the name of the specific Chat Llama model chosen for interacting with the API, such as Chat Llama 7B or Chat Llama 13B. Different models have different strengths and limitations, so the appropriate model should be chosen based on the intended application. Fine-tune parameters. Temperature: a parameter that controls the randomness or creativity of the model's response. A higher temperature value results in more unexpected or diverse outputs, while a lower temperature produces more predictable and consistent responses. Challenges and fixes. Authentication issues: challenges related to authenticating with the Chat Llama API using the provided API key. Ensure valid application programming interface key: verify that the provided API key is correct and has not expired. Incorrect or expired keys can prevent successful authentication. Verify correct application programming interface endpoint. Ensure that the API endpoint URL used in the request is accurate. Mismatched endpoints can result in connection errors or incorrect responses. Model availability challenges related to accessing the desired Chat Llama model. Check for model availability. Ensure that the selected Chat Llama model is currently available for use. Some models might be temporarily unavailable due to maintenance or server overload. Select different model if the desired model is not available. Choose a different Chat Llama model with similar capabilities. Rate limiting challenges related to exceeding the rate limits imposed by the Chat Llama API. Implement backoff strategy. Implement a mechanism to slow down requests if the rate limit is reached. This involves waiting for a predetermined period before sending further requests to the API. Use a proxy server. Employ a proxy server to distribute requests across multiple servers, reducing the load on the Chat Llama API and avoiding rate limiting. Response formatting challenges related to the formatting of the text response generated by the Chat Llama model. Adjust response format using application programming interface parameters. Utilize parameters available in the Chat Llama API to customize the output format of the generated response. This could involve setting line breaks, indentation, or other formatting options. Use a custom post-processing function. Employ a custom function to process the raw text response received from the API and modify its formatting or structure according to specific requirements. This can involve adding punctuation, converting the output to Markdown, or implementing other post-processing steps. Langchain Experimental LLMs. Experimental LLM classes in langchain refer to the set of classes that are under active development and are not yet considered stable or fully supported by the langchain library. These classes offer exciting new capabilities and advancements in natural language processing but might require additional testing and evaluation before widespread use. Inputs. The input to langchain's experimental LLM classes can be diverse, ranging from plain text to structured data formats like JSON or CSV. For instance, you could provide a piece of text for summarization, a question for question answering, or a set of instructions for code generation. Outputs. The output of the experimental LLM classes is also varied, depending on the specific task and LLM model used. It can be text, code, structured data, or even images, depending on the nature of the task. Steps. Initializing the LLM involves configuring the desired model, including any specific parameters, loading the necessary weights, and establishing a connection to the model's application programming interface API. Calling the LLM with the input means sending the prepared data to the LLM through its API and waiting for the model to process it. This step involves the actual execution of the LLM's computations to generate a response. Processing the LLM's output might involve tasks like formatting the output into a desired format, extracting specific information, or further refining the results based on context or constraints. Prerequisites. Langchain installed refers to the requirement of having the langchain library installed on your system to use the experimental LLM classes. Installation can be achieved using the pip package manager, which is a standard tool for installing Python packages. The command to install langchain is pip install langchain. Fine-tune parameters. Temperature is a parameter that controls the randomness or creativity of the LLM's output. Higher temperature values lead to more diverse and unpredictable outputs, while lower values produce more deterministic and predictable responses. Top K parameter defines the number of most likely words that the LLM will consider when generating its output. This parameter helps control the output's fluency and coherence by limiting the choices for the next word to the most probable ones. Top P, also known as nucleus sampling, is a parameter that limits the probability distribution of the next word to a certain percentile. It helps in generating more focused and consistent output by excluding less probable words from the selection pool. Challenges and fixes. LLM not responding correctly can occur due to various reasons, including incorrect initialization or configuration of the LLM. To address this, it's essential to review the model setup and ensure all parameters are correctly set and the model is functioning properly. LLM output is not formatted correctly can arise when the output needs additional processing or transformation to align with the desired format. Employing appropriate post-processing techniques, such as formatting libraries or custom code, can help to achieve the desired output structure. LLM is too slow or inefficient can happen if the model selection is inappropriate for the task or if the execution process is not optimized. Choosing a more efficient model or optimizing the execution environment can significantly improve the LLM's performance. LLM output is not relevant can be due to inadequate prompts or context, or because the model needs further fine-tuning. Refining the prompts by providing more specific and relevant context and fine-tuning the model with additional data related to the task can improve the relevance of the output. Summary of Langchain Experimental LLMs Llama-P Chat Llama API. This is an LLM application programming interface wrapper built for the Chat Llama model. This API allows users to interact with the Chat Llama model, generating text using a provided prompt. Inputs. The prompt is the input text that the user provides to the LLM. Initiating the desired conversation or text generation task. For instance, write a short story about a robot who learns to laugh. Temperature. A parameter that controls the randomness of the generated text. Higher temperature values lead to more creative and unpredictable responses. Lower values generate more deterministic and predictable outputs. Top K. An integer value that determines the number of most likely tokens to be considered for each step in the text generation process. This limits the range of potential words for prediction. Top P. A parameter that determines the probability threshold for selecting the next token. It works by ranking tokens based on their probability and then selects all tokens whose cumulative probability exceeds the specified threshold. This parameter balances diversity and quality in the generated text. Max tokens. An integer that defines the maximum number of tokens the model can generate in response to a prompt. This prevents the LLM from generating excessively long outputs. Outputs. The model generates text in response to the provided prompt. This generated text can be a coherent conversation, a creative story, a factual summary, or any other type of text depending on the user's prompt. Steps. A request is sent to the Chat Llama API with the prompt and all the necessary parameters. The Chat Llama API processes the request, generating a response with the generated text, which is then returned to the user. Prerequisites. You need an API key from OpenAI. You can find the necessary steps to obtain an API key on the OpenAI website by navigating to https://beta.openai.com account API keys. Install the required packages for using Chat Llama API pip install langchain llama index. This installation ensures you have the necessary libraries to interact with the LLM. Fine-tune parameters. Temperature, as described above, controls the randomness and creativity of the generated text. Experiment with different temperature values to achieve the desired balance between predictability and originality. Top K. A parameter that limits the selection of tokens for each step of the text generation, allowing for greater control over the generated text. Top P. A parameter that sets a probability threshold for selecting the next token, providing a way to balance the diversity and quality of the output. Max tokens. The maximum number of tokens that the LLM can generate is a parameter that allows users to manage the length of the generated text. Challenges and fixes. If an API key is not provided, the model cannot access the Chat Llama API. Ensure that a valid API key is included in the constructor of the Chat Llama API object. Invalid API requests can occur due to incorrectly formatted prompts or incorrect parameter values. Double-check the format and the values of the prompt and parameters, making sure they comply with the API specifications. API rate limits are set to prevent excessive usage. Respect these limits by scheduling your requests to avoid exceeding the allowed usage per unit of time. Network connection issues can hinder communication with the Chat Llama API. Ensure a stable network connection to allow smooth communication with the API server. The Chat Llama model might be unavailable due to technical maintenance or high server load. Wait a short period and try again later if the model appears to be unavailable. LM Format Enforcer. A comprehensive description of the LM Format Enforcer, including its purpose, inputs, outputs, steps, prerequisites, fine-tune parameters, and challenges with their respective fixes. Raw output from an LLM refers to the original unprocessed text generated by the large language model. It can be in various forms, including plain text, JSON, or other structured formats. For example, if the LLM is asked to summarize a text, the raw output might be a paragraph of text. Desired output format is the specific format that the user wants the LLM output to be converted to. It could be a predefined format like JSON, CSV, or a custom format specific to the application. This allows for efficient integration of LLM outputs into existing workflows. Formatted output represents the final output after the LM Format Enforcer has applied transformations to the raw LLM output. It conforms to the desired output format specified by the user. This formatted output can then be used by downstream applications without needing to handle different output formats from various LLMs. Parse the LLM's raw output involves analyzing the raw output from the LLM to understand its structure and identify the relevant information. This step ensures that the LLM output is correctly understood before applying any transformations. For example, if the raw output is in JSON format, this step will involve parsing the JSON to extract the required information. Apply format-specific transformations involves converting the raw LLM output to the desired format based on the user's specifications. This may involve extracting specific information, restructuring the output, or applying formatting rules. For example, if the desired output format is a CSV file, this step might involve extracting data from the raw output and creating a comma-separated structure. LLM output must be parsable signifies that the raw output from the LLM should be in a format that can be analyzed and understood by the LM Format Enforcer. This ensures that the tool can successfully process the output. If the output is in an unstructured or unreadable format, the LM Format Enforcer will not be able to process it. Defined output format implies that the user needs to specify the desired format for the output beforehand. This allows the LM Format Enforcer to know which transformations to apply to the raw LLM output. Having a defined output format ensures that the final output is consistent and usable for downstream applications. Format-specific transformations refer to the specific rules and operations that are applied to convert the LLM output to the desired format. These transformations may vary depending on the specific format and the desired output structure. They can be adjusted and fine-tuned to achieve optimal results based on the user's requirements. For instance, if the desired output format is a table, the transformations might involve extracting data from the LLM output and arranging it into rows and columns. LLM output format is inconsistent refers to the challenge that different LLMs may generate outputs in different formats. making it difficult to process them consistently. This can be addressed by adapting the LM format enforcer to various output structures. For example, the tool might need to handle different JSON structures or variations in plain text outputs. Adapt to various output structures involves designing the LM format enforcer to handle different output structures from various LLMs. It might include using flexible parsing algorithms or incorporating pattern recognition to identify key information across different output formats. This allows the tool to accommodate the diverse output styles of various LLMs. Missing or invalid data in output is another challenge where the LLM output might be incomplete or contain errors. This can be tackled by handling missing or incorrect data in a robust manner. For instance, the LM format enforcer might include mechanisms to detect missing data, fill in missing values using logical inferences, or flag invalid data for user attention. Handle missing or incorrect data involves incorporating error handling mechanisms to deal with missing or invalid data in the LLM output. This could include using placeholder values for missing data, applying data validation rules, or providing options for manual correction of errors. These techniques ensure that the final output is as complete and accurate as possible despite potential issues in the raw LLM output. Summary of langchain experimental LLMs JSON decoder import JSON. This component utilizes the capabilities of JSON to decode and retrieve information from JSON data. It shines in scenarios where intricate nested JSON structures necessitate transformation into a more organized format for easier analysis and usage. Inputs: the raw JSON data that needs to be processed. A schema that defines the structure of the input JSON data, used to ensure accurate decoding and extraction. Outputs: the extracted data organized into a more accessible format, typically a dictionary or list, enabling further analysis and processing. In case of decoding errors or inconsistencies, the component provides helpful messages to identify and resolve issues. Steps: 1. The input JSON string is converted into a Python dictionary using a JSON library, transforming the raw text into a structured representation. 2. The parsed JSON data is checked against the provided schema. This step verifies that the data follows the expected structure and type definitions, enhancing reliability and preventing errors during subsequent processing. 3. Using the schema, the component efficiently extracts specific data elements from the parsed JSON, filling a new dictionary or list with the desired information. 4. The extracted data is formatted and presented in a structured format, typically a Python dictionary or list, making it easily usable for further analysis and processing within your application. Prerequisites: a valid JSON schema that complies with the JSON schema specification is necessary to guide a decoding process. JSON type object, properties, name, type string, age, type integer, required name, age. Make sure a JSON library like JSON or OJSON is installed in your Python environment to enable efficient JSON parsing and manipulation. Fine-tune parameters. Adjust the schema to precisely match the specific structure and data types of your input JSON data. Define custom rules within the schema to specify how specific data elements should be retrieved and organized in the output. Challenges and fixes. Challenge 1: the input JSON data does not conform to the specified schema, leading to decoding errors. 1. Examine the input JSON data against the schema for inconsistencies or errors. 2. Update the schema to accurately represent the structure and data types of the input JSON data. 3. Modify the data extraction rules within the schema to accommodate any discrepancies between the input JSON and the schema. Challenge 2. The schema is incomplete or inaccurate, resulting in incorrect data extraction. 1. Carefully review the schema to ensure it accurately reflects the structure and data types of the input JSON data. 2. Update the schema to include any missing properties or adjust existing ones to match the input JSON. 3. Define clear extraction rules within the schema to guide the data retrieval process accurately. Langchain experimental LLM format enforcer decoder. Import LM format enforcer. Summary of langchain experimental LLMs. LM format enforcer decoder. Import LM format enforcer. Inputs: a function to convert the output of the language model into a human-readable format. The decoder is a crucial component of any natural language processing pipeline. For example, if a language model generates text in a specific format like JSON, the decoder can be used to convert it into a more user-friendly format like plain text or HTML. A component to ensure the language model output conforms to the desired format and structure. For example, if the desired output should be in JSON format, the format enforcer can ensure that the output follows the JSON syntax. Outputs: a function that takes a prompt as input and returns the output of the language model after applying decoding and format enforcement. It provides a streamlined and consistent way to interact with the language model, ensuring that the output is properly formatted and understandable. Steps: import both the decoder and format enforcer functions to make them available for use. Combine the imported components to create a callable function. This function encapsulates the decoding and format enforcement processes, making it easy to use the language model and obtain well-formatted output. Prerequisites: a function capable of transforming the language model output into a comprehensible form. A decoder is essential for any scenario where the language model output is in a specific format that may not be immediately understandable by humans. A function to ensure the language model's output conforms to the desired format and structure. A format enforcer is crucial to maintain consistency and reliability in the output, guaranteeing that the information can be easily processed and used in downstream applications. Fine-tune parameters. Not applicable. Challenges and fixes. The decoder may be unable to process the output generated by the language model due to format inconsistencies or errors in the language model's output. This can be addressed by checking the decoder's compatibility with the language model output format and providing appropriate error handling mechanisms. Additionally, the format enforcer may not be able to properly enforce the desired format due to limitations in the enforcer itself or unexpected output from the language model. This can be resolved by carefully choosing a suitable format enforcer that aligns with the expected output format and incorporating error handling mechanisms to address any unexpected outputs. Langchain experimental LLMs onformer decoder. Import JS onformer. Summary: a langchain component that allows you to leverage the power of JS onformer, a powerful tool for decoding and interpreting JSON data within your langchain applications. This component enables you to extract structured information from JSON data and utilize it within your langchain workflows. Inputs: input JSON data, the JSON data that needs to be decoded and interpreted. This data can be a JSON file, a JSON string, or any other source of JSON data. For example, you might have a JSON file representing product information, customer data, or sensor readings. Optional: a custom JSON schema to guide the decoding process. An optional custom JSON schema can be provided to guide the decoding process. This schema defines the expected structure of the JSON data, helping the decoder to accurately interpret the data and extract relevant information. For instance, you might define a schema to specify the fields you expect within a product information JSON document, such as product name, price, and description. Outputs: structured data extracted from the input JSON, ready for further analysis or processing. The output of the JSON former decoder is structured data extracted from the input JSON. This data is ready for further analysis or processing within your langchain application. For instance, you might use the extracted data to query a knowledge base, generate a summary, or perform other tasks. Steps: 1. Initialize a JSON former decoder object. Optionally passing a custom schema. The first step is to create a JSON former decoder object. You can optionally provide a custom JSON schema to the decoder during initialization. 2. Feed the input JSON data to the decoder. The input JSON data is then fed to the initialized decoder. The decoder will process the input data, interpreting its structure and extracting relevant information. 3. Decode the JSON data according to the schema if provided, or automatically infer the structure. A decoder will decode the JSON data based on the provided schema or automatically infer the structure if no schema is specified. This allows for flexibility in handling various JSON data formats. 4. Output the extracted data as a structured object, which can be readily integrated with langchain's other components. Finally, the decoder outputs the extracted data as a structured object. This object can be easily integrated with other langchain components for further processing and analysis. Prerequisites: install the JSONformer library to use the JSONformer decoder component. You need to install the JSONformer library. This can be done using the following pip command: pip install JSONformer. Have a valid JSON input file or string. A valid JSON input file or string is required for the component to function correctly. The input JSON data should adhere to the JSON format specifications, ensuring that it is well structured and correctly formatted. Fine-tune parameters. Schema: provide a custom JSON schema to guide the decoding process. You can fine-tune the decoder by providing a custom JSON schema. This schema will help the decoder interpret the input JSON data more accurately and extract the desired information. For instance, you could define a schema to specify the fields you expect in a customer data JSON document, such as customer name, email address, and contact number. Challenges and fixes. The input JSON is not valid. If the input JSON is not valid, the decoder will be unable to process it correctly. Ensure that the input JSON conforms to the JSON format specifications, including proper syntax, data types, and structure. The input JSON is too complex to decode automatically for complex JSON structures. It might be challenging for the decoder to automatically infer the structure. In such cases, providing a custom JSON schema will guide the decoder and improve the accuracy of the decoding process. This allows for more precise extraction of information from complex JSON data. ensuring that the desired data is properly interpreted. Prerequisites. This section details the process of integrating a retrieval augmented language model (ReLLM) decoder into the langchain framework. Inputs. An instantiated ReLLM decoder object. A transformers pipeline object designed for text generation. For instance, it could be a pre-trained model like GPT-2 or BART, configured to perform text generation. Optional parameters that fine-tune the ReLLM decoder's behavior. These parameters include temperature controls the randomness of the generated text. Top K limits the number of possible next tokens, influencing the model's creativity and diversity. Top P limits the probability mass of the next tokens, affecting the model's focus and predictability. Max length sets the maximum length of the generated text, preventing the model from generating excessively long outputs. Outputs. The result is a langchain wrapper for the ReLLM decoder, enabling text generation grounded in knowledge retrieved from an external knowledge base. For example, when asked what is the capital of France, the ReLLM decoder, integrated with langchain, could retrieve information about France from a knowledge base and then generate the output Paris. Steps. First, the ReLLM decoder object is instantiated. This involves loading a pre-trained model and configuring it for the desired task, such as text generation. Then, the decoder object is wrapped within a langchain LLM class. This integration provides a standardized interface for interacting with the decoder within a langchain framework. Prerequisites. REM decoder. A pre-trained transformers pipeline object designed for text generation, such as GPT-2 or BART, which is already loaded and configured for text generation. Fine-tune parameters. Temperature. This parameter controls the randomness of the generated text. A higher temperature value increases the model's willingness to explore less likely but potentially more creative or surprising outputs. Conversely, a lower temperature value encourages the model to generate more predictable and consistent text. Top K. The top K parameter restricts the number of possible next tokens that the model can select from at each generation step. A higher top K value allows the model to consider a larger set of potential tokens, potentially leading to more diverse and surprising outputs. A lower top K value limits the model's choices, resulting in more predictable and focused text generation. Top P. The top P parameter, also known as nucleus sampling, controls the probability mass of the next tokens. It restricts the model's choices to a subset of tokens that collectively account for a certain probability mass. A higher top P value allows the model to consider a wider range of tokens, potentially resulting in more diverse outputs. A lower top P value concentrates the probability mass on a smaller set of tokens, making the model's output more predictable and focused. Max length. The max length parameter sets the maximum length of the generated text. This parameter ensures that the model does not generate outputs that exceed a specified length, preventing unnecessarily long or verbose responses. Challenges and fixes. Challenge 1. Errors encountered when importing the ReLLM decoder. Fixes to Challenge 1. This challenge can often be resolved by verifying that the ReLLM decoder, including its dependencies, is properly installed and configured in the system's environment. Challenge 2. The ReLLM decoder fails to generate coherent or meaningful text. Fixes to Challenge 2. Adjusting the fine-tuning parameters, such as temperature, top K, and top P, can help improve the coherence and quality of the generated text. Experiment with different parameter values to find a configuration that balances creativity, predictability, and semantic meaning. For example, if the generated text is too random or incoherent, try lowering the temperature value or increasing the top K parameter. Conversely, if the text is too repetitive or predictable, consider increasing the temperature or decreasing the top K parameter. Langchain experimental LLMs RailLM decoder import RailLM summary. This section describes how to integrate a retrieval augmented language model RailLM into langchain for utilization with the RailLM decoder. Inputs: a pathway to a directory that encompasses the RailLM model files. For instance, this could be a directory containing a pre-trained model from the Hugging Face Model Hub. An optional dictionary of keyword arguments quags that can be passed to the Hugging Face auto model for SUC2 SQLM, load from pre-trained method. These quags allow you to customize the model loading process, such as specifying the device CPU or GPU or loading specific parts of the model. Outputs: a langchain RailLM decoder object. This object represents the RailLM model integrated with langchain and ready for use with the RailLM decoder. The RailLM decoder uses the RailLM model to generate text based on retrieved information from a knowledge base. Steps: load the RailLM model from the specified directory using the Hugging Face auto model for SUC2 SQLM. Load from pre-trained method. This method retrieves the model files from the directory and initializes the model for use in your application. Construct a langchain RailLM decoder object utilizing the loaded model. This step integrates the RailLM model with the langchain framework, allowing you to easily interact with the model and utilize it for text generation tasks in conjunction with retrieved information. Prerequisites: ensure that the Hugging Face Transformers library is installed. This library provides the necessary tools to interact with and manage Hugging Face models, including RailLM models. To install the library, use the following command in your terminal or command prompt: pip install transformers. The RailLM model files must be readily accessible in the specified directory. These files are essential for loading and using the RailLM model. You can obtain the model files from the Hugging Face Model Hub or from other sources, depending on the specific model you wish to use. Fine-tune parameters. Model path: this parameter specifies the path to the directory containing the RailLM model files. It is crucial to provide the correct path to the directory to ensure that the model is loaded successfully. Quags: this parameter represents a dictionary of keyword arguments quags that can be passed to the Hugging Face auto model for SUC2 SQLM, load from pre-trained method. These quags enable you to customize the model loading process based on your specific needs. For example, you can specify the device CPU or GPU to load the model onto or choose specific parts of the model to load. Challenges and fixes. An error could occur during model loading. In such a scenario, verify that the model files are properly located in the specified directory. Additionally, ensure that the correct Hugging Face model identifier is utilized. The model identifier is typically a unique string that identifies the model on the Hugging Face Model Hub. If you are unsure of the correct model identifier, consult the Hugging Face Model Hub documentation. The creation of the RailLM decoder might fail. To resolve this issue, confirm that the loaded model is compatible with the RailLM decoder. Compatibility refers to whether the model's architecture and capabilities align with the requirements of the RailLM decoder. Additionally, double-check that the appropriate arguments are supplied to the RailLM decoder constructor. The constructor takes various parameters, such as the loaded model, retriever, and other configuration options. Providing incorrect or insufficient arguments could lead to errors during the decoder's creation. Summary of langchain experimental LLM SLM format enforcer decoder import LM format enforcer. This component ensures that the output from a language model is presented in a consistent and desired format. This is crucial for downstream applications that rely on structured data. Inputs: the raw text output generated by the language model. This output might be in a variety of formats depending on the model's configuration and the specific task. The target format in which the output needs to be presented. This could be a structured format like JSON JavaScript object notation or CSV comma-separated values. Outputs: the language model's output, but formatted according to the specified output format. This enables seamless integration with other systems and applications. Steps: the component first analyzes the model's output to determine the current format. It might involve identifying delimiters, key-value pairs, or other structural elements. Based on the identified format and the desired format, the component applies transformations to convert the output into the specified format. This might involve parsing the output, extracting relevant data, and restructuring it according to the target format's rules. Prerequisites: the presence of a language model from the langchain library. This could be a large language model LLM like Llama 2 or GPT-3, which are capable of generating human-like text. The specification of the desired output format. This could be a widely used format like JSON, which is commonly used for data exchange, or CSV, which is often used for tabular data. Fine-tune parameters: the specific type of format being enforced. For example, it could be a specific JSON schema or a CSV with predefined columns and data types. The names and order of the columns in the final output. This is especially relevant when converting the output to a CSV format. Challenges and fixes: the language model's output might not follow any standard format, making it difficult to parse and structure. Various techniques are employed to convert the output into a usable format. This might involve using pattern recognition, data extraction methods, or predefined rules to identify and structure the data. The output format might not be consistent across different model runs, or even within the same run. This could lead to parsing errors and inconsistencies in the final output. Regular expressions, which are powerful tools for pattern matching, can be used to parse and normalize the output. This ensures that the data is consistently formatted and can be processed reliably. Langchain experimental PAL chain summary. A chain that allows you to interact with a large language model LLM in a way that is more like a conversation, where the LLM can remember past interactions and use that context to generate more relevant responses. An example could be a chatbot that remembers previous conversations and uses that information to tailor its responses. Inputs: a query is the user's input to the LLM. It could be a question, a statement, or a request. History is the record of previous interactions between the user and the LLM. This could be a list of questions and answers, or a more structured representation of the conversation. Outputs: the response from the LLM is the output of the conversation chain. It is generated based on the query and the history. It could be an answer to a question, a continuation of a story, or a suggestion. Steps: the query is passed to the LLM, which uses its knowledge and the context provided by the history to generate a response. The response is then returned to the user. Prerequisites: A large language model LLM, such as GPT-3. A history of past interactions with the LLM. Fine-tune parameters. Temperature is a parameter that controls the randomness of the LLM's responses. A higher temperature will produce more creative and unpredictable responses, while a lower temperature will produce more consistent and predictable responses. Top P is a parameter that controls the diversity of the LLM's responses. A higher top P will produce responses with a wider range of words, while a lower top P will produce responses with a more focused set of words. Challenges and fixes. The LLM may generate responses that are not relevant to the query, or that are repetitive. This can be addressed by providing more context to the LLM, or by using a different LLM. For example, if the LLM is asked a question about a specific topic, but the user's previous queries were about a different topic, the LLM may generate a response that is not relevant to the current query. This can be addressed by providing more context to the LLM, such as by including a summary of the previous queries in the history. The LLM may generate responses that are offensive or harmful. This can be addressed by using a LLM that has been trained on a dataset that is free from bias and harmful content, or by using a LLM that has been fine-tuned to prevent the generation of offensive or harmful content. For example, if the LLM is asked to write a story, it may generate a story that contains offensive language or harmful content. This can be addressed by using a LLM that has been trained on a dataset that is free from bias and harmful content, or by using a LLM that has been fine-tuned to prevent the generation of offensive or harmful content. Langchain Experimental PAL Chain Summary. This section describes the langchain experimental PAL chain summary, a YAML structure that represents a chain that acts as a personal AI assistant. Inputs. User input. This is a key-value pair, where user input represents the input that the personal AI assistant receives. It's the text that the user types in to interact with the AI assistant. Outputs. Response. This is a key-value pair that represents the output generated by the AI assistant in response to the user's input. This can include text, code, or any other type of response that the AI assistant is designed to generate. Steps. User input is processed. This step describes the initial processing of the user's input. It can involve tasks like tokenization, cleaning up the input text, and potentially performing basic natural language understanding to identify the type of input. Chain determines intent of the input. This step focuses on the AI assistant's ability to understand the user's intent based on the input. This is a crucial step for a personal AI assistant, as it helps determine the appropriate response. For example, a user might ask a question, make a request, or give a command. Chain generates a response based on intent. This is the core step of the AI assistant. It involves generating a response that is aligned with the user's intent, drawing from its knowledge base and capabilities. This can involve retrieving information, performing calculations, or creating content. Prerequisites. Large language model LLM. This is a fundamental requirement for a personal AI assistant. LLMs are powerful neural networks trained on massive datasets of text and code. They are capable of generating text, translating languages, writing different kinds of creative content, and answering your questions in an informative way. LLMs can be used to power chatbots, language models, and other AI applications. Real-world examples of LLMs include OpenAI's GPT-3 in Google's Palm. Memory component. This refers to a component that allows the AI assistant to retain information. about previous interactions with the user. This is crucial for maintaining context and providing personalized responses. For example, the memory might store previous conversations or user preferences. Fine-tune parameters. Memory size. This parameter controls how much of the past conversation the AI assistant will retain in its memory. This can impact the AI assistant's ability to provide context-aware responses. A larger memory size allows for more context, but can also consume more computational resources. Prompt engineering. This involves carefully crafting the instructions or prompts that are used to guide the LLM in generating responses. The prompt plays a vital role in determining the quality and accuracy of the AI assistant's output. Fine-tuning the prompt can involve adjusting the structure, language, and information provided to the LLM to improve its performance. Challenges and fixes. Handling context from previous interactions. This refers to the challenge of ensuring that the AI assistant can maintain a consistent and relevant understanding of the conversation history. This is addressed by employing a memory component to store past interactions. Understanding user intent. This addresses the challenge of correctly interpreting the user's intent based on their input. This can be achieved by training the AI assistant on a dataset with examples of different intents. Generating coherent and accurate responses. This addresses the challenge of ensuring that the responses generated by the AI assistant are both meaningful and accurate. This can be achieved through fine-tuning the prompt to provide clear instructions to the LLM, as well as selecting a robust LLM that is capable of producing high-quality outputs. Langchain experimental. Palchain, base, Palchain summarization. A base class for Palchain, which is a type of chain used for processing text. This class provides the fundamental structure and functionality for Palchain objects. It is designed to be extended and customized for specific use cases. Inputs. The query to be processed by the chain. Typically a string that represents a question or a request for information. A list of strings representing the history of previous interactions with the chain. This history can be used to provide context and ensure that the chain's responses are consistent with prior interactions. Outputs. The response generated by the chain based on the input query and history. This response is typically a string containing the answer to the query or a relevant piece of information. Steps. The chain is initialized with the necessary parameters and configuration. This step sets up the chain's internal state and prepares it for processing requests. The chain processes the input query and history, applying its logic and using the configured components to generate a response. This step involves analyzing the query, retrieving relevant information, and generating an appropriate response. The chain returns the generated response to the user or calling program. This step completes the interaction with the chain and delivers the output to the user. Prerequisites. The langchain, chains.palchain, base, palchain class, which provides the core functionality for palchains. It is a fundamental dependency for this chain and defines the basic structure and methods used for processing text. The langchain, chains, base, chain class, which is a base class for all types of chains in langchain. It provides essential functionality for managing and running chains, such as handling inputs, outputs, and steps. Fine-tune parameters. A Boolean flag that controls whether the chain should print verbose logging messages during its execution. Enabling this parameter provides detailed information about the chain's internal operations, which can be helpful for debugging and understanding the chain's behavior. A memory object that stores the chain's history of interactions. This memory object can be used to provide context for future interactions and ensure that the chain's responses are consistent with past conversations. There are various types of memory objects available, each offering different capabilities for storing and retrieving information. A Boolean flag that controls whether the chain should return intermediate steps during its execution. Enabling this parameter can be useful for debugging or understanding the chain's internal processing. It provides insights into the individual steps taken by the chain to generate the final response. A callback manager object that allows the chain to register and manage callbacks during its execution. Callbacks are functions or methods that are called at specific points in the chain's execution, such as before or after each step. They provide a mechanism for monitoring the chain's progress and performing custom actions based on the chain's state. Challenges and fixes. The PAL chain does not work as expected, failing to generate the desired response or behaving in an unexpected way. This can occur due to various factors, including incorrect initialization, faulty configuration, or data issues. To resolve this challenge, carefully review the chain's initialization process, ensuring that all necessary parameters are set correctly and the chain's components are properly configured. Verify that the input query and history are provided in the expected format and that the chain's data sources are accessible and functional. The PAL chain returns an empty response, failing to provide any meaningful output. This can happen if the chain encounters an error during its execution or if it cannot find relevant information to generate a response. To troubleshoot this issue, check the input query and history for any errors or inconsistencies. Ensure that the query is well-formed and that the history contains relevant information that the chain can use. Verify that the chain's configuration is correct and that its components are functioning as expected. The PAL chain throws an error during its execution, preventing it from completing its task successfully. This can be caused by various factors, including programming errors, configuration issues, or unexpected input data. To address this challenge, inspect the error logs for detailed information about the error's source and nature. Use debugging tools to step through the chain's code, identify the location of the error, and investigate the underlying cause. This may involve inspecting the input data, reviewing the chain's configuration, or examining the implementation of its components. Langchain experimental.pal chain, base, PAL validation summary. None. The PAL validation class is used to assess the quality of outputs produced by a large language model (LLM) by comparing them with the expected or ground truth outputs for a specific task. Inputs. The input is a list of strings, where each string represents an individual query for which we desire to evaluate the LLM's performance. The ground truth output is also a list of strings, each string representing the expected output corresponding to each query in the input list. Outputs. The validation results consist of a list of dictionaries, with each dictionary containing the evaluation metrics for a single query. These metrics provide insights into the LLM's performance on the specific query. The final accuracy score is computed as the average accuracy across all queries, representing an overall measure of the LLM's performance on the given task. Steps. The PAL validation class systematically iterates through each query present in the input list. For every query, the LLM's generated output is compared with the corresponding ground truth output. Based on this comparison, evaluation metrics such as accuracy, precision, recall, and F1 score are calculated to quantify the LLM's performance. The results for each query are stored in a dedicated dictionary, facilitating the analysis of individual query performance. Finally, the average accuracy across all queries is calculated and reported as the final accuracy score, providing a comprehensive summary of the LLM's performance on the task. Prerequisites. The large language model LLM employed for generating outputs must be configured and ready for use. It should be initialized and have access to the necessary resources for processing the queries. Example: before using the PAL validation class, ensure that the LLM is instantiated and connected to an appropriate API or service that allows it to generate responses for given inputs. Ground truth outputs corresponding to all queries in the input list must be readily available. This requires having a dataset or knowledge base that contains the correct answers or expected outputs for each query. Example: in a question answering task, the ground truth outputs would be the correct answers to the questions provided in the input list. These answers could be sourced from a database, a knowledge graph, or any other relevant repository. Fine-tune parameters. The evaluation metrics utilized for comparing the LLM's output to the ground truth output can be tailored according to the specific needs of the task. The threshold for determining the accuracy of the LLM's output can be adjusted based on an acceptable level of error tolerance for the task. This threshold defines the minimum level of similarity required between the LLM's output and a ground truth output for the output to be considered accurate. Challenges and fixes. Challenge 1: handling instances where the LLM produces outputs that are semantically similar but not precisely identical to the ground truth. This can occur due to variations in phrasing, word choice, or sentence structure. Fixes to challenge 1. To address this challenge, one approach is to employ techniques like semantic similarity analysis. This involves using algorithms or models that can compare the meaning of the LLM's output and a ground truth output, even if they are not exactly the same. Another approach is to relax the accuracy threshold, allowing for a degree of semantic similarity to be considered accurate. Challenge 2: dealing with queries that have multiple possible correct outputs. In certain tasks, the correct answer may not be unique, and multiple valid outputs could exist. Fixes to challenge 2: to handle such situations, the PAL validation class can be modified to evaluate the LLM's output against all possible correct outputs. If the LLM's output matches any of the valid outputs, it can be considered correct. Alternatively, the class can be adjusted to assess the degree of overlap between the LLM's output and the set of correct outputs, providing a more nuanced evaluation of its performance. Langchain experimental open clip summary. A langchain component that integrates OpenAI's clip model for image text retrieval and generation. This component leverages the power of clip contrastive language image pre-training, a model trained to understand the relationship between images and text. It enables you to perform tasks such as finding images similar to a given text description or generating captions for images based on their content. Inputs. Image: the input image that you want to analyze or compare. It can be a URL to an image or a local image file. Text: the text input, such as a description, caption, or query. This text will be used to interact with the image in various ways. Outputs. Similarity score: a numerical score representing how similar the input image and text are. This score ranges from 0 to 1, with 1 indicating a perfect match and 0 indicating no similarity. Text-image embeddings: vector representations of both the input image and text, capturing their underlying semantic content. These embeddings allow for efficient comparison and retrieval, even between diverse inputs. Steps. Encode image and text into embeddings. Both the image and the text are converted into numerical representations called embeddings. These embeddings capture the essence of the image and text in a way that allows for comparison and analysis. Calculate similarity score between embeddings. The embeddings of the image and text are compared using a similarity metric. This metric quantifies how closely the two representations align, providing a numerical measure of their similarity. Prerequisites: OpenAI Application Programming Interface Key, an authentication key provided by OpenAI that allows your application to access the CLIP model and its capabilities. To obtain an API key, you need to sign up for an OpenAI account. OpenAI CLIP model: this refers to the specific CLIP model you choose to use. OpenAI offers various CLIP model variants, each with different capabilities and computational requirements. You need to select the appropriate model based on your use case and resources. Fine-tune parameters. Model size: this parameter allows you to adjust the size of the CLIP model you use. Larger models have higher accuracy but require more computational resources. Smaller models are less demanding but may have lower performance. Batch size: this parameter controls the number of data samples processed in each iteration during training or inference. A larger batch size typically speeds up processing but requires more memory. Smaller batch sizes can be helpful for managing memory limitations. Challenges and fixes. Incorrect application programming interface key: if you provide an invalid or incorrect application programming interface key, the component will fail to access the OpenAI CLIP model. Verify and correct application programming interface key: double-check that the API key you are using is valid and has the necessary permissions to access the OpenAI CLIP model. You can usually verify the key's validity on the OpenAI website or within the platform where you obtained it. Model availability: the OpenAI CLIP model may not always be available for use due to maintenance, updates, or other factors. Choose an available model if the desired CLIP model is unavailable. Explore alternative models provided by OpenAI or consider using different image text retrieval or generation tools. Langchain experimental plan and execute. Executors base executor summary. Description of base executor: a base class for executors in the plan and execute framework. This class provides a foundational structure and core functionality for executing a series of steps as outlined in a plan. Inputs to base executor: a plan, which is a list of steps to execute. The plan defines the sequence of actions to be performed by the executor. It can be thought of as a recipe for how to achieve a specific goal. For example, a plan for getting a cup of coffee could include steps like boil water, grind coffee beans, brew coffee, and pour coffee. A context, which is a dictionary containing information about the execution. This context provides additional data and parameters relevant to the execution of the plan. It acts as a repository of knowledge that the executor can use to make decisions and adjust its behavior during execution. For instance, the context for getting a cup of coffee might include the desired type of coffee, the amount of coffee to brew, and any preferred brewing methods. Outputs of base executor: the result of the execution. The executor produces the outcome of executing the plan based on the provided context. The result might be a success or failure message, a generated document, or any other output relevant to the task defined by the plan. In the case of getting a cup of coffee, the output might be a message indicating whether the coffee was successfully brewed and whether it was served according to the preferences defined in the context. Steps in base executor execution. Initialize the executor. This step sets up the executor with any required resources and configuration. It might include loading the plan, accessing the context, and preparing any necessary tools or libraries for the execution. Execute the plan steps. The executor iterates through each step in the plan and performs the corresponding action. It uses the context to guide the execution and make informed decisions. For instance, if the plan step is grind coffee beans, the executor might access the coffee type and amount specified in the context to determine pay, appropriate grind size and quantity. Return the execution result. Once all steps have been executed, the executor generates and returns the final result of the execution, including any relevant information or artifacts. This output might be a simple message indicating success or failure, or it could be a more complex output like a generated document, a dataset, or a visual representation of the results. Prerequisites for base executor execution. The plan must be a list of steps. The executor requires a well-defined plan in the form of a list of steps to ensure that the execution proceeds in a structured and organized manner. The context must be a dictionary. The executor needs access to the context as a dictionary to retrieve relevant information and make informed decisions during execution. Fine-tune parameters of base executor. None. Base executor has no fine-tune parameters. Challenges and fixes for base executor. The plan may be invalid. The plan might contain errors or inconsistencies that would prevent the executor from successfully executing it. For instance, the plan might contain steps that are not well defined or steps that depend on conditions not present in the context. Validate the plan before execution. The executor can validate the plan by checking for completeness, consistency, and correctness of the steps and their dependencies. The context may be missing information. The context may not contain all the information necessary for the executor to complete the plan. For example, the context for getting a cup of coffee might not specify the desired coffee type or the amount to brew. Check for required context information. The executor can check for the presence of essential information in the context before attempting to execute the plan. If necessary, it can prompt the user for missing information or use default values based on common practices. The executor may not be able to execute a step. The executor might encounter unexpected issues while executing a step in the plan. This could be due to external factors, software errors, or limitations in the executor's capabilities. Handle errors during step execution. The executor should be designed to gracefully handle errors during execution. This might involve identifying the cause of the error, attempting to recover from the error, or providing informative feedback to the user. In cases where recovery is not possible, the executor should provide clear error messages and stop execution to prevent further issues. Langchain experimental plan and execute agent executor plan and execute summarization. A description of the langchain experimental plan and execute agent executor plan and execute summarization agent executor, which uses a planning and execution loop to process user input and produce an output. Inputs: the user input that the agent receives and processes. For example, a user may provide a prompt such as summarize the main points of the article about the history of AI. Outputs: the final output produced by the agent after executing its plan. The output is the agent's response to the user input, fulfilling their request. For example, in response to the prompt summarize the main points of the article about the history of AI. The agent might produce a concise summary of the key points from the article. Steps: The agent receives the user input and initializes its internal state. For example, the agent may store the user input and any relevant context in its memory. The agent calls the planner to generate a plan of actions to take. The planner uses the user input, the agent's internal state, and any other relevant information to decide how to best fulfill the user's request. The plan might involve a series of steps, like retrieving specific information from a database, applying a language model to process text, or generating creative content. The agent iterates through the plan, executing each action. For example, if the plan involves retrieving information from a database, the agent will use a database executor to perform the query and retrieve the relevant data. The agent uses the results of each action to update its internal state. For example, after retrieving information from a database, the agent may update its memory with the new information. The agent continues to execute the plan until it reaches a terminal state. The terminal state indicates that the plan has been completed and the agent has fulfilled the user's request. The agent returns the final output to the user. The final output is the result of executing the plan, providing the user with a response to their initial input. Prerequisites. Langchain is a framework for building and deploying language models. Langchain allows developers to easily connect different language models, data sources, and tools to create complex AI applications. For example, a developer could use langchain to build a chatbot that can access a database of knowledge, use a language model to generate creative text, and interact with a web API to retrieve information from the internet. Planners are responsible for generating plans of actions to take. Planners use the user's input, the agent's internal state, and any other relevant information to decide how best to fulfill the user's request. For example, a planner might decide to first retrieve information from a database, then summarize the information using a language model, and finally present the summary to the user. Executors are responsible for executing individual actions. For example, a database executor would be responsible for retrieving data from a database. A language model executor would be responsible for processing text using a language model. And a web API executor would be responsible for interacting with a web application programming interface. Fine-tune parameters. The planner to use. For example, the agent may use a different planner for different types of user input, such as a simple planner for simple requests and a more complex planner for complex requests. The executor to use. The choice of executor depends on the specific action to be performed. For example, if the plan involves retrieving data from a database, the agent will use a database executor. While if the plan involves processing text using a language model, the agent will use a language model executor. The maximum number of steps to take. This parameter limits the number of actions the agent can take in a single plan. Limiting the number of steps is important to prevent the agent from getting stuck in an infinite loop. The maximum number of retries for each action. This parameter defines how many times the agent will try to execute an action before giving up. This is useful for handling situations where an action might fail due to a temporary error. The logging level. The logging level controls how much information the agent logs about its actions. Setting a higher logging level provides more information about the agent's behavior, which is helpful for debugging and understanding the agent's decision-making process. Challenges and fixes. The agent may not be able to find a plan that leads to a successful outcome. This can happen if the user's request is too complex or if the planner is not well suited for the task. For example, If the user asks the agent to write a poem about a specific topic, the planner may not be able to generate a plan that leads to a successful outcome if it does not have access to a good language model for generating creative content. The agent can be fine-tuned with more data or a different planner. Providing the agent with more data can help the planner to generate better plans. For example, providing the agent with a large corpus of poetry can help it to learn how to generate poems using a different planner might also be helpful. For example, if the agent is using a simple planner that is not well suited for complex requests, using a more sophisticated planner might lead to better results. The agent may encounter errors while executing actions. This can happen for various reasons, such as a network error, a database error, or a problem with the language model. The agent can be fine-tuned with better error handling or a more robust executor. Fine-tuning the agent with better error handling can help it to recover from errors and continue executing the plan. Using a more robust executor can also help to reduce the likelihood of errors. For example, using a language model executor that is more tolerant to errors can help to prevent the agent from crashing when encountering errors in the language model's output. Chain executor. Chain executor. Inputs. Input documents which are to be processed by the chain. The user question or prompt that the chain should address. Outputs. Output documents which are the result of chain's execution. Steps. Generate a plan based on the input question. This step involves analyzing the question, identifying relevant information, and deciding which steps to take. Execute the plan by following the steps outlined in the previous step. This involves using the chain to retrieve information, generate text, or perform other tasks as needed. Combine the results of the execution steps and return them as output documents. This step might involve summarizing the results, formatting the output, or generating a final response. Prerequisites. Chain. Chain type. Chain type specifies the type of chain to be used. This influences how the chain processes information and generates responses. For instance, stuff chain concatenates all input documents and passes them to the language model, while MapReduce chain processes each document individually and then combines the results. Chain quags. Chain quags provide additional parameters that can be used to customize the behavior of the chain. For example, verbose controls the level of logging output, and return intermediate steps determines whether to return intermediate steps of the chains. Execution. Executor. Executor type. Executor type defines the strategy for executing the plan. Common executor types include sequential executor, which executes the steps of the plan in order, and async executor, which executes the steps in parallel. Executor quags. Executor quags are used to customize the behavior of the executor. For example, verbose controls the level of logging output. Fine-tune parameters. Chain type. Choosing a suitable chain type for the task at hand is crucial for efficient plan generation and execution. Some chains excel at specific tasks, while others are better suited for others. For instance, stuff chain might be suitable for tasks involving summarizing a single document, while MapReduce chain might be more appropriate for tasks requiring processing multiple documents. Executor type. The choice of executor type can impact the execution strategy and efficiency. Some executors, like sequential executor, execute steps linearly, while others, like async executor, leverage parallel execution. The choice should be made based on the task's requirements and resource constraints. Chain quags. Fine-tuning the chain parameters can refine its behavior during plan generation and execution. For example, using a larger context window in the chain might help it process longer and more complex documents, while enabling return intermediate steps can provide insight into the chain's execution process. Executor quirks. Executor parameters can significantly impact the executor's performance and efficiency. For instance, adjusting the max workers parameter in an async executor can control the number of parallel tasks. Challenges and fixes. Challenge 1. The plan generated by the chain may not always be the most effective solution for the task. This can be due to various factors, such as an incomplete understanding of the user question, limitations in the chain's knowledge base, or biases in the chain's training data. Fixes to challenge 1. One approach to improve plan quality is to fine-tune the chain using a dataset relevant to the task. This can help the chain learn patterns and generate more effective plans for specific use cases. Alternatively, experimenting with different chain types might lead to a better fit for the particular task. Challenge 2. Executing the plan efficiently can be challenging, especially when dealing with complex tasks or large datasets. The executor might face bottlenecks, resource constraints, or limitations in its ability to handle specific operations. Fixes to challenge 2. Optimizing the executor's performance involves considering the task's requirements and resource availability. Using a different executor type might be beneficial, such as switching from a sequential executor to a parallel one, depending on the task's computational needs. Adjusting the executor's parameters, such as increasing the number of worker threads or setting appropriate timeouts, can also improve efficiency. Langchain experimental plan and execute executors base chain executor. Chain executor is a base class for executors that plan and execute chains. It provides a framework for defining and running chains of steps, where each step can be a different component like a language model, a tool, or a custom function. The chain executor manages the flow of data between these components. Inputs. Input chain refers to the sequence of components or steps that are connected to process the input data. This chain is defined by the user and can be customized based on the specific task. Inputs to the chain refers to the data or information that is fed into the chain for processing. This can include text, code, or other types of data, depending on the task. Outputs. Output of the chain refers to the result produced by the chain after processing the input data. This could be a summary, a translation, a generated text, or any other output that the chain is designed to produce. Steps. 1. Plan. The chain execution refers to the process of determining the order in which the steps in a chain will be executed. The chain executor analyzes the chain definition and identifies the dependencies between the steps to create an execution plan. 2. Execute. The chain refers to the actual running of the chain, where each step is invoked in the order defined by the execution plan. During execution, the chain executor manages the flow of data between steps, passing the output of one step as input to the next. 3. Return. The output refers to the final step where the chain executor returns the output produced by the chain to the user. Prerequisites. Langchain refers to a Python library that provides tools and building blocks for building and deploying language-based applications. It offers a wide range of components for tasks such as text generation, question answering, and summarization. Chain executor is built on top of langchain and leverages its components. Chain is a core concept in langchain. It represents a sequence of steps or components that are connected to process data. Chains are defined by users and can be composed of various components, such as language models, tools, and custom functions. Fine-tune parameters. Verbose is a parameter that controls the level of logging and output produced by the chain executor. Setting verbose to true will provide more detailed information about the execution process, such as the execution plan and the output of each step. Chain type is a parameter that specifies the type of chain being executed. Different types of chains have different functionalities and requirements, and specifying the chain type helps the chain executor to manage the execution process appropriately. Challenges and fixes. Challenge 1: the chain may not be able to execute properly. Fixes debug the chain and ensure that it is working correctly. This involves examining the chain definition, checking for any errors in the code, and verifying that the individual components are functioning as expected. Challenge 2: the chain may take a long time to execute. Fixes optimize the chain for speed. This involves identifying bottlenecks in the chain, such as slow components or inefficient data processing steps. Strategies for optimization can include using faster components, reducing the amount of data being processed, and improving the efficiency of the data flow between components. Langchain Experimental Plan and Execute Planners Base LLM Planner. This component is a foundational building block for automating tasks using a combination of language models and external tools. It employs the capabilities of an LLM planner to generate a sequence of actions needed to accomplish a user-defined task, then executes those actions using available tools. Inputs. The user provides a task description or input, specifying the desired outcome. This can range from a simple request like find the weather forecast for tomorrow in New York to more complex tasks like book a flight to Paris next week. This input includes essential elements for task completion. These elements include a language model LLM capable of understanding and generating natural language, tools such as APIs, databases, or external scripts that can be used to perform actions, and other components that facilitate the execution process. Outputs. The system generates a structured plan, outlining the steps needed to achieve the desired task. This plan acts as a roadmap, detailing the specific actions to be performed by the tools in the order in which they should be executed. Following the execution of the plan, the system presents the results of the task. These results can vary depending on the nature of the task, from a simple weather forecast to a confirmed flight booking. Steps. The process begins by receiving the user's task description or input. This input can be provided through various interfaces, including text-based commands or conversational interactions. The LLM planner, utilizing the provided LLM, analyzes the input and generates a detailed plan of action. The plan outlines the individual steps required to complete the task, taking into account the available tools and their functionalities. The generated plan is then executed using the designated tools and components. The plan specifies which tool should be used for each step, and the system orchestrates the interaction between the tools to perform the required actions. The final output of the process is the result of the task execution. This output may be presented to the user in various forms, depending on the nature of the task. For example, a weather forecast may be displayed as text, while a flight booking might be confirmed through an email or online portal. Prerequisites. This component relies on the availability of an LLM planner instance. This instance can be created using the langchain experimental, plan and execute, planners, LLM planner class, providing the necessary parameters for its operation. To execute the plan generated by the LLM planner, The system requires a set of tools and components. These tools are typically external resources, such as APIs, databases, or scripts, capable of performing specific actions required by the task. Fine-tune parameters. The selection of the appropriate language model (LLM) is crucial for effective plan generation. The chosen LLM should be capable of understanding the user input and generating relevant and accurate plans. The performance of the LLM planner can be further refined by adjusting various plan generation parameters. These parameters may include the desired length of the plan, the level of detail required in each step, and the specific criteria for choosing the appropriate tools for each action. Challenges and fixes. One potential challenge is that the LLM planner may generate plans that are incorrect or incomplete. This could occur due to limitations in the LLM's understanding of the task, inaccuracies in the provided tools, or ambiguities in the user input. If the generated plan is incorrect, it can be addressed by regenerating the plan or refining the LLM planner's configuration. This might involve providing additional context to the LLM, verifying the accuracy of the tools, or re-evaluating the plan generation parameters. Another challenge arises when the tools or components used for task execution fail to perform as expected. This could be due to errors in the tool's implementation, connectivity issues, or unexpected data formats. Addressing this challenge involves debugging and fixing the tool or component issues. This may require reviewing the tool's documentation, verifying its configuration, or consulting with the tool's developers to understand the cause of the failure and implement the necessary corrections. Summary of langchain experimental plan and execute planners chat planner planning output parser. Inputs. User provided query that the chat planner needs to address and the configurations for the chain used to handle the query. Outputs. The conversation history between the user and the planner during planning and the steps that the planner has decided to execute to address the user query. Steps. Receive the user input query and the configuration options for the chain that will be used to handle the query. Initialize the chat planner with the given chain options to configure the planning process based on the given chain options. Iterate through the conversation history to understand the context of the conversation and plan the steps needed to address the user query using the chosen chain. Execute the plan by running the chosen chain with the planned steps and generate the output based on the execution results. Return the planned steps that were executed and the chat history that occurred during the planning process. Prerequisites. Langchain experimental plan and execute planners chat planner, which is a tool for planning a sequence of steps to address a user query by interacting with the user and choosing appropriate chains. Langchain experimental plan and execute planners chat planner planning output parser, which is responsible for parsing and interpreting the output of the chat planner and extracting the planned steps and conversation history from it. Fine-tune parameters. The type of chain that will be used to execute the planned steps and the temperature parameter, which controls the creativity and randomness of the planner. Challenges and fixes. Challenge 1. Planner fails to plan correctly due to ambiguous user input, which makes it difficult for the planner to understand the user intent. Fixes to challenge 1. Provide more specific and clear user input to reduce ambiguity and help the planner understand the user intent clearly. Challenge 2. Planner gets stuck in a loop while planning steps, which can occur when the planner cannot find a suitable plan or when the planning process becomes too complex. Fixes to challenge 2. Set a maximum number of iterations for planning to prevent the planner from getting stuck in an infinite loop and ensure the planning process completes within a reasonable time. Challenge 3. Planner generates irrelevant or unhelpful steps which can occur when the planner is not properly trained or when the user input is not aligned with the planner's knowledge. Fixes to challenge 3. Fine-tune the planner with more relevant data to improve its understanding of the domain and its ability to generate relevant and helpful steps. Langchain experimental, plan and execute, planners, chat planner, planning output parser. This class parses the output from a chat-based planner to extract plan information. Chat-based planners use natural language dialogue to understand the user's goals and generate a plan. To achieve them, planning output parser processes the conversation history and extracts the plan in a structured format. Inputs: a list of message objects representing the chat history of the planning process. Each message object contains the content of a message, the sender, user or planner, and the timestamp. This chat history captures the entire conversation between the user and the planner, including the user's goals, the planner's suggestions, and any clarifications exchanged. Outputs: a dictionary containing the extracted plan. This dictionary includes a list of steps that need to be taken to achieve the goal, any prerequisites that must be met before the plan can be executed, and other relevant metadata, such as potential challenges or resources needed. This structured representation of the plan can be readily used by an execution engine to carry out the plan. Steps: the parser first identifies the plan within the chat history by recognizing keywords and phrases that indicate planning steps. For example, phrases like first, we need to, or next, we should, are strong indicators of plan steps. Once the plan is identified, the parser extracts the individual steps along with any associated details. These details might include information about the step's purpose, the actions involved, or any specific conditions that need to be met. The parser identifies any prerequisites or constraints that must be satisfied before the plan can be executed. For instance, the plan might require access to certain resources or completion of specific tasks before proceeding. Finally, the parser extracts any other relevant information, such as potential challenges that might be encountered during plan execution, the resources needed to execute the plan, and the desired outcomes of executing the plan. This additional information provides valuable context and insights that can aid in plan execution and troubleshooting. Prerequisites: the chat history should contain clear and concise instructions for the planner. This includes a clear definition of the goal, any relevant context, and any constraints or preferences. The planner needs sufficient information to understand the user's requirements and generate a comprehensive plan. Fine-tune parameters. The output parser parameter within the chat planner class allows you to specify a custom parser. This gives you flexibility in customizing the parser's behavior to meet the specific needs of your planning scenario. You can, for example, define custom rules for identifying plan steps, extracting details, or handling specific types of information. Challenges and fixes. Plan steps may not be explicitly stated in the chat history. This requires the parser to infer the steps from the conversational context. For example, a user might say, "I need to book a flight to Paris and then find a hotel." While the steps are not explicitly stated, the parser can infer them by recognizing the actions in the sequence in which they are mentioned. The parser can use techniques like keyword extraction, semantic analysis, and context-aware understanding to infer plan steps. This involves identifying relevant keywords, understanding relationships between words and phrases, and considering the overall conversational context to deduce the implied plan steps. The chat history might contain irrelevant information, making it difficult to extract the plan. For example, the conversation might include personal anecdotes or off-topic discussions that are not directly related to the planning process. The parser can implement filtering mechanisms to remove irrelevant chat messages from the history. This can involve identifying messages that contain keywords associated with planning, filtering based on the sender, e.g., only retaining messages from the planner, or using machine learning techniques to identify relevant and irrelevant content. Langchain experimental plan and execute schema-based step container summarization. This YAML document describes the process of summarizing text using a language model. It defines the steps, inputs, outputs, prerequisites, fine-tuning parameters, and common challenges along with their fixes. Inputs. This is the text that needs to be summarized. For example, an article, a blog post, or a document. Outputs. This is the shortened version of the input text, retaining the most important information. Steps. 1. Extract key phrases. This involves identifying the most important words and phrases in the input text. This can be done using techniques like TF-IDF, term frequency inverse document frequency, or by analyzing the frequency of words in the text. 2. Group key phrases. Once the key phrases are identified, they are grouped together based on their semantic relationships. This helps to organize the information and identify the main themes of the text. 3. Generate summary. Finally, a summary is generated using the grouped key phrases. This can be done using a variety of methods, including using a language model like BART or T5, which can generate fluent and concise summaries. Prerequisites. Input text. This is the text that needs to be summarized. It can be any type of text, including articles, blog posts, or documents. A sample text could be an article about a new scientific discovery, a blog post about a recent event, or a document outlining a business proposal. Summarization model. This is a language model that is trained to generate summaries. Examples include BART and T5. BART bidirectional encoder representations from transformers and T5 text-to-text transfer transformer are powerful language models that can be used to generate summaries. They are trained on massive datasets of text and can understand the nuances of language, making them ideal for summarizing complex information. Fine-tune parameters. Maximum length. This parameter sets the maximum length of the generated summary. It helps control the length of the summary and ensure that it is concise. Minimum length. This parameter sets the minimum length of the generated summary. It helps ensure that the summary is not too short and contains enough information. Challenges and fixes. Summarized text is too short. The summary may not contain all the necessary information. Increase maximum length. Increasing the maximum length allows the model to generate longer summaries, potentially including more information. Summarized text is too long. The summary may be too lengthy and difficult to read. Decrease maximum length. Decreasing the maximum length forces the model to generate shorter and more concise summaries. Summarized text is not coherent. The summary may lack a logical flow and be difficult to understand. Fine-tune model. Fine-tuning the model with more specific training data can improve its ability to generate coherent summaries. Summarized text is not accurate. The summary may contain factual errors or misinterpretations of the original text. Use a more accurate model. Using a more accurate model can help to improve the accuracy of the summary. Summarized text is not relevant. The summary may not focus on the key themes of the original text or may include irrelevant information. Use a more relevant model. Using a more relevant model can help to ensure that the summary focuses on the key themes of the original text. Base planner. Base planner. An abstract base class that serves as a blueprint for defining planners. Planners are essential components in automated systems designed to strategize and execute tasks effectively. They operate by breaking down complex objectives into smaller, manageable steps, thereby enabling efficient and goal-oriented execution. Inputs. A dictionary containing a set of key-value pairs that represent the input parameters needed for the planner to function. These parameters could encompass various data points, such as user preferences, task constraints, or environmental variables, providing the planner with the necessary context to generate a suitable plan. For example, in a task management application, the inputs might include the task description, deadline, priority level, and available resources. Outputs. A list of outputs generated by the planner. These outputs typically represent the planned steps or actions to be executed, outlining the sequence of actions needed to achieve the desired goal. The output can be in various formats, such as a list of instructions, a flow chart, or a sequence of API calls. A typical output for a simple planner could be a list of steps for ordering groceries online, such as log into the website, select desired items, enter shipping address, choose payment method, and place order. Steps. The process of planning, involving the identification and ordering of steps required to reach the desired outcome. This step entails analyzing the inputs, considering constraints, and generating a coherent plan that outlines the actions to be taken and their sequence. For instance, if the goal is to write a blog post, the planning step might involve brainstorming ideas, researching relevant information, structuring the content, and outlining the paragraphs. The actual execution of the planned steps, which involves carrying out the actions outlined in the plan. This step entails invoking the appropriate tools or functions to perform the actions, managing resources, and monitoring the execution progress to ensure successful completion. In the blog post example, the execution phase would involve writing the paragraphs based on the outline, adding images and formatting, and publishing the post on the desired platform. Prerequisites. A plan and execute function, which is a crucial component that enables the planner to effectively bridge the gap between planning and execution. This function typically receives the plan as an input, translates it into executable instructions, and orchestrates the execution of the plan, potentially interacting with external systems or tools. For example, the plan and execute function could be responsible for calling external APIs, launching scripts, or managing hardware resources based on the plan generated by the planner. Fine-tune parameters. None. Challenges and fixes. Planning can be challenging or even impossible, especially when dealing with complex tasks or dynamic environments. This might arise due to incomplete information, conflicting constraints, or unpredictable external factors. Employing a more sophisticated planning algorithm can help address these challenges. Advanced algorithms, such as constraint satisfaction solvers, heuristic search strategies, or machine learning techniques, can handle more complex scenarios and generate more robust plans. Execution might fail due to various reasons, such as unexpected errors, resource limitations, or external disruptions. Robust error handling mechanisms are essential to ensure graceful execution. This involves anticipating potential errors, implementing appropriate error handling code, and providing informative feedback to the user. It may also be beneficial to incorporate retry mechanisms to handle temporary failures or to implement alternative execution paths to ensure task completion. Langchain experimental, plan and execute, planners, base planner summary. A base class for all planners in langchain. This class serves as a foundation for various planners within the langchain framework, providing a standardized structure and defining core functionalities. Planners are essential components in langchain as they guide the execution of complex tasks by breaking them down into smaller, manageable steps. Inputs. The input to the planner, which could be a string, list, or dictionary. The input serves as the initial data or information that the planner receives to work with. This could include a user query, a set of data points, or a structured representation of a task. Examples of inputs include a natural language query like "What is the capital of France?", a list of items to purchase, or a dictionary containing information about a specific topic. The context of the planner, which could be a string, list, or dictionary. The context provides additional information that is relevant to the input and helps the planner understand the task in a broader context. This could include background knowledge, previous interactions, or specific constraints. Examples of context include a document containing relevant facts, a list of previous user interactions, or a set of rules or guidelines. Outputs. A plan, which is a list of steps. The planner generates a plan based on the provided input and context. The plan outlines the sequence of actions or steps that need to be taken to complete the task. Each step represents a specific action or operation that the planner identifies as necessary to achieve the desired outcome. Plans are typically represented as lists, where each element corresponds to a step. The output of the planner, which could be a string, list, or dictionary. The output of the planner represents the final result of the planning process. This could include a response to a user query, a solution to a problem, or a generated document. The format of the output can vary depending on the specific planner and the task being addressed. Steps. Receive input and context. The initial stage involves receiving the input and context information that the planner will use to formulate a plan. This step is crucial as it lays the foundation for the planning process. Create a plan. This step involves the core functionality of the planner generating a plan based on the input and context. This could involve analyzing the input, applying rules or algorithms, and identifying the necessary steps to achieve the desired outcome. Execute the plan. Once a plan is created, the planner executes it. This involves carrying out the steps defined in the plan, potentially using other tools or resources as needed. Return the output. After the plan has been executed, the planner returns the output, which represents the result of the planning process. This could be a solution to the task, a generated response, or any other relevant information based on the specific planner and the task at hand. Prerequisites. A planning engine that can generate plans. A planning engine is responsible for creating a plan based on the input and context. It could be a simple rule-based engine, a more complex algorithm, or a sophisticated AI system capable of reasoning and decision-making. A rule-based engine uses predefined rules to determine the next step in the plan based on the current state. For example, if a rule states if the goal is to find a restaurant, then the next step is to ask the user for their location. Then the planner will follow this rule when formulating the plan. An execution engine that can execute the plan. The execution engine is responsible for carrying out the steps defined in the plan. This could be a simple function that executes a list of steps, a more complex system that interacts with external services or databases, or a combination of different engines depending on the complexity of the plan. For instance, a function that executes a list of steps could be used to send a series of commands to a web browser or a database. Fine-tune parameters. The planning engine to use. Selecting the appropriate planning engine is crucial for the effectiveness of the planner. Different planning engines have strengths and weaknesses based on the type of task and available resources. For example, a rule-based engine might be suitable for simple tasks with well-defined rules, while a more complex AI system might be better suited for tasks that require reasoning and adaptation. The execution engine to use. The choice of execution engine also significantly impacts the planner's capabilities. The execution engine should be capable of executing the steps defined in the plan efficiently and accurately. For example, if the plan involves interacting with an application programming interface API, then the execution engine should be able to make API calls and handle the responses. Challenges and fixes. The plan may not be optimal. The generated plan might not be the most efficient or effective way to achieve the goal. This could be due to limitations in the planning engine, the complexity of the task, or the lack of complete information. Using a more sophisticated planning engine, such as one based on machine learning or optimization algorithms, can help to address this challenge. These engines can learn from past experiences and data to improve the quality of the generated plans. The execution engine may not be able to execute the plan. The execution engine might not be able to execute the plan due to various factors, such as missing dependencies, access restrictions, or unexpected errors. To overcome this challenge, using a more robust execution engine that is designed to handle these situations is crucial. This could involve implementing error handling mechanisms, providing fallback options, or using more reliable and resilient systems for executing the plan. Plan output parser schema summary. Input description. The inputs required for plan output parser. The input parameters for plan output parser can vary depending on the specific use case. For example, in a scenario where you are analyzing the output of a Terraform plan, the input could be the Terraform plan file itself. In another use case, where you are parsing the output of a Kubernetes deployment, the input could be the Kubernetes manifest file. Output description. The outputs generated by plan output parser. The output of plan output parser is typically a structured representation of the input data. This could be in the form of a dictionary, a list, or any other suitable data structure. For example, when parsing a Terraform plan, the output could be a dictionary containing information about the resources that will be created, updated, or destroyed. Similarly, when parsing a Kubernetes deployment, the output could be a dictionary containing information about the deployments, services, and pods that are defined in the manifest. Steps description. Step 1 of plan output parser. This involves identifying the specific format of the input data. For instance, if the input is a Terraform plan file, plan output parser would need to identify the format of the plan file and the specific data elements it contains. Step 2 of plan output parser. This involves parsing the input data and extracting the relevant information. The parsing process may involve using regular expressions, parsing libraries, or other techniques depending on the format of the input data. Prerequisites description. Prerequisites for plan output parser. This includes having a clear understanding of the format of the input data. For example, if you are parsing a Terraform plan file, you would need to be familiar with the structure of a Terraform plan file and the different data elements it contains. Example values for the prerequisite. For instance, you would need to be familiar with the resources section of a Terraform plan file, which contains information about the resources that will be created, updated, or destroyed. Fine-tune parameters description. Parameters to fine-tune plan output parser. These parameters can be used to customize the behavior of plan output parser. For example, you can specify the level of detail that you want to extract from the input data or the specific data elements that you are interested in. Challenges and fixes description. Challenge faced while using plan output parser. One challenge that is often faced when using plan output parser is handling different versions of a input data format. For example, Terraform plan files can have different versions, and each version may have a slightly different structure. Fixes for the challenge. To address this challenge, plan output parser should be able to handle different versions of the input data format. This can be achieved by using version-specific parsing logic or by using a generic parsing approach that can handle different versions of the input data format. Langchain experimental plan and execute executors agent executor load agent executor summarization. Langchain is a framework for developing and deploying language models. The plan and execute executors agent executor load agent executor summarization is a component of Langchain that combines the planning and execution capabilities for creating effective agents. Inputs. An agent is a program that can interact with its environment and learn from its experiences. An agent typically has a set of predefined tools and a large language model (LLM) that it uses to make decisions. A user input or task is a request from a user that the agent is expected to complete. This could be a question, a command, or a more complex task that requires multiple steps to complete. Outputs. The agent's output is the response to the user input or task. This could be a simple answer to a question, a list of steps to complete a task, or a more complex response that includes text, code, or other data. Steps. The agent uses the LLM to plan a series of steps to complete the user input or task. This planning process may involve analyzing the input, identifying relevant tools, and generating a sequence of actions that are likely to achieve the desired outcome. The agent executes the planned steps using the tools that are available to it. This may involve calling APIs, interacting with databases, or performing other actions that are necessary to complete the task. The agent gathers the results of its actions and analyzes them to determine if the task has been completed successfully. The agent provides the final output to the user, which may include the results of its actions, any feedback on the success or failure of the task, or other relevant information. Prerequisites. LangChain is a Python library that provides a framework for building and deploying language models. It includes a wide range of tools and components for working with LLMs, including agents, tools, chains, and more. To use the plan and execute executors agent executor load agent executor summarization, you will need to have LangChain installed on your system. An agent is a program that can interact with its environment and learn from its experiences. An agent typically has a set of predefined tools and a large language model (LLM) that it uses to make decisions. To use the plan and execute executors agent executor load agent executor summarization, you will need to define an agent that has the necessary tools and LLM to complete the user input or Task. Fine-tune parameters. The LLM model is the core of the agent and plays a critical role in planning and executing tasks. Fine-tuning the LLM model can significantly improve the performance of the agent. This can involve adjusting the model's parameters, training the model on a specific dataset, or using other techniques to optimize the model for a particular task. Agent configuration involves defining the tools, the LLM, and other parameters that the agent will use to complete tasks. Fine-tuning the agent configuration can involve adjusting the order of tools, changing the LLM, or modifying other settings to optimize the agent's performance for a specific task or environment. Challenges and fixes. The agent may fail to plan effectively if the user input or task is not clear, or if the agent does not have the necessary tools or knowledge to complete the task. This can be addressed by providing clear and specific instructions to the agent, ensuring that the agent has access to the necessary tools and information, and using a more powerful LLM that can handle complex tasks. For example, if the task is to write a short story about a robot that travels to the moon, the agent may not be able to plan effectively if it does not have access to information about robots, the moon, or story writing. In this case, providing the agent with access to relevant resources, such as Wikipedia articles or online tutorials, can help it plan more effectively. The agent may struggle with tool execution if the tools are not properly integrated, or if the agent does not have the necessary permissions to use the tools. This can be addressed by ensuring that the tools are properly configured and integrated into the agent's environment, verifying that the agent has the necessary permissions to access and use the tools, and providing clear and concise instructions on how to use each tool. For example, if the agent needs to access a database to retrieve information, the agent may need to be configured with the correct database credentials and permissions to access the data. Similarly, if the agent needs to use an API to get information from a website, the agent may need to be configured with the correct API key and other necessary information. The agent may produce incorrect outputs if the LLM is not accurate, if the tools are not reliable, or if the agent does not properly validate the results of its actions. This can be addressed by selecting a reliable and accurate LLM, ensuring that the tools are well tested and validated, and implementing mechanisms for the agent to verify the results of its actions. For example, if the agent is asked to write a summary of a news article, it may produce incorrect outputs if the LLM is not able to accurately understand and summarize the text. In this case, the agent could be designed to use a tool that can verify the accuracy of the summary, such as a plagiarism detection tool. Langchain experimental plan and execute planners. Chat Planner. Load Chat Planner. Chat Planner is a tool that assists in executing plans by leveraging chat models. It can be used to create plans and execute steps. This tool can be used to break down large tasks into smaller, manageable steps and then use a chat model to complete these steps. Inputs: a plan or goal to achieve. This can be anything from writing a blog post to booking a flight. The goal should be clearly defined and specific. Contextual information related to the plan. This can include any relevant information that the chat model needs to know in order to execute the plan. For example, if the goal is to write a blog post, the context might include the topic of the post, the target audience, and the desired length. Outputs: an execution plan. This is a step-by-step guide that outlines how the chat model will execute the plan. The plan should be detailed and easy to follow. Output of the executed plan. This is the result of the chat model executing the plan. For example, if the goal was to write a blog post, the output would be the completed blog post. Steps. Define a goal. The first step is to clearly define the goal that you want to achieve. This should be a specific and measurable goal. Create a plan to achieve the goal. Once you have defined your goal, you need to create a plan to achieve it. This plan should outline the steps that need to be taken to achieve the goal. Execute the plan by interacting with the chat model. The final step is to execute the plan by interacting with the chat model. The chat model will follow the steps in the plan and complete the tasks. Prerequisites. A working chat model. This is a large language model that can be used to interact with the chat planner tool. ChatGPT is a large language model chatbot developed by OpenAI. It is a powerful tool that can be used for a variety of tasks, including generating text, translating languages, writing different kinds of creative content, and answering your questions in an informative way. BARD is a factual language model from Google AI, trained on a massive dataset of text and code. It can generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. A plan or goal to achieve. This is the task that you want the chat planner tool to help you with. Write a blog post. This could be a blog post on any topic, such as technology, travel, or food. Book a flight. This could be a flight to any destination, such as a vacation spot or a business meeting. Fine-tune parameters. Prompt engineering. This is the process of crafting effective prompts for the chat model. The prompts should be clear, concise, and specific. Model selection. This is the process of choosing the right chat model for the task. Some chat models are better suited for certain tasks than others. Challenges and fixes. Plan complexity. If the plan is too complex, the chat model may not be able to execute it properly. Use a more capable model. If the plan is too complex for the current chat model, you can try using a more capable model. Ambiguous instructions. If the instructions in the plan are ambiguous, the chat model may not be able to understand what is being asked of it. Improve plan clarity. If the instructions are ambiguous, you should try to improve the clarity of the plan. This can be done by providing more specific instructions or by breaking down the plan into smaller, more manageable steps. Model limitations. Chat models have limitations and may not be able to perform all tasks. Modify plan or use different model. If the chat model is unable to perform a task, you may need to modify the plan or use a different chat model. Langchain experimental plan and execute. Executors agent executor load agent executor. Agent executor is a langchain executor that combines planning and execution. It utilizes a large language model LLM to plan tasks and a set of tools for execution. For example, the agent executor can be used to plan a trip, where the LLM would plan the itinerary and the tools would be used to book flights and hotels. Inputs. Agent executor requires a tool specification, which defines the tools that the agent can use, and a large language model LLM. The LLM provides the intelligence for the agent, while the tools provide the ability to interact with the real world. An agent is a conversational AI that can complete complex tasks. It is trained to understand and respond to natural language, and it can be used to automate a wide variety of tasks. For example, an agent can be used to book a flight, order food, or schedule a meeting. Outputs. Agent executor provides results from the agent's execution. These results can be in the form of text, code, or other data formats. Agent executor returns a structured output. This output can be used to understand the agent's reasoning and the steps that were taken to complete the task. Steps. Agent executor uses the large language model LLM to plan a series of steps. The LLM analyzes the task and generates a plan of action, taking into account the available tools and their capabilities. The agent uses the tools to complete the planned steps. The agent executes the plan, using the tools to interact with the real world and gather information. The agent returns the results from the execution. The agent provides a summary of the completed tasks, including any errors or warnings that occurred. Prerequisites. Knowledge about large language models, LLMs, and tool integration. An LLM is a type of artificial intelligence that can understand and generate human-like text. Tool integration refers to the process of connecting an LLM with external tools that can perform specific actions. OpenAI Application Programming Interface API key is required for accessing OpenAI's language models. Familiarity with task execution workflows. This involves understanding how to break down a complex task into smaller, manageable steps. It also requires an understanding of how to use tools to complete these steps. Agent specification defines the agent's capabilities and how it can be used to complete a task. Fine-tune parameters. Large language model LLM model selection. This involves choosing an LLM that is best suited for the task at hand. Factors to consider include the LLM's size, training data, and cost. Tool configuration. This involves setting up the tools that the agent will use. This includes providing the necessary credentials and configuration parameters. Challenges and fixes. Large language model LLM might generate incorrect or incomplete plans. This can happen if the LLM is not properly trained or if the prompt is not clear and concise. Use a more powerful large language model LLM or refine the prompt. A more powerful LLM is likely to be able to generate more accurate and complete plans. Refining the prompt involves providing the LLM with more specific instructions and context. Tools might not work as expected. This can happen if the tools are not properly configured or if there are errors in the code or data used by the tools. Verify tool configurations and update them if needed. This involves checking that the tools are properly configured and that the necessary credentials are in place. If necessary, update the tool configuration to fix any errors. Langchain experimental prompt injection identifier, Hugging Face identifier. Hugging Face injection identifier. This identifier is used for detecting prompt injections in Hugging Face models. It is specifically designed to analyze the input provided to a Hugging Face model and determine if it contains malicious code that could manipulate the model's behavior. Inputs. The input provided to a Hugging Face model. This could be text, code, or any other type of data that the model is trained to process. Outputs. A Boolean value that indicates whether a prompt injection was detected. A true value signifies the presence of a potential injection, while false indicates no such injection was found. Steps. The identifier analyzes the model input to pinpoint potential injection points. These points are typically locations within the input where malicious code could be inserted to influence the model's response. For example, the identifier might look for unusual characters, specific patterns in the input, or commands that could potentially be exploited. After identifying potential injection points, the identifier assesses the level of risk associated with each point. This assessment typically involves comparing the detected patterns against known attack techniques. and evaluating the potential impact of an injection on the model's output. Based on this evaluation, the identifier assigns a risk score to each potential injection point. Prerequisites: a Hugging Face model. This could be any model available on the Hugging Face hub, such as a language model, a code generator, or an image classifier. For example, a popular language model is GPT-2, which can be used for generating human-like text. Model input: the input text provided to the model, which can be any text or code that the model is designed to process. For instance, the input could be a prompt for text generation or a code snippet for code completion. Fine-tune parameters. Injection risk threshold. This parameter allows the user to adjust the sensitivity of the identifier by defining the specific threshold for risk levels. The identifier then only flags potential injections that surpass this threshold. This threshold can be fine-tuned to balance accuracy with sensitivity, based on the specific use case and the desired level of security. Challenges and fixes. False positives. These occur when the identifier incorrectly identifies a legitimate input as a potential injection. This could happen due to the presence of specific patterns in the input that the identifier interprets as malicious, despite being harmless. To mitigate false positives, the threshold for risk levels can be revised to make the identifier less sensitive and focus on identifying more likely injection points. Missing injections. This issue arises when the identifier fails to detect a genuine prompt injection that is present in the model input. This could occur due to limitations in the identifier's detection capabilities, particularly when encountering novel or complex injection techniques. To improve detection, the identifier can be enhanced with advanced pattern recognition algorithms and updated with knowledge of emerging injection methods. This ensures that the identifier stays ahead of potential attackers and maintains its effectiveness. In identifying prompt injections, langchain experimental prompt injection identifier, Hugging Face identifier, Hugging Face injection identifier. This component aims to detect vulnerabilities related to prompt injection in Hugging Face models. Prompt injection occurs when an attacker can manipulate the input prompt to influence the model's output in unintended ways. This component assesses the model's susceptibility to such attacks by analyzing its responses to carefully crafted test prompts. Inputs. Hugging Face model. This refers to the specific model from Hugging Face that is being evaluated for prompt injection vulnerabilities. The model could be a pre-trained model or a fine-tuned model. Input prompt. The input prompt is the text that is fed into the Hugging Face model as a starting point for generating output. It can be a question, a statement, or any text that prompts the model to generate a response. Outputs. Boolean indicating prompt injection vulnerability. This output represents the result of a vulnerability assessment. It will be either true or false, indicating whether the Hugging Face model is deemed vulnerable or not to prompt injection. Steps. Load the Hugging Face model. This step involves retrieving the specified Hugging Face model from the Hugging Face repository. It loads the model's weights and configuration, preparing it for analysis. Generate responses using the model with a set of test prompts. The core of the analysis process. It involves feeding a carefully designed set of test prompts into the model and observing its responses. These test prompts are crafted to potentially trigger prompt injection vulnerabilities. Analyze the responses for any signs of prompt injection. After generating responses to the test prompts, this step involves scrutinizing the responses for any evidence of prompt injection vulnerabilities. The component analyzes the responses for unexpected behaviors, deviations from expected outputs, or patterns suggestive of malicious influence. Prerequisites. Hugging face model. This prerequisite implies that the Hugging Face model being analyzed needs to be clearly specified. It requires providing the model's name and its corresponding ID within the Hugging Face repository. For instance, you might need to specify GPT-2 as the model name and GPT-2 as its ID. Input prompt. The input prompt is another prerequisite, and it entails providing several example prompts that are representative of the types of inputs the model is expected to handle. These examples can be diverse, encompassing various styles of prompts, questions, or statements. For instance, examples could include "What is the capital of France?" or "Summarize the plot of the movie The Matrix." Fine-tune parameters. Test prompts. The test prompts are one of the critical components of the vulnerability assessment. Carefully designing them is essential to uncovering potential vulnerabilities. They need to be strategically crafted to explore various ways an attacker might attempt to inject malicious code or influence the model's behavior. Vulnerability detection criteria. These criteria act as the rules or guidelines used to determine whether a vulnerability has been detected. They define the specific signs or patterns in the model's responses that would indicate a prompt injection vulnerability. Challenges and fixes. False positives due to complex model behavior. The complex nature of large language models can sometimes lead to responses that appear to be vulnerabilities but are actually just unintended outputs. These false positives can arise from the model's inherent limitations or its training data biases. Use more diverse test prompts. Refine vulnerability detection criteria to minimize false positives. It's essential to employ a wide range of test prompts that cover diverse input scenarios. This diversity helps to reduce the likelihood of misinterpreting unintended model behavior. Refining the vulnerability detection criteria, making them more specific and tailored to the model's behavior, can also contribute to reducing false positives. Missing vulnerabilities due to limited test prompt coverage. A limited set of test prompts might fail to identify vulnerabilities that could be triggered by certain specific types of inputs. Expand the set of test prompts. Consider edge cases. Expanding the set of test prompts to include edge cases, less common but still relevant input scenarios, can enhance the thoroughness of the vulnerability assessment. This expansion helps to catch vulnerabilities that might otherwise go undetected. Langchain experimental recommenders. Recommending content and items to users using langchain. This YAML document provides an overview of langchain experimental recommenders, highlighting its purpose, inputs, outputs, steps, prerequisites, fine-tune parameters, and challenges with corresponding solutions. A module for building recommendation systems using langchain. It allows developers to create systems that suggest relevant content or items to users based on their preferences and historical data. Inputs. User preferences. These are the individual tastes and interests of the users. For example, if a user is interested in movies, their preferences might include genre, actors, directors, or themes. Historical data. This refers to the past interactions of users with the system or with related items. Examples include previously viewed movies, purchased products, or rated items. Outputs. Recommended items. This is the primary output of the recommender system, consisting of a list of items that are most likely to be relevant and appealing to the user based on their preferences and historical data. Explanations for recommendations to enhance transparency and user trust. These explanations provide insights into the reasoning behind the recommended items. For instance, the explanation could highlight the specific user preferences or historical data points that led to the recommendation. Steps. Define user preferences. This step involves understanding and representing the user's interests and preferences in a structured format suitable for the recommender system. This can involve capturing explicit preferences, e.g., through user-provided ratings or reviews, or inferring preferences from implicit data, e.g., viewing history or clickstream data. Retrieve historical data. This step involves accessing and gathering past interactions of the user with the system or related items. This historical data is crucial for understanding the user's past behavior and predicting future preferences. Generate embeddings for user preferences and items. This step involves converting user preferences and items into numerical representations, called embeddings. These embeddings capture the semantic meaning and relationships between items and users. Facilitating similarity calculations. Calculate similarity scores. This step involves measuring the similarity between user preferences and items based on their embeddings. Various similarity metrics, such as cosine similarity or Euclidean distance, can be employed to quantify the degree of resemblance. Rank items based on similarity. This step involves sorting items according to their similarity scores, ranking the most similar items higher. This ranking process ensures that the most relevant items are presented to the user first. Provide recommendations. This final step delivers the ranked list of recommendations to the user. This could involve presenting the top few recommendations or offering a personalized list tailored to the user's specific preferences. Prerequisites. Langchain. Langchain is a powerful framework for building and connecting language models and other tools. It provides a flexible and modular approach to developing recommender systems, enabling seamless integration of various components and functionalities. Embedding models. Embedding models are essential for representing user preferences and items in a numerical format suitable for similarity calculations. These models learn to map words or phrases into dense vector spaces, capturing the semantic relationships between items. Fine-tune parameters. Similarity metric. The choice of similarity metric plays a crucial role in determining the effectiveness of the recommender system. Different metrics capture different aspects of similarity, and selecting the appropriate metric can significantly impact the quality of recommendations. Ranking algorithm. The ranking algorithm determines the order in which recommended items are presented to the user. The choice of ranking algorithm can influence the diversity and relevance of recommendations. Challenges and fixes. Cold start problem. This challenge arises when there is limited historical data available for a new user or a new item. Without sufficient data, it is difficult to accurately predict the user's preferences or the relevance of the item. Utilize external data sources. This solution involves leveraging external data sources, such as social media profiles, product descriptions, or user reviews, to supplement the limited historical data. This additional information can help infer user preferences or item relevance in the absence of direct user interactions. Data sparsity. This challenge occurs when the data available for user preferences or item interactions is sparse and incomplete. Sparse data can make it difficult to accurately capture user preferences or item relationships. Employ collaborative filtering techniques. Collaborative filtering techniques leverage the preferences of other users who have interacted with similar items to make recommendations for the current user. This approach helps to overcome data sparsity by considering the collective preferences of similar Users. Bias in recommendations. This challenge arises when the recommendations are not fair or representative of the diverse user population. Biases can stem from various factors, including historical data reflecting existing societal biases or algorithmic biases introduced during model training. Implement fairness constraints to mitigate bias. Fairness constraints can be incorporated into the recommender system. This involves ensuring that the recommendations are not disproportionately favoring certain user groups or items, promoting a more equitable and diverse set of recommendations. Explaining recommendations. Providing explanations for recommendations is crucial for building user trust and transparency. Explanations help users understand the reasoning behind the recommendations and increase their confidence in the system. Leverage LLMs for generating explanations. Large language models (LLMs) can be employed to generate natural language explanations for recommendations. LLMs can understand the context of user preferences, historical data, and similarity calculations to create coherent and informative explanations. Langchain Experimental Prompt Injection Identifier. This tool aims to identify potential prompt injection vulnerabilities within langchain chains. Prompt injection occurs when an attacker can manipulate the prompts used by a language model, potentially leading to unintended or malicious outputs. This tool analyzes langchain chains, searching for points where user input could be injected into prompts and potentially exploited. Inputs. The input to this tool is a langchain chain. A langchain chain is a series of components that are linked together to perform a specific task. For example, a chain could be used to summarize a document, translate a text, or generate creative content. Outputs. The output of this tool is a list of vulnerabilities. Each vulnerability represents a potential point where an attacker could inject malicious input into the chain's prompts. The list of vulnerabilities includes information about the severity of each vulnerability and potential mitigation strategies. Steps. The first step in identifying prompt injection vulnerabilities is to analyze the chain structure. This involves understanding the components of the chain, the flow of data through the chain, and the ways in which user input is processed. Once the chain structure is understood, the tool identifies potential injection points. These are points where user input could be directly or indirectly injected into the prompts used by the language model. The final step is to evaluate the severity of each vulnerability. This involves considering the potential impact of an attacker successfully exploiting a vulnerability. The severity is rated based on the potential damage that could be caused, such as data leakage, system compromise, or reputational damage. Prerequisites. A fundamental understanding of langchain is necessary. This includes knowledge of chain composition, the different types of chains available, and the input-output types supported by langchain. Langchain chains are composed of different components, such as prompts, language models, and data sources. Understanding how these components are interconnected is crucial for identifying vulnerabilities. Langchain supports various chain types, including simple chains, chains with loops, and chains with parallel execution. Each type has different characteristics and potential vulnerabilities. Understanding the input and output types of each component is essential for assessing the potential impact of prompt injection. Knowledge of prompt injection attacks is crucial. This includes understanding attack vectors, common mitigation techniques, and the potential consequences of successful attacks. Attack vectors in prompt injection include injecting malicious code, manipulating the context, or altering the desired output. Mitigation techniques for prompt injection vulnerabilities include input sanitization, prompt engineering, and code analysis tools. Successful prompt injection attacks can lead to various consequences, including data leakage, system compromise, reputational damage, and the generation of harmful content. Fine-tune parameters. The vulnerability detection rules are used to identify potential injection points in the chain. These rules are based on patterns and characteristics of known prompt injection vulnerabilities. The severity scoring mechanism is used to assign a severity rating to each vulnerability. This mechanism considers the potential impact of exploiting the vulnerability and the likelihood of success. The scoring system helps prioritize vulnerabilities and guide mitigation efforts. Challenges and fixes. False positives can occur when the tool incorrectly identifies a vulnerability that does not exist. This can happen due to the complexity of the analysis process or limitations in the detection rules. One approach to address false positives is to refine the detection rules based on feedback and additional testing. It can be challenging to identify complex vulnerabilities, especially those involving multiple components or intricate data flows within the chain. Implementing advanced analysis techniques, such as static code analysis and dynamic analysis, can help identify complex vulnerabilities. The tool may have limited support for all chain types, particularly those involving custom components or complex logic. Expanding compatibility to cover a wider range of chain types requires ongoing development and testing. Assessing the impact of vulnerabilities can be challenging. Determining the potential damage caused by an attacker successfully exploiting the vulnerability requires a comprehensive understanding of the chain's functionality and its integration within a larger system. Integrating with security tools, such as vulnerability scanners and security information and event management SIEM systems, can provide valuable insights into the impact of vulnerabilities. The tool may lack automated mitigation mechanisms, requiring manual intervention to address vulnerabilities. Developing automated patching mechanisms for prompt injection vulnerabilities is an ongoing area of research. These mechanisms would automatically identify and fix vulnerabilities, reducing the burden on developers and improving security posture. Langchain experimental recommenders Amazon personalized summarization. This is a description of a recommender based on Amazon Personalize. Amazon Personalize is a service that helps you build personalized recommendations for your customers. It is a powerful and versatile tool that can be used for a variety of recommendation tasks. Inputs. The user's past interactions refer to data about the user's behavior in the past. This might include items that they have purchased, items they have added to their shopping cart, items they have viewed, items they have rated, or any other type of interaction data that you can collect. This refers to features that describe each item in your catalog. This could include information such as the item's title, description, and category, the price, color, size, and other attributes of the item, the item's popularity and ratings, the item's image, video, and other media. Outputs. The output of the recommender is a list of items that are recommended to the user. This list may be ranked in order of relevance, with the most relevant items appearing at the top. Steps. The first step is to initialize an Amazon Personalize client. This can be done using the Amazon Personalize Application Programming Interface API. The next step is to create a dataset group. This dataset group is used to store the data that you will use to train your recommender model. The data is then imported to the dataset group. This data will be used to train your model and generate recommendations. The fourth step is to create a solution. This solution is a configuration that defines the recommender model that you want to build. The fifth step is to train the solution. This step uses the data you have imported to train the recommender model. The sixth step is to create a recommender. This recommender is an endpoint that you can use to generate recommendations. The final step is to generate recommendations. Once the recommender is created, you can use it to generate recommendations for your users. Prerequisites. To use Amazon Personalize, you need an Amazon Personalize account. An Amazon Web Services (AWS) account is required for accessing Amazon Personalize. Amazon Web Services is a suite of cloud computing services offered by Amazon. You will need the Amazon Personalize service itself. Amazon Personalize is a fully managed service that provides the tools and infrastructure that you need to build and deploy personalized recommendations. To train the recommender model, you need data about the items and users that you want to recommend. User interaction data describes the user's interactions with your system. For example, the items they have viewed, the items they have added to their cart, the items they have purchased, or the items they have rated. Item metadata is information about the items that you want to recommend. For example, the item's title, description, category, price, color, size, or other attributes of the item. Fine-tune parameters. The number of recommendations to return is the number of recommendations that the recommender will generate. You can adjust this parameter to control the number of recommendations that are generated. Recommendation relevance is a measure of how relevant the recommendations are to the user. You can adjust this parameter to control the quality of the recommendations that are generated. Challenges and fixes. The cold start problem occurs when you have limited data about a new user or a new item. In this case, it is difficult to generate accurate recommendations. Content-based filtering is a technique that can be used to address the cold start problem. It uses the features of the item to generate recommendations. For example, if a new user is interested in books about cooking, you can recommend other books that are in the same category. Data sparsity occurs when you have a limited amount of data about your users and items. Collaborative filtering is a technique that uses the past interactions of other users to generate recommendations. For example, if two users have purchased the same items in the past, you can recommend items that the first user has purchased to the second user. Hybrid recommendation is a technique that combines content-based filtering and collaborative filtering to generate recommendations. This can be used to address the challenges of cold start and data sparsity. Data quality is important for generating accurate recommendations. Cleaning and pre-processing data involves removing errors, inconsistencies, and duplicates from your data. This can help improve the accuracy of your recommendations. Data augmentation techniques are used to generate synthetic data that can be used to train your model. This can help improve the accuracy of your recommendations, especially when you have limited data. Scalability is important when dealing with large amounts of data. Amazon Personalizer's managed services are designed to scale to handle large amounts of data. This allows you to build and deploy recommender models without having to manage the underlying infrastructure. Optimizing model architecture involves selecting the right model for your use case and tuning the hyperparameters of the model. This can help improve the performance and scalability of your recommender model. Explainability is important for understanding how recommendations are generated. Interpretable models are models that are easy to understand and explain. This can help you understand why certain recommendations are being made. Generating explanations for recommendations can help users understand why they are being recommended certain items. This can increase user trust and confidence in the recommender system. Langchain Experimental Recommenders. A module within langchain that provides tools for building recommender systems based on language models. Inputs. A set of user preferences or historical data which can be explicit preferences like reviews or ratings, or implicit preferences like browsing history or purchase history. A corpus of potential recommendations which can be a collection of books, movies, products, or any other items that you want to recommend. Outputs. A list of recommended items which could be a list of books, movies, products, or any other items that are relevant to the user's preferences in the provided corpus of potential recommendations. Steps. Represent user preferences or historical data as a vector, which is a mathematical representation of the user's preferences. This representation can be used to calculate the similarity between the user and the items. Represent potential recommendations as vectors, which is a mathematical representation of each item. This representation can be used to calculate the similarity between the user and the items. Calculate similarity between user and item vectors. This is a measure of how similar the user's preferences are to each item. Rank recommendations based on similarity scores, which is a list of recommended items sorted by their similarity to the user's preferences. Prerequisites. A language model capable of generating embeddings, which is a numerical representation of text that can be used to calculate similarity between different pieces of text. OpenAI's Text Embedding ADA-002 model, which is a state-of-the-art embedding model from OpenAI that can be used to generate text embeddings. This model can be used to represent both user preferences and potential recommendations as vectors. A data set of items to recommend, which can be a collection of books, movies, products, or any other items that you want to recommend. For example, an e-commerce store may have a dataset of products that it wants to recommend to its users. A set of products in an e-commerce store which can be used to create a recommender system that recommends products to users based on their preferences and purchase history. Fine-tune parameters. Embedding model parameters, which are the parameters that control how the embedding model generates embeddings. These parameters can be fine-tuned to improve the performance of the recommender system. Similarity metric parameters, which are the parameters that control how the similarity between user and item vectors is calculated. These parameters can be fine-tuned to improve the performance of the recommender system. Ranking algorithm parameters, which are the parameters that control how the recommendations are ranked. These parameters can be fine-tuned to improve the performance of the recommender system. Challenges and fixes. Cold start problem, which is the problem of recommending items to new users who have no history or preferences. Utilize techniques like collaborative filtering, which is a technique that uses the preferences of other users to recommend items to new users. Data sparsity issues, which is the problem of having limited data about user preferences or item properties. Leverage techniques like content-based filtering, which is a technique that recommends items based on their content similarity to items that the user has already interacted with. Scalability concerns, which is the problem of recommending items to a large number of users in real time. Optimize vector similarity calculations, which can be optimized to improve the performance of the recommender system and make it more scalable. Bias in recommendations, which is the problem of recommending items that are biased towards certain Groups of users employ fairness-aware ranking algorithms, which are algorithms that take into account fairness considerations when ranking recommendations. This can help to reduce bias in the recommendations. Langchain experimental plan and execute executors agent executor load agent executor summary. The agent executor and load agent executor are components within langchain's experimental plan and execute feature, enabling the execution of complex tasks involving multiple steps. These executors are designed to handle tasks that require a series of actions and decisions, often involving external tools or APIs. The agent executor utilizes an agent, which is a self-contained entity that possesses knowledge, reasoning capabilities, and access to tools to accomplish tasks effectively. Inputs. Agent and agent is an essential element for the agent executor. It encompasses a set of tools, memory, and a language model. The agent leverages these resources to execute tasks intelligently and efficiently. The task is a concise and well-defined description of what needs to be accomplished. It serves as a guide for the agent, outlining the desired outcome and any constraints. An example of a task could be retrieve the weather forecast for tomorrow in New York City. Outputs. The output represents the outcome of the agent's execution of the task. It can be a variety of formats, such as text, a list, a table, or any other data structure appropriate for the task. For example, the output for the weather forecast task could be a text string containing the predicted weather conditions for tomorrow in New York City. Steps. Agent receives the task. The agent begins by receiving the task from the user or another component in the system. This involves understanding the task's requirements, objectives, and any relevant context. Agent plans how to execute the task based on the task received. The agent generates a plan of action. This plan involves selecting appropriate tools, deciding on the sequence of steps, and anticipating potential challenges. The agent executes the plan. The agent then carries out the plan, invoking tools, accessing data, and making decisions based on its knowledge and the available information. Agent returns the output once the plan is executed. The agent delivers the output back to the user or the requesting component. This output represents the completed task and the results of the agent's actions. Prerequisites. Agent definition. An agent definition is a blueprint that outlines the agent's capabilities. It includes a comprehensive list of tools, access to memory for storing past interactions, and a language model that enables the agent to understand and generate human-like text. The agent definition is crucial for the agent to function effectively, as it provides the necessary components for its operations. Task definition. A clear and well-defined task definition is essential for successful execution. It ensures that the agent understands the task's objective, constraints, and any specific requirements. The task definition should be unambiguous and comprehensive to avoid any misinterpretations by the agent. For example, a task definition for retrieving the weather forecast in New York City should clearly specify the location New York City, the desired time frame tomorrow, and the type of information to be retrieved weather forecast. Fine-tune parameters. Agent configuration. Agent configuration involves fine-tuning various parameters to optimize the agent's performance. These parameters may include the selection of the language model, the number of steps allowed in the plan, the memory capacity, and the threshold for using different tools. By adjusting these parameters, the agent's behavior can be tailored to specific needs and improve its efficiency. Tool configuration. Tools are essential resources for agents. allowing them to interact with the outside world and perform actions. Tool configuration involves specifying the parameters and settings for each tool. For instance, configuring an API tool might involve setting authentication credentials, API endpoints, and request limits, challenges and fixes. Missing tools: if an agent lacks the necessary tools to execute a task, it may fail to complete the task successfully. This challenge can be addressed by ensuring that the agent definition includes all the tools required for the tasks it is expected to perform. For instance, if the agent needs to access a weather API to retrieve weather forecasts, the API tool must be included in the agent definition. Unclear task instructions: if the task definition is ambiguous or lacks clarity, the agent may misinterpret the instructions and produce incorrect or irrelevant results. To resolve this, the task definition should be carefully crafted to be clear, concise, and unambiguous. For example, instead of a vague task like "Tell me about New York City," a more specific task definition could be "Provide information about the population of New York City." Limited memory agents may have limited memory capacity, which can hinder their ability to remember past interactions and learn from previous experiences. To address this challenge, agents can be equipped with larger memory capacities or utilize memory optimization techniques to store and access relevant information efficiently. Agent performance: the agent's performance can be affected by factors such as the efficiency of its planning process, the selection of tools, and the underlying language model. By fine-tuning the agent configuration, such as adjusting the planning algorithm or choosing a more powerful language model, the agent's performance can be enhanced. Error handling: agents should be equipped with robust error handling mechanisms to prevent unexpected failures and ensure graceful recovery from errors. This can involve implementing exception handling, error logging, and strategies to retry failed operations. Robust error handling is crucial for reliable agent execution, especially in environments where external tools or APIs might be unstable or unavailable. Langchain experimental RL chain. A description of an RL chain: this chain utilizes reinforcement learning to fine-tune a language model. It trains a language model by iteratively generating responses, evaluating them with a reward function, and updating the model based on these rewards. Inputs. Prompts for training: these are the text inputs used to generate responses during the training process. The model will learn to generate text that aligns with the provided prompts. For example, a prompt could be a question or a statement, and the model would learn to generate appropriate responses. Reward function: this is a function that evaluates the quality of the responses generated by the model. It assigns a numerical score to each response, indicating how well it satisfies a specific criteria. For example, a reward function could be designed to evaluate the fluency, coherence, and relevance of the generated responses. Outputs. Fine-tuned language model: the output of the RL chain is a language model that has been optimized for a specific task based on the training data and the reward function. This model will be able to generate responses that are more aligned with the desired criteria than a model that has not been fine-tuned. Steps. Data collection: in this step, the model generates responses to the provided prompts. These responses will be used as training data for the model. For example, the model could be asked to summarize a news article or to generate creative writing. Response evaluation: the generated responses are evaluated using the reward function. This function assigns a score to each response based on its quality. For example, if the reward function is designed to evaluate the fluency of the responses, The responses that are grammatically correct and flow naturally will receive a higher score. Model update based on the rewards received for each response. The model's parameters are updated. The goal of this step is to improve the model's ability to generate responses that are rewarded more highly. This process of generating responses, evaluating them, and updating the model is repeated iteratively until the model reaches a desired level of performance. Prerequisites. GYM environment: a software environment that allows for the implementation and execution of reinforcement learning algorithms. The OpenAI GYM environment provides a collection of standard tasks that can be used to train and test reinforcement learning agents. Examples of tasks include controlling a robotic arm, playing a game, or navigating a maze. Reinforcement learning algorithm: an algorithm that learns to optimize its behavior in an environment by receiving rewards or penalties. The proximal policy optimization (PPO) algorithm is a widely used reinforcement learning algorithm that has been shown to be effective in various applications. PPO is a policy gradient method that uses a surrogate objective function to improve the policy while maintaining stability. Fine-tune parameters. Learning rate: the learning rate controls the step size taken during the model update process. A higher learning rate results in larger updates, which can lead to faster learning but may also increase the risk of instability. A lower learning rate results in smaller updates, which can lead to more stable learning but may also slow down the learning process. The optimal learning rate depends on the specific task and the model architecture. Discount factor: the discount factor determines the importance of future rewards relative to immediate rewards. A discount factor closer to 1 indicates that future rewards are highly valued, while a discount factor closer to 0 indicates that future rewards are less important. The choice of discount factor affects the agent's long-term planning horizon. Challenges and fixes. Reward function design: designing an effective reward function is crucial for the success of a reinforcement learning system. The reward function should accurately reflect the desired behavior of the agent. One approach to reward function design is to use expert demonstrations. Expert demonstrations provide examples of optimal behavior that can be used to guide the agent's learning. For example, in a game-playing setting, expert demonstrations could consist of gameplay by professional players. Overfitting to training data: overfitting occurs when the model learns to perform well on training data but generalizes poorly to unseen data. Regularization techniques can be used to prevent overfitting. Regularization techniques introduce penalties to the model parameters that discourage the model from becoming too complex. Common regularization techniques include weight decay and dropout. Weight decay reduces the magnitude of the model parameters, while dropout randomly drops out units in the neural network during training. These techniques can improve the generalization ability of the model. Langchain experimental, RL chain, base, auto selection scorer summary. A detailed description of the auto selection scorer, a component of reinforcement learning RL chains in langchain. The current state of the environment, which is the context or situation the RL chain is operating in. For example, if the RL chain is a chatbot, the environment might be the ongoing conversation with a user, the specific action taken by the chain within the environment. For instance, if the chain is a chatbot, the action could be the choice of the next response to be sent to the user. The reward for taking the action. This reward is a numerical value that reflects how well the action contributed to achieving the overall goal of the RL chain. The higher the reward, the more desirable the action was. Calculate the reward for the action based on a predefined reward function. This function quantifies the benefit of the action in the current environmental context. Return the calculated reward to the RL chain. This reward is used by the RL algorithm to learn and improve its decision-making process by adjusting the weights of its components. An RL chain is a collection of modules that work together to perform a task. The chain's objective is to maximize the reward it receives over time through interactions with its environment. A reward function is a mathematical expression that assigns a numerical value to each possible action taken by the chain. It acts as a guide for the chain, indicating which actions are most likely to lead to success. The reward function, which is the core element in shaping the behavior of the RL chain. By adjusting this function, you can fine-tune the chain's preferences for certain actions or outcomes. The RL chain itself, which is trained to maximize its reward using an algorithm like q-learning or policy gradient methods. Fine-tuning the chain involves adjusting the parameters of this algorithm, like learning rate or exploration rate. The reward function may not accurately represent the desired outcome, potentially leading to suboptimal behavior in the RL chain. Define a reward function that is closely aligned with the goals of the task. For example, if the RL chain is a chatbot, a reward function could be based on user satisfaction, fluency of responses, and factual accuracy. The RL chain may struggle to learn effectively due to factors like a poorly chosen algorithm or insufficient data. Consider using a more powerful RL algorithm, such as deep q-learning or proximal policy optimization, or employing techniques like transfer learning to improve the chain's ability to learn. Langchain experimental RL chain, a reinforcement learning chain that aims to improve the performance of language models. Inputs: the text or prompt that the language model will be trained on. A function that defines the reward for the language model, encouraging it to produce desired outputs. Outputs: an improved language model that has been trained using reinforcement learning techniques. A strategy or policy that guides the language model in generating text. This policy is learned through the reinforcement learning process. Steps: the initial language model is set up and prepared for training. The specific reward function is defined, which determines how the model will be rewarded based on its generated outputs. The model is trained using a reinforcement learning algorithm, where it learns to maximize its reward through interactions with the environment, the text and pay. Reward function: the performance of the trained model is evaluated to assess its effectiveness in generating desired outputs. Prerequisites: Python version 3.7 or later is required for this chain to function. LangChain is a library that provides tools for building and working with language models. It is essential for this chain. TensorFlow or PyTorch are deep learning frameworks that are necessary for implementing pay. Reinforcement learning algorithms used in this chain. Fine-tune parameters. Learning rate controls the size of steps taken during the model's training process. Adjusting this parameter can influence the speed and stability of learning. Discount factor determines the importance of future rewards compared to immediate rewards. A higher discount factor emphasizes long-term benefits. Number of training epochs represents the number of times the entire training data set is processed during the training phase. Increasing this parameter allows for more extensive training. Batch size defines the number of training examples processed together in each iteration. Smaller batch sizes can provide more frequent updates but may be slower. Challenges and fixes. Designing an effective reward function is crucial for guiding the language model towards desired behavior. Combining multiple reward functions can provide a more comprehensive and nuanced assessment of a model's performance, encouraging it to excel in various aspects. The training process can be unstable and prone to fluctuations. Adjusting the learning rate can help stabilize training and prevent oscillations. Using a smaller batch size can introduce more frequent updates and potentially improve stability. Increasing the number of training epochs can allow the model to learn more effectively and overcome potential instabilities. Overfitting occurs when the model learns the training data too well, resulting in poor generalization to new data. Regularization techniques, such as adding penalties to model complexity, can prevent overfitting. Providing more diverse and extensive data to the training set helps the model generalize better to unseen data. Early stopping, which terminates the training process before the model overfits, can help maintain good generalization performance.